decomposition model. And as I've shown before, these ideas of over decomposition in CHARM++ and message-driven execution and migratability, and based on that, the introspective and adaptive runtime system actually lead to a variety of benefits, including like power and energy optimizations or fault tolerance. I already mentioned dynamic load balancing, and the fact that you know what's running next can lead to a variety of things like perfect prefetch and so on and so forth. So these capabilities are mentioned here, some of them. Then the programming systems developed on top of this runtime is, of course, in addition to CHARM++, there is adaptive MPI, which is a full-fledged MPI implementation. I will say a bit more about it later. CHARM4Py, which is evolving towards a well-supported implementation at CharmWorks. Charades, which is being renamed to CharmDes, which is a discrete event simulation system. And then there are several experimental languages, and you'll hear a bit about them in the workshop as well. And I really, those of you into language design, CHARM++ and Converse are an excellent substrate for designing your own higher level languages with adaptive runtime basis. One of the useful things you get from that is composability. Different modules can interleave their execution on nodes when they're written with this message-driven runtime system. Many example applications, there are dozens. I just listed a few here. Of the most well-known, maybe NAMD, but there are several others, and you hear from some of them today and tomorrow. There are application papers. I just thought, since the slides will be there, that maybe if I want to point just a few papers to look at, those would be some examples, but there are many more on our website. And just a brief point about current state. We have work on energy control by turning cores on and off dynamically that happened last year. Adaptive MPI is now substantially improved and at a point where you can just use it for your MPI application without worrying too much about anything. We have automatic ways of running MPI code virtualized. That's one thing that AMPI needs is encapsulation of your global variables, which is a good thing in general, but most codes don't have it, and we provide it automatically. New codes can easily accommodate this in the way they write it. So, as with standard compliance, with performance, with automatic ways of running MPI codes, it is well near a production system and being used. Communication optimizations is something that I hope you'll hear a bit about in the workshop. But the over decomposition automatically gives you the ability to spread communication over time, but multiple cores and GPUs add some nuances to it. You will hear about that. I will, since I'm running out of time, I will not say much about this. Then some grants I will mention. AstroTrees for cosmology, Prevents is for storm surge simulations, and energy optimization at AMPI I already mentioned. Michael Robson's PhD thesis was finished last year, and you will hear from that project as well. And at CharmWorks, there are many projects that are proceeding. In addition to the AMPI, which we will be renamed and relaunched as CharmMPI, and Charades, which will be launched as CharmDes. And so those are the things that are coming from CharmWorks. Probably worth clarifying the relationship with CharmWorks. CharmWorks is a spin-off from our university research group. And the hope is that it will do more engineering work there and leave us to do research in our group. Although historically the strength of our research group has been the engineering work that we do, so we'll hopefully continue to do that as well at Illinois. The versions, the CHARM++ is certainly available for all nonprofits through the university, and that will continue to be so. And we are merging up all the work that we are doing at CharmWorks so far. I'm announcing a weekly webinar series starting next week, but the details of that are not quite fixed. So watch this space. Maybe by tomorrow I'll fix some details and announce them. The workshop itself, we have a keynote by Jeffrey Vedder today. We have talks on CFD, on the Quinoa project, and by Joseph Bokosi's team. We have Lawrence Rauschenberger talk about his graph processing. There's going to be 3 talks from 3 completely different groups on cosmologies. For whatever reason, cosmology has emerged as a area where there are many CHAM++ based codes. Electronic structure, open atom, there'll be 2 talks on that. Storm surge simulations, there'll be a joint talk on that today. And the system talks on adaptive MPI and loop parallelism. Tomorrow, there'll be keynotes by Hartmut and John Malcolmi. There'll be talks on Dharma system, a couple of them actually, talked by Abhinav Batele and Jaemin Choi on GPUs and languages, and on vector load balancing by Ronak. And there'll be an AMD talk. And then in the end, we'll have some sort of a user group discussion preceded by the release of the next version of CHAM++. That is all I wanted to say. I will stop with that. And pause for a second. I don't know if there is, Jamin, Matthias, is there anything any question in the chat that I or you need to address?
There was a question on MPIO, but Sam also answered it in the chat.
Okay. Anything that you want the audience to know? Otherwise, I'll start my next session and don my other hat. Give me a second to do that. I see. Jeff, can you get your screen sharing started?
Sure. Did that work?
Yep.
Very good.
Just give me a minute now and I'll get my act together here. All right. So I'm so happy to see Jeff here for a talk, although it would have been really nice to have him back at Illinois. He's, for those of you who don't know, spent several years at Illinois as well. I forget exactly how many, but and so that was 15, 20 years ago. Jeff Vedder is a corporate fellow and a group leader, founding group leader of Future Technologies Group and at ORNL. He graduated from Georgia Tech, then spent some time at Lawrence Livermore and also at Illinois before joining Oak Ridge. And he has been working on a variety of things, but the Future Technology says it all. We would like to be considered a future technology, but we are a future technology forever. So we'll see how that goes. But in any case, I think Jeff's focus is on future technologies, especially in all the hardware technologies that are arising in the exascale space and shepherding them through the DOE ecosystem. He has a talk that's very relevant to that theme, preparing for extreme heterogeneity in high performance computing. And without further ado, Jeff.
Thank you, and thanks for that kind introduction. I too wish I could have been in Illinois visiting again. Every time I'm there, I try to drop by Papa Del's and get some pizza or something. And so maybe we can do it next year, hopefully, if things shape up. So I really enjoyed your overview as well. You guys have certainly been one of the leaders in the field of intelligent runtime systems. And so that's something that's going to come up later. I'll say a few words about. And so today I'm going to talk about extreme heterogeneity. And that's really a word we started applying to the diversity of architectures we see coming in HPC. And so if you want the highlights of my talk, first, it's no secret that trends in computing paint an ambiguous future for future architectures. And by that, I mean, there's a lot of different directions that architectures can take in a very short amount of time. And so ultimately, this is leading to a lot more complexity. And we're labeling this extreme heterogeneity. But the outcome of that is that I believe that applications and software systems are really starting to reach a state of a crisis, right? And so if you believe that the hardware really is going down this road of mass customization and domain-specific computing, how do you build software for that? And so you have to have things like programming and operating systems, runtime systems that are portable across all these architectures, and they have to have some element of performance portability, right? And then the other things, just like architectures, how do you know the systems you're buying today will be faster than the systems you already have on the floor? It gets very complicated. And so that's something that I'll say a couple words about. The programming systems are really the layer that insulate the users from this. And functional portability, we all know about. Performance portability is the big challenge, and trying to hide as much of that from the users as possible. I think we ought to strive for a write once, run anywhere model. I know that might be an impossible goal in some sense, but ultimately we want the applications teams to be able to write their code and with minimal modifications or compiler changes, port to a new architecture. We need things like descriptive models of parallelism and data movement inside of the application that's portable across architectures. We need introspective runtime systems. And maybe most importantly, we need layered modular open source approaches. And I say that because, you see with the emergence of LLVM, I think one of the largest strengths of LLVM is this idea that it's got a very permissive license. So companies can contribute to it, can pick it up and use it, can ship it with their products without any real restrictions. And so it makes it very easy for people to extend and buy into that approach. I'm going to talk about 3 examples. And so the first one is there's investments in LLVM. I'm going to highlight a couple of those. The first one will be Fortran in LLVM, as well as the GPU offloading. We've got several efforts there in ECP. The second one is programming FPGAs. FPGAs have been around forever. But it's more likely than ever we're going to see some element of reconfigurable computing in a future architecture. And then finally, memory systems are changing too. We all know about GPUs and processors changing, but memory systems are changing, and that's going to lead to maybe even a more fundamental shift in the way we program our systems. So first, I always like to motivate this with a poll just to give you an idea of what we're encountering. Think back 10 years. How many of you would have predicted that many of our top HPC systems would be heterogeneous architectures today? And that is GPU based. We see that everywhere. Of course, I usually, when I do this talk live, I get about 20% of the people that say they foresaw that. And if you look at the growth in things like GTC for NVIDIA and other places, it kind of corresponds to that. Then now think forward 10 years. So this is where it gets really interesting. How many of you would predict that our top 100 HPC systems will have some or all of these architectural features? And assume we can get a multi-purpose, a general purpose multi-core CPU there, but there's a vast array of opportunities, right? First, a GPU. Everyone expects to see a GPU there. Reconfigurable architecture, neuromorphic, deep learning processor, maybe a quantum processor. There are believers, there's a huge amount of money going into quantum computing these days. How about a RISC-V processor? With NVIDIA buying ARM, that makes RISC-V a lot more attractive to the community. Some new unknown processor. I mean, the TPU and some of those things didn't exist several years ago that we knew of, and they might just pop on the scene, right? And then finally, kind of all of these in one node or one MCM that allows you to really compose the chip that you need for your target. Okay, now think about that, and then bring it home to the applications. Now imagine you're building a new application with an expected 3 million lines of code and 20 team members over the next 10 years. What on-node programming system do you use to future-proof your application? And again, make some basic assumptions. Say you have C and C++. There are a huge number of choices there. And so one of the things I'm going to talk about later is the fact that there are a lot of choices that and many of them are incomplete or not performing up to the levels people expect. But here we have just things like Fortran. We have domain-specific languages. We have proprietary languages like CUDA, directive-based languages. And then we have, of course, Legion, Charm, HPX, a lot of different programming models out there that people can choose from. Now, remember, when applications teams buy into this, they expect the model to last for 10 years, and they expect to have an ecosystem as well as support and other things that keep it ported to future platforms. And so there's a huge amount of sustainability that's required in that choice for the future. And of course, it could be some new unknown programming approach at this point. It could be TensorFlow. Where was TensorFlow 5 years ago? And of course, some combination. So that's the motive, kind of the overarching view of my talk is that's the problem we're facing in places like DOE. And so let's dive down into motivating trends. Some people still don't see this domain-specific computing as a real future. And so I always like to have that discussion just to make sure people understand where we're going. So if you think about architectures, everyone knows the Moore's law arguments and Dennard scaling. I like to point to the economics, right? If you look at this chart and you see how many foundries there are compared to a decade ago, you see it's shrinking very quickly. So one of the things you get from that is the fact that vendors are going to be have difficulty differentiating themselves based on their process because everybody's going to be using the same process. And so they're going to start doing domain-specific computing to target specific markets. And if there's an impact there, it impacts your plans, our plans, like you see with Aurora and Intel having a delay. That changes people's plans. And so it may end up changing other features of the system like their programming model. And you see this happening more broadly. The whole business climate is very aggressively positioned for mergers and acquisitions right now. And then you see AMD buying Xilinx, or trying to buy Xilinx. You see NVIDIA acquiring Mellanox and now trying to buy ARM. That's a big deal because, like I said earlier, there's potential to change the roadmaps for all of these companies and having them sorry, I had a bleep on the screen. Can you still hear me?
Yes, we can still hear you, Jeffrey.
Okay, I'm sorry. The, like I mentioned earlier, with NVIDIA trying to acquire ARM, a lot of companies have publicly stated they're going to start looking at RISC-V as an alternative to ARM at this point, just because they're worried about the potential proprietary turn that ARM might take. So in the general sense, I love this diagram by Kurzweil out of one of his books, and it shows kind of the trajectory over the last century of computing. And you see in the past 50 years, we've been in this integrated circuit phase, and it's a wonderful technology, probably nothing like it's ever happened before. And really, optimistically, we're just entering this transition period where we're moving into the sixth wave of computing, and we're not quite sure what that is going to be, but there's certainly going to be a transition period. So if we think about being in that transition period, what are the things that we should be doing as researchers? Well, the first one is optimizing software and exposing new levels of parallelism. And this is something that you've done, I've done, a lot of the people, especially in the HPC community, is focused on for decades, right? The second one is the emerging technologies. And as I mentioned earlier, quantum is getting a massive amount of funding and interest right now. Then you have neuromorphic, you also have advanced digital like carbon nanotube computing, and even emerging memory devices like Optane, memristors, and other types of devices. The challenge there is that with quantum computing, if you look at the NAE report that came out last year, there are probably at least 10 years before we see a practical application of quantum computing if they meet some of the milestones that you see here in this chart on the right. So there's a lot to do, right, in that 10 years to be able to apply it to something like RSA encryption. Here's a fun question for you, just in context of this. We know how important a field effect transistor has been. When was it patented? Anyone want to venture a guess there? So I get a lot of guesses, and people say things like 1947 because that's around the time AT&T and Shockley and others were looking at it. But it was actually 1926. The patent had expired on field effect transistor before the Shockley work even happened, right, and got all its notoriety. And so the moral of this story is that it may take decades for this technology to become manufacturable, economical, and usable in some way. You need to keep your eye on it, but of course it could be a long, long time before it comes to fruition. So that kind of bounds the spectrum, right? And what I'm going to focus on today is this architectural specialization and integration. And as I mentioned earlier, it really is using CMOS more effectively for specific workloads and domain-specific computing. And so, 2 minutes. Various markets are already experiencing this. We've been looking at these systems on a chip, as I'm sure others have, things like the Snapdragon, the Xavier from NVIDIA. Are very complex. And today they already have, the Xavier, for example, has ARM cores in a multi-core configuration, and has Volta cores for the GPU. It has a deep learning accelerator. It has a vision accelerator, and so on. And then if you just look at the AI chip landscape out there, there are literally hundreds of companies trying to build hardware specialized for AI. So we definitely see this trend happening elsewhere. And we're seeing it happen in DOE. And so if you scroll back a few years, we were really focused on multi-core. And that goes back to even Blue Gene and Jaguar and some of those systems. They were slightly different than your normal desktop system, but that's what they were. And then starting in about 2012, GPUs came onto the scene, and NVIDIA really owned that space for, not quite a decade, but almost. And so you had some choices there with Knights Landing as well. But now we're moving into this plan where the exascale systems that DOE has announced include a AMD CPU GPU system called Frontier here at Oak Ridge, an Intel CPU GPU system at Argonne, and then some of the other systems like Perlmutter at LBNL with the NVIDIA system. And so if you're a user of DOE systems and you run your climate model or your fusion models on these systems, right now you have to prepare for all three of those, or ultimately you would like to prepare for all three of those, right? You wouldn't want to buy a system and have to program specifically for that particular system. And then just to round this out, the idea that DARPA has that I subscribe to somewhat is this one of an open source hardware world, where it makes it very easy to rapidly design chips that are specialized and essentially have mass customization. And you've all heard about RISC-V, and it seems to be blossoming right now after 10 years, as well as DARPA has a couple programs that create this universal hardware compiler from top to bottom. And that's been one of the expensive parts of building a chip in the past. And we hope that this will succeed. I love this picture Andreas has put on his slide that shows him on the beach uploading his output from his universal compiler to a company like Amazon, and they basically fab the chip and send it to him in a couple of weeks in a box, and he can plug it in and use it, right? But what about the software, right? How do we write software for those systems? And so that's really the takeaway message is we're in this sixth wave transition. We have this Cambrian explosion of architectures. The first question is, how do we design the right architectures? How do we know that we're building systems that can fit our workloads? The second thing is programmability. And this is something that we've had a couple workshops on. We call it extreme heterogeneity. But the idea is, how do you have some level of performance portability across systems as diverse as the SoCs I showed you earlier? And one key here is the software lasts much longer than any of the transient hardware platforms that we have. You know, on occasion in DOE, you'll see a system last maybe 6 years, but in most cases, it's about 5. And so many software packages last longer than that. So the implications that we need to think about in our community in computer science is, again, this explosion of incomplete programming systems, right? So if you look at the ECP systems that I just showed you, this is a partial list of the programming models being offered to the applications teams to prepare for those systems, right? And so there's a very confusing picture because all of these have implementations. They all have different performance and different support models. Some of them are open source, some of them are not. How do you decide, right? And just looking at SYCL, which has been advocated by Intel recently, if you just look at the implementations there, you've got, you know, a company as big as Intel building a SYCL implementation, and then you have, you know, a university doing it. And they run on different platforms, they have different support models, they have different performance. We've measured performance variance of as much as an order of magnitude, where you take SYCL and run it on a specific architecture and a specific application on a specific architecture, and that order of magnitude difference comes from just the SYCL implementation you use. So there's a huge amount of performance variability there. So that was kind of the motivating trends, and I hope you're, you know, convinced that you know, even if we don't make it to the age of mass customization, we're headed into a future that's a lot more diverse. And so let's now talk about some of the strategies we've been using to try to approach this and prepare for it. So as I mentioned earlier, the overall goals for this are really to strive for write once, run anywhere application. And again, if you are working in DOE and in ECP, we have about 25 application teams with on the order of 50 applications. They have to make serious choices about how their code is going to be written, what programming models and libraries they're going to use. And it's very, you know, a very important decision for them. They've been looking for more descriptive models to kind of divorce the applications from the architectures. But ultimately, as a computer scientist, I think we really have to focus on this layered modular open source approach. And one organization can't do it all. I mean, it's come to that where a compiler is such a massive effort that, you know, you have to get contributions from many different people to keep it vibrant and alive and active. So I'm going to talk about 3 examples here. The first one is contributing to LLVM, and in ECP, we've got a major investment in LLVM, and one of those investments is Fortran for LLVM, and it includes GPU offloading, which has been a problem over time. The second one is programming FPGAs. And as I said earlier, every computer engineer gets introduced to FPGAs at some time and you know, thinks of the possibilities, but then you hit the programming challenges and it's a lot less fun at that point. And then memory systems are changing too. Don't forget about memory. There's a lot of new technologies coming on the market that are going to diversify in the same way. So let's talk about LLVM. So if you look at contributing to LLVM, that's in the context of ECP. And if you're not sure what ECP is, you can go to the web and search it. It is the Exascale Computing Project. It's the largest program in the Office of Science right now, over $1 billion. And so it's really funding the development of 25 applications for these exascale systems, the software technology to try to mitigate some of these challenges that I was talking about. We have almost 80 products that are being bundled in SDKs right now that are openly available. And then the hardware and integration, where we've been working with specific vendors to advance some of their technology and just make sure that some of the important components, the critical components, get improved. And so in that, one of the projects that I manage is the LLVM compiler ecosystem. And so this slide really summarizes that. And there's, again, a lot more information that I can point you to if you have questions on these. But we all agree LLVM is a very popular open source compiler infrastructure at this point, and its permissive license makes it used almost everywhere in heterogeneous computing. Almost everyone's heterogeneous compiler is based on LLVM at this point. We have a project Solve led by Barbara Chapman at Stony Brook that's focusing on OpenMP support in LLVM, in particular offload. We've got Proteus Tune here at Oak Ridge, and it focuses on core optimizations to LLVM, but also OpenACC capability in LLVM, both in the Clang front end and in the new Fortran front end. The FLANG project is a project that was started several years ago by NNSA, and it essentially is asked PGI, NVIDIA to open source their Fortran front end and put it into LLVM. And so most of that's finished. If you look at the parser and the front end portions of it, it's in LLVM now. You don't get an executable when you compile with that, but that's the plan, and there's a lot of work going on to support that. Likewise, there's support for OpenMP and OpenACC and Fortran that we're putting in there. We have HPC Toolkit, and I understand John's going to give a talk, so he'll tell you more about that. But they've been focusing on some of the profiling interfaces and other improvements in that regard to OpenMP and side of LLVM. And then finally, ATDM is the NNSA projects, and they've been doing things like looking at just-in-time compilation for template expansion for some of these metaprogramming models that are popular now, as well as testing of FLANG. And then we have many collaborations with the different vendors, trying to coordinate and keep in touch with all the contributions that are being made in the areas that I mentioned. So just to give you a snapshot, this project is Fortran, and it's very popular still in DOE. We approximately half our applications still have some element of Fortran in them, and it's preferred. I like to call it the original domain-specific language, right? It's a domain-specific language for scientific computing. And over the years, the support's varied. And so one of the things we want to have is a very strong open source Fortran compiler. And so the FLANG project is leading that with NVIDIA and PGI. And then, as I mentioned earlier, we have Solve, Proteus Tune, and other projects contributing to this to make it a solid compiler that will satisfy our problems. If you look at the diagram on the right, one of the things I wanted to comment on here was that we have, leveraged the LLVM community and infrastructure very strongly when we're doing this. One of the things that the Fortran parser will do is lower that representation, that Fortran representation, into MLIR, which is something that Google contributed earlier this year to LLVM. And it's a multi-level intermediate representation so that you can go in and create dialects, like in dialect for OpenACC or dialect for OpenMP or dialect for GPUs, and then have that representation persist inside of the compiler while it's compiling, so you can make more intelligent decisions about code generation. And then as you lower it, you can eventually lower it to directly to something like the SPIR-V-IR or the LLVM-IR, and then generate your code. And the idea is that once you create that OpenACC dialect in MLIR, that anybody that uses MLIR and wants to use OpenACC can make use of it. And so that's been a big win. The second one is a project here at Oak Ridge that is being led by Joel Denny, and he is trying to add OpenACC support to Clang. And so if you look at the current status of LLVM and Clang, it supports OpenMP, and what we wanted to do was extend that to OpenACC. On our current Summit system, CUDA is the #1 programming model, and OpenACC is the second most popular programming model. And so we need some support for OpenACC. And so the project in ECP that's addressing that is this CLAC project. And the way we're doing it again is we're not creating a compiler on our own. We're taking LLVM and adapting it to provide this. So if you look at the diagram on the right, essentially what's happening is you take your OpenACC source, you create the AST, and then you transform it into a new AST that's the OpenMP version of that, because the OpenMP infrastructure has been there for a while. It's got a lot more, it's had a lot more investments made in it. And so we just wanted to make that transformation, because you're taking OpenACC and lowering it to essentially OpenMP. And then at that point, you can actually just generate the code straight away in LLVM, or you can actually output it to OpenMP and then take it, and perhaps if you have another OpenMP compiler that you don't have access to in LLVM, you can generate the OpenMP source and recompile it for the target that way. And so that's the two real highlights from ECP. There are many others. I'm sure John will mention some of his work during his talk. But those are really important, because there's no way we could build a compiler on our own. We're leveraging LLVM to do that, and we think it'll last. I mean, some of these things like a Fortran compiler and LLVM could last for 20 years or more, right? Okay, moving on. So the second example is FPGAs, and I said earlier, FPGAs are well known. They're exciting. Everybody, does some project in graduate school focusing on FPGA and realize it's really neat technology. But it's also hampered by, programmability and some portability issues. And a lot of times you have to use HLSs or actually write HDLs using something like Verilog to get good performance out of these devices. That is typically not portable, and it's usually not an open standard, right? Each company has its own tool chain that has to be licensed and paid for and all of that. What we were looking at coming from HPC is there a way we can really insert FPGAs into our portfolio without disrupting the users that much? We can't go teach climate scientists how to do Verilog. It's just not going to happen on a large scale, and they wouldn't want that in their code base anyway, right? So one of the things we first thought about was OpenCL, and some of the vendors, Altera and Xilinx, had started creating their own OpenCL implementations. And so that got us thinking that we already had a directive-based compiler that's at a higher level that could generate that OpenCL directly. And so, most of the OpenACC and OpenMP compilers really only targeted specific architectures, but we wanted to see what we could get out of that. And so what we did there was we have a research compiler called OpenArc. It is a compiler that Seong Lee spearheaded during his PhD about 10 years ago at Purdue. And basically what you see on the right is an illustration of how OpenArc works. And if you look at that, we have our OpenArc front end that really has its own MLIR-like high-level intermediate representation. And that's a real benefit for us, because we can do some high-level optimizations on things like nested loops, or different types of data layouts at that high level and not have to recover that information from the LLVM IR. But here we generate our own OpenArc IR, and then it gets sent to the back end, and the back end essentially generates kernels and the host program from that. And then it gets compiled with the downstream tool chain, which would be an NVCC or the FPGA OpenCL compiler. And on the right, you see some of the support we have with that. We have CUDA, AMD, OpenCL, Xeon Phi, and we were adding Altera's FPGA here, and they have an OpenCL. And of course, we've got to map in the runtime system for each one of those, which have kernel launch and data movement, direct data movement routines. And we did that pretty easily by creating our own library. So this is what we did. A couple highlights here. The real goal was to write the code once and run it across all the architectures that OpenACC supported. So we were hoping that we would not have to add any specialized features for FPGAs. We would be able to run that code across NVIDIA and AMD and Altera without any problem. We did find that there were some things that were more difficult to do for FPGAs than others. And so we added some optimizations. Now, some of these optimizations we did manually at first, but some of them we found ways to automate. And so what I'm going to walk through is just kind of the overall design, and then I'll give you a idea of what the optimizations are so that you can see that, yes, it is possible to do this and use OpenACC to FPGA. So yes, as I mentioned, it works like our other compiler for GPUs worked, where we generated the OpenCL backend. We didn't find a way to speed up the OpenCL to bitstream compilation process. That still took some time, but fortunately that could be insulated from the users. If you look at an FPGA, the OpenCL architecture maps on to the FPGA in the following way. You have the host processor on the left that's connected with a PCIe to the global memory interconnect, and then you have some external memory on your FPGA. But more importantly, you have some local memory and basically a variable number of kernels and compute units that you can tune. And this is where some of the auto-tuning technology can help a lot. First, you've got a pipeline depth that basically you can change for the different loops that you're synthesizing. You can also have a vector width that you can change. And then you have this replicated number of compute units that really you can scale up to fill up the number of LUTs or bits that you have in the FPGA. And so that is a bit more of a complex auto-tuning activity, but if you want optimal energy efficiency out of your device and good performance, then you really need to find those saddle points in the optimization process. One of the optimizations that we found that was really important was the following. This is a kernel pipelining transformation. So if you just generate an OpenACC program and have it write kernels out, essentially what it does is take each loop and create a kernel for it. So it could be a nested loop, but most of those get offloaded that way. And so when you annotate those loops, it by default just creates those kernel offloads that way. It doesn't really do a lot of inner loop analysis to look at the data reuse or anything like that. And so in an FPGA, that tends to be a real problem, because if you use something like Altera's OpenCL, it'll force you to read from global memory and write from global memory by default every kernel iteration. And so this is very expensive, as you would imagine. Altera and Xilinx both have some proprietary extensions that allow you to take data from kernel 1 and pass it to kernel 2 directly in the system. Now, the data access patterns have to match up, and you have to guarantee that. But as you'll see in a moment, we believe we can add some OpenACC extensions to satisfy that. So if you look at the input OpenACC code on top, it's just pretty straightforward the way someone would write this type of annotation, right? You use the present modifiers to tell the system where the data is living, and then it would compile these two kernels, and you get the behavior that I meant, the bad behavior that I mentioned earlier. The Altera OpenCL code with channels allows you to use a channel, what they call a channel, to pipe the data from one kernel to the next. And so that's what you see here in an abbreviated form. What we did was create an extension to OpenACC called pipe that basically makes that connection. And so user, instead of annotating it like they do above, would actually do it like you see at the bottom, where you create a pipe, and then you annotate the loops with a pipe out and a pipe in directive. And the nice thing about these is they deprecate really well. So if you don't have an FPGA or you don't have a channel capability, it'll just default back to the behavior that works, but it just may not perform as well. And so when we have that transformation, we see a big boost in performance, and in the results I show in a few minutes, you can see what kind of difference that makes. There are several other optimizations that we found as well. There are things like reductions and sliding windows for convolutions or other types of analysis that can use shift registers. And shift registers are very fast in FPGAs. Some of those can be detected automatically based on the semantics you find in OpenACC and OpenMP right now. If you kind of roll that all together and put it in one slide, this is the takeaway slide from our OpenARC FPGA evaluation. This is a couple years old, so it was on a Stratix 5, and we have Stratix 10 now. We're starting to repeat some of these experiments and seeing even better results for the FPGA. But the takeaway message here is that yes, you do see the FPGA perform poorly on a few of the kernels, and specifically the ones with random memory access patterns like sparse MATVEC. But on others, you see surprisingly good performance. And so especially on the FFT1D and FFT2D, you're seeing even better performance than the GPUs. And GPUs are very good at floating point. And that's why, it's kind of pushed out the whole FPGA revolution, is because GPUs do floating point really well. The takeaway message here is that when you have pipelines that you can keep full and generate long pipelines, you can see even better performance than you can on those GPUs for floating point computation. And so that's a summary of FPGAs. Finally, I wanted to turn the tables a minute and focus on emerging memory systems. Almost everything I've talked to you about up till now has been on processors, and yes, processors are the thing that get a lot of attention. But if you look at all the architectures I mentioned earlier, they really are getting a wide range of memories in them. Everything from your normal DDR4, DDR5 to HBM2, to non-volatile memory, to specialized memories like texture memory in a GPU. And so those are in some ways more important, I think, than the processors, but they're less studied in most sense. And I love this slide by IMEC. It really shows you what's happening in the memory market. There's a huge amount of effort in what I would call storage class memory, where you see the red arrow here. There are your traditional technologies for registers and caches like SRAM, and then you move into technologies for DRAM, but they're seeing a whole new class of memories in storage class memory. And this is Optane. It's what you see a lot of memristors, and other things like that. And so again, that's diversifying. And I think it's going to be driven by, again, the cost and the capacity that people need for their problems. And so that's really something to keep an eye on. NVRAM is what I'm going to focus on today. If you've looked out across the space, it's sometimes hard to believe that you can buy non-volatile memory at the capacities that you see. I mean, I like to take a lot of pictures. Nowadays, you can buy a card as big as your thumbnail that holds over a terabyte, right? That's almost inconceivable. And then you look at the price, and it's, while shocking here, just a few years ago, that would have been price prohibitive, right? And so there's a lot of I think, changes coming in HPC architectures based on the availability of this cheap memory. If you think about that and then say, okay, how are users going to use this non-volatile memory? One choice is you just use it as a cheap bulk memory, and you don't worry about persistence. You just say, look, I've got this huge amount of memory, and I'm going to treat it like scratch and not really benefit from the persistence. But we wanted to take a different approach and think more carefully about how you might exploit that persistence. And think about things like checkpoints. I mean, what you do nowadays with checkpoints is really snapshot the progress of the state of the application so that you can both restart it at one of those points or take one of those checkpoints and make a visualization out of it or track the results of your application. In some ways, though, that's just a representation of the changing state of the application over time. And if that was all stored in non-volatile memory, there may be a lot of clever things you could do to both save amounts of memory and perhaps even improve the performance of your application because you don't have slow I/O ops that you need to worry about. So non-volatile C is a project we started to look at language support for non-volatile memory. And it's really this idea of extending C to support non-volatile memory. So one of the first design goals we had was to look at something that was familiar. Like I mentioned earlier, you've got 50 applications out there. You can't easily start off with a new language, right? It just makes it really hard for the apps teams to embrace. But we wanted to try and add some extensions to C. And so what we did was limit our changes in C to type qualifiers and pragmas. And so on the left-hand side, you see some of those. We have a header file. NVL is a type qualifier that indicates that that's going to be pointing to non-volatile memory, for example. And then we had some memory allocation routines we had to supply so that you could actually load those non-volatile heaps and interact with them. And it's really a superset of C, so we believe it could be easily used. The other thing you have to worry about, if you're using cheap bulk memory, you really don't worry about the persistent data corruption, right? And so what we wanted to do, again, we're worried about persistence. So once you corrupt the data, it's very much like corrupting a file system. If it's written out in a way that maybe your linked list has a bad pointer in it, it's very hard to recover that later on when you notice it. And so this is where you can introduce a new category of pointer bugs when you're thinking about non-volatile memory, and I'll show you an illustration of that in a second. But also, you want to make it high performance. You can't, log every load and store. You really need to use optimization so that you can track what's going on and be able to recover it if you do find something that's corrupt. We settled on using transactions for that, and I'll give you an illustration of that in a moment. Our implementation was pretty straightforward. What we did was take OpenArc, which I've mentioned already, and we added our type qualifiers and pragmas for transactions and created our own IR that had that meta information in the IR. And then we would do our passes on that IR to generate LLVM IR. And the LLVM IR would be annotated with the type information and other things that we use the LLVM infrastructure to check the types of and check for correctness in. And then LLVM would just generate the backend target as it normally does. And then we link it with a novel C runtime, and that would, at that time, we were using the PMEM object from library, PMEM object library from Intel. And so that's available. It's open source, so you can go download it. It provides routines to manage non-volatile memory on SSDs as well as Optane and others. Here's what it looks like. So just again, we have minimal changes to C. You can still use DRAM, right? You don't have really any real differences there other than just the annotations. And you can intermix pointers between volatile and non-volatile memory. The pointer safety is something that gets checked automatically in the system. The transactions help you take snapshots of the changes you're making and do them atomically to keep the state from becoming inconsistent. And then there's a range of optimizations we applied. Now, I can't get into all of those today. And so if you're interested, you can maybe look at the paper we have here listed at the bottom. But again, it was built on LLVM. The pointers themselves are like what we used to call, fat pointers. They are bigger than a normal architecture pointer, like a 64-bit pointer, because it has to have some metadata that you track along with it. If any of you have used UPC or some of those other programming models, it's kind of the same concept. It allows you to, in this example, you open the heap, you interact with the runtime system, and then once you get that pointer to the node in this example, you can start walking the node and modifying it as you normally would in a volatile memory program, right? The nice thing about this is it really does facilitate compiler analysis of these pointers so that you can find out that you have an error when you try to do something incorrect. And so I already mentioned the wide pointers. Those wide pointers, another point about that is that you have to hoist a lot of the metadata out of loops, important compute intensive loops. And that's actually very important because, if you can just rely on that load store address, the compiler is fantastic at optimizing that on the back end. But if you have that fat pointer in there, you really need to hoist that out and do some of your bookkeeping before you get started in that loop. Simple example of how this works is the programming model when you want to access the non-volatile memory. And the best way to think about this is your volatile memory is normal, and it's your stack and BSS and heap. But now you have this non-volatile memory, and you can kind of roughly think of it as a file. Maybe the file gets read in to non-volatile memory, or maybe your file system just gives you a pointer to that memory because it's already available in the node that you're working on. And so you open that, you get a pointer to that heap, and then that's just a pointer to the heap. Then you want to actually get access to some piece of data in that heap. And that's where the root pointer is a routine that you have to ask it to get the root of that tree or whatever structure you have there. And then you can start operating on it. And it's typecast and everything just the way you would expect it to be here with a T. Now, some of the pointer problems that you run into are these. You can have things like volatile to non-volatile memory pointers, but you can't have non-volatile to volatile memory pointers, right? And these are the kinds of things the compiler can really analyze in depth and give you warnings about. If you look at the bottom example here, just think about it for a minute. You have a non-volatile heap B, and you've stored in it an address of a volatile piece of memory. So when some other application loads in non-volatile heap B, it has no idea what the state of that volatile memory is. And so it would just be wrong. And so basically that gets flagged as a compile time error. There are some other things that happen. There are some runtime checks that happen looking at, for example, the inner heap non-volatile to non-volatile memory pointers. And that is where some of the metadata we use in the wide pointers helps us. We can check for those things at runtime. So finally, the transactions are just a way to ensure data consistency. So the big challenge here is you're updating multiple attributes to a single data structure, or perhaps even multiple data structures. And you want all of them to occur atomically. And so what we added were pragmas to give you that capability to actually make a transaction. And we create an undo or a redo log. We experimented with both. And then if the transaction completes, those pointers get updated. If it doesn't, then it can retry. But this is important for things like unexpected application terminations for a variety of reasons, because if that structure is left in an inconsistent state, it can be very hard to recover that information. This is a simple example, just briefly. I don't want to get into too many details here to try and keep on time, but if you look at this, you see the atomic notation around that loop. The loop is obviously you don't want to create a transaction log every time you update an element of your matrix, but what you like to do is bundle those together. And so the way to do that is use compiler optimizations to find those points that make it feasible to write out the logs without too much overhead. We did add some extra pragmas here. We found it necessary to, look at things like suppressing the undo logs. So if you have some data you just created and you're not worried about what's stored there in an array, for example, you can say clobber that. Don't keep a backup of it. Just overwrite it. And so that kind of feature, some of that can be analyzed directly with the compiler, but these options are in here for just manual annotation. So finally, just to summarize this, the evaluation on Lulesh, for example, and what you see here is from SSDs. It's not from Optane. We're still working on Optane, but what you see is the normalized time. And so worse is higher and better is lower. And then you see several different strategies we used. We also used hoisting to try to get the performance better, but we also experienced a slowdown on nearly all of them. Now, the thing I wanted to mention about this is that, we're not using non-volatile memory because it's faster than DRAM. DRAM is a wonderful technology. There's virtually no persistent technology, memory technology, that's going to be faster than DRAM. But what you are doing is using it to trade off against massive amounts of storage, because it is denser and it is cheaper than DRAM. And so in the future, I could easily see people minimizing the amount of DRAM they have in the system while balancing that out with more and more non-volatile memory. And so you could maybe run a bigger problem using the non-volatile memory technology than you could otherwise. And so that's where the trade-off is really application specific. So just to summarize on the non-volatile C, I told you it's, non-volatile memory is hot. It's a new technology. It's, again, unbelievable, like some of the others. We looked at Novel C to try and figure out how to integrate some of this into a language like C with as minimal impact as possible. And then we talked about several optimizations there. We're working on the Optane DIMMs for now, but we think it'll perform even better on Optane than it did for our SSDs, and that's a work in progress. So with that, I'm going to wrap up and just remind you of what we talked about here. The first one is, I think, we are in the era of extreme heterogeneity. We are seeing a lot of complexity, and a lot of applications teams are really starting to realize that there's a crisis in front of them. The programming systems are something that's really going to have to fill that gap. There's no way around it. It might be a new programming system. It might be some of the programming systems that we improve, but that's something we need to do. And I talked about several examples here, both short-term and long-term, that can be brought to bear on this. And with that, I'll wrap up and answer any questions that you might have. Thank you very much for your time.
All right, thank you. I can't hear everyone clapping, but they are, I assure you. So as to questions, thanks to Phil Miller, who has created a Google Doc, and people have typed some questions there. We could go to those questions one at a time. I don't know who typed the first question about fat nodes. Please go ahead and.
Sure, I just pulled that up. I'm just starting to look at those now.
Oh, but I wanted to give a chance to the person who.
Oh, okay.
State. Is that possible, Jamin? You'll have to unmute.
Yeah. So I was the one who asked the question, actually.
Okay.
Yeah.
Okay.
So yeah, do you think the trend of fat nodes, where the single node performance is outpacing the internode network bandwidth, for example, with multiple GPUs per node, will continue?
Yeah, right. Yes, right now. I mean, I've looked at some of the, even the carbon nanotube technologies and other things that the DARPA is working on out that far, and you just see tighter and tighter integration and going in 3D. And so as that continues, you give the processors more memory so they can continue to work at very low latencies and very high bandwidths locally. But anytime they go outside of that realm, they're in high latency situations, let's say. Now there is silicon photonics, and if you look at Karen Bergman and some of the companies out there working in silicon photonics, again, it's one of those future technologies where there'll be a crossing point somewhere where you'll be able to have extremely high bandwidth between multi-chip modules or processors with different chiplets on it, but they have tremendous amounts of bandwidth. And so I think in the next 3 or 4 years, we may see some real silicon photonic technology that solves that problem, but that's really the only technology that I think will be there. It seems like the electrical connectivity is really starting to top out. Just the physics of it is very difficult. And so our best hope is silicon photonics.
Okay, thank you.
Sure.
David Hardy.
Yeah, hi. First, thanks for a very interesting talk. I really enjoyed it. I especially liked your looking backwards and looking forwards of these different technology trends.
Sure.
You talked about FPGA versus GPU performance on FFTs, and you mentioned that that was because FPGAs were outperforming floating point with GPUs, but I think that's maybe more a comment on the memory access.
Mm-hmm.
Just because FFTs are inherently not cache friendly, and so I think that's what might be the performance difference there, but maybe you could comment further on that.
Right. Yeah, I think you're true. I mean, I think that's true. The pipeline kind of implies regularity to the memory access pattern, right? And that's kind of what in an FPGA it looks like. And so you're defining what the data flow is. And so the longer you can do that in terms of a pipeline length, the better performance you tend to get. And so I think you're right when you think about it as being memory accessy being more important than a floating point performance. Absolutely.
Thanks.
Sure. Thank you.
I think the next question is me. Well, first of all, you win the prize for the most slides in a talk. 823. I think you're competing with C++ standard there.
Yeah.
So my question was about a slide that came before 182, because that's where I noticed the slide numbers. But basically, following up on David's question here, it's basically, if you look at those regular loops that you're trying to translate to FPGAs, which is low-hanging fruit, I assume, so that's the right thing to do, but then you're never going to be do better than GPUs, except for a few cases like the convolution. So what are the unique strengths of FPGAs that they will do better than the GPUs on like not streaming computation, I suppose. Convolutions comes to mind. I think the basic capability is the sheer number of data paths between all memory and all floating point units.
Right.
What kind of computations leverage that, and what are the plans for the compilers to address those well?
Right. Yeah, I agree. So just to back up for a minute on the FPGAs, I mean, one area where I think FPGAs will maybe get their first use in a system is not just as the accelerator. It won't be just, one accelerator and it'll be an FPGA accelerator. I think it'll be in combination with other accelerators on the chip, like I showed you earlier. And again, I'm speculating here, but I could see it being used as a specific accelerator for very specific things. Like I showed you the SoCs, and they have a vision accelerator and a deep learning accelerator and those types of things. I forget the company name, Convey. Was it Convex or Convey? I can't remember. They had the personalities, and it could be in a future supercomputer. You can't really build a workload specific supercomputer, but you could build a system that has different personalities for different jobs. And the FPGA allows you to tune that, where you download an MD accelerator and you don't compile it yourself. You maybe have an expert write it for you. And that's the library you use, the FPGA. In fact, most users wouldn't even know it's an FPGA. They would just say, I need the molecular dynamics accelerator and FFT accelerator, install those when my job loads and then use that, right? It probably still has the challenge of being a pain to compile with HLS systems and other things. And until, we see some real products and coarse grain reconfigurable architectures that raise the level of abstraction above LUTs, I think that's going to be the case. I just think you're going to have to, start talking about higher level quantities, like a load store unit and a floating point unit, and then maybe some configurable interconnect. And that's what you compile. You're not compiling every floating point unit down to a bit stream, right? That's already there for you. And so, that's a tough one, because it's just, I still don't think FPGAs are adaptable to our applications teams, right? It's going to have to be introduced in a way that it's very easy for them to use and portable. And that's where I think will, be the driving factor.
Okay, thanks. We are 7 minutes or so behind. Phil, can you confine yourself to one question for now? We can.
No need to actually address all of mine.
We'll pick one. I get to pick
part of the moderation list is that we can just pick out what
Sure.
things people have posed rather than going one by one.
Right. So a lot of yours are about non-volatile memory. So just let me ad lib here on non-volatile memory. So I've been a big fan because most of our systems don't have any local storage, and they don't have disks or SSDs on them. They've recently just started introducing non-volatile memory into the systems on every node. And I think that's important because the IO performance on these systems today is really horrible. I mean, if you look at the growth and the bandwidth to the off system storage area network, it's went up by 2x, while the size of the systems went up by 10x or more, right? And that's the way it's going to continue. And so if you start thinking about operating the system where you never move the data out of the system, there is a possibility that you could see big improvements just because you're not limited by that IO bandwidth. And it could just be using it, as a POSIX file system, but it could also be a KV store. It could be other types of things. Intel has Deos. We've created a KV store called Papyrus. And so there's, I think, a lot of opportunities out there just to get away from that bottleneck of the IO system, the POSIX-based like cluster IO system.
Okay, let's take John's question next.
John, I
Sure.
see you there.
So Jeff, I enjoyed your talk. So
Thank
I
you.
thought that actually your talk was really much like the motivation that Intel has been discussing for their one API programming model, where they're envisioning a future with FPGAs and spatial accelerators and GPUs and CPUs, and you'd like one programming model that rules them all. And I'm wondering whether you've had enough experience with one API at this point, whether you feel optimistic about this goal of this one programming model to rule them all.
Right. Well, that's one of the reasons we started doing a deep dive on SYCL. And so to understand that a little bit more, I think, one API is still really new. And so the experience with it has been limited. I mean, we've had reasonable experience. Like when we started, we ran like 38 SYCL benchmarks across the different implementations that I showed in that earlier picture. And, most of them compiled. I mean, we had a couple implementation backends that didn't work, and we highlighted those, and it's in an upcoming workshop paper. But most of them compiled. Now, we did see a wide variance in the performance of SYCL. And I really like the idea of the single source programming model. And I think that also has a lot of strengths. My biggest worry is Intel will add proprietary extensions to it like they have with DPC++, and people will start staying away from that, and then they won't see good performance, and then they'll start questioning their decision, right? And so it's and the other thing is the tools ecosystem. I mean, let's be honest, these programming languages don't exist in a vacuum. People need to be able to monitor them and debug them and those types of things. And Intel's a huge company, so they'll provide some support for that. But if I was a, betting man, I would say, right now I'm probably less than 50%. So I SYCL, and that's for SYCL, right? Just because, half of our applications in Fortran. What do the Fortran users use, right? How are they going to get any benefit out of this? And so those kind of showstoppers are not easy to change.
Thanks.
Sure. You're on mute.
Yes, I'm mute. Jim,
Oh, there you go.
do you want to take the discussion to the coffee break?
Okay.
Okay. So what I'm suggesting, in the coffee break, we're going to open breakout rooms. So you should feel like you're joining a little group around the stars or whatever, around your favorite people or around your favorite discussions. So how is that going to work, Jamin?
Yeah, so I just created the breakout rooms. So currently there's 10 of them. And yeah, you can basically choose any that you want to join, and yeah, take it from there.
Well, we probably should have like 4 and then add them more, because otherwise you'll be checking lots of empty rooms to see if there is anyone there. Anyways, where are they?
So they should be on the bottom bar where it says breakout rooms.
Is everyone else seeing, I assume, Korean?
Yeah, I do not see a breakout room. I have on other conferences, so
Let's see if this.
maybe
I see them with Korean labels.
And I updated Zoom right before my talk to make sure I had the latest version. So,
well, in that case, well, let me first thank Jeff.
yes, thank you.
Thank you very much. And I don't know what the sound of virtual clapping is, Glenn, but yes, that's what the sound we are making. Thanks a lot. And it was an interesting talk, glimpse of a variety of things that are coming down the line. Thanks again. And we'll continue. We can assume this room to be the coffee room for now, while we see the other rooms.
Sure.
And we'll resume supposed to resume in 7 minutes, but maybe we'll take 15 or 10, 15. What do you want? We need at least the bio break time. They can be parallel today.
Okay.
All right.
Thank you all so much.
Yeah. definitely there are more questions for you, Jeff. So Jim, you want to ask, presuming this to be a coffee room?
Sure. So I'm when I saw that you were extending the language to support non-volatile memory, I was a little confused because we've been treating disk-like memory and memory-like disk for at least 40 years now. If you just use, checkpointing or snapshotting of the non-volatile memory, would that satisfy most of the use cases?
Yeah, so I mean, we have thought about that. One way to think about this is any application is an evolving state, right? It has arrays and other things in it that are constantly being updated. And this idea of snapshotting that is right. That's what a checkpoint does. And that's kind of what burst buffers do. If you look at the first use for non-volatile memory in our systems, it's that burst buffer where the checkpoint data gets flashed over to the non-volatile memory, and then it bleeds out to the storage area network that I mentioned earlier that's really slow. In my view, maybe a more attractive approach to that is where you have a lot of non-volatile memory in the system, maybe not on your node perhaps, and as you make incremental changes to those arrays, you just update your logs and the copies that you're using in a way that you would in a journaling file system, right? Where things the changes are being logged, and it's making the updates as you move along. And then you have to worry about consistency and things like that. But that may be a nice way to think about it, rather than having just a big checkpoint. And then at any time you could create a job level checkpoint, but this incremental updating would let you get away from this overall IO problem that I mentioned earlier.
Right. And also even disk-based file systems are, perennially trying to move away from POSIX towards things that are more scalable, like object storage. So this guaranteeing very low level atomicity seems expensive. And I was just, eyeballing the performance numbers, like, heck, we could write it 3 times and get better performance. So
right.
You thought about that. I was trying to understand what.
Sure. Yeah. I mean, we've thought about this a lot. It's just because, the non-volatile memory is one of those trends it's hard to ignore. It keeps getting cheaper and cheaper and denser and denser. And so, when you have that kind of memory capacity, it's really interesting to think about how you might use it. And so one of the things that we've created here is a parallel key value store. So you can start up an MPI job or a UPC job, and then you can access all of the data in that store using just a key. And that can come from any of the parallel tasks in the job. And the nice thing about that is it can be a small key or it can be a big key. It doesn't matter. It can be 2 GB value or a 15 byte value, but you still have it available in a way that allows you to, do millions of those concurrently. So you're not bound to some POSIX standard about metadata consistency, for example. And, I'm enthusiastic about that. I think, the other thing about non-volatile memory is we really need to change the way our systems are operated. And what I mean by that is, now once you are kicked off a node by Slurm or whatever your scheduler is, everything there gets wiped out, right? There's no sense of storing anything there. And ideally in a non-volatile memory world, each one of those nodes would have some non-volatile store on it that was accessible to everyone in a secure way, so that if they wanted to, stripe their data across, thousands of nodes, their climate data, for example, then they could do that. And then whenever they needed a certain value, they could just go to that node and grab it using a key.
That seems a lot like using the nodes as file servers, sort of what BGFS does.
Yeah.
I've seen this shift back and forth between we should put the disks on the nodes, all the disks go on the things, and most recently, I mean, you're not even, you're not even putting the flash drives on the same servers as the rotating media.
Right.
It's sort of, that's all been segregated. So it's hard. I assume that there's something that keeps pulling things back to dedicated nodes with the network in between.
Yeah, and that's where I think, at some point it's just going to be, somebody's going to have to cry foul, because if you look at some of the papers, I think it was somebody from NCSA there had done a study of several different HPC systems, like the real performance, Argonne and NCSA, I believe, of real file system performance. And it was abysmal. I mean, it was, the effective file system performance was like megabytes per second, not gigabytes per second across the nodes. And so I don't know what's going to have to happen to change that. But I think non-volatile memory is certainly a possibility to help solve that problem.
Anybody else? Well, one other thing that I thought of with the FPGA extensions to OpenAC for stream in and stream out,
Right.
The new Ampere architecture at the individual block level now has asynchronous copies into the shared memory.
Right.
And I think some people are going to be treating this as the new normal, where rather than reading and writing directly from global memory, you copy to shared memory while you're processing. You copy A to shared memory while you're working on B, and C you're writing back out to global memory, and you set up this mini pipeline.
Right.
And having that kind of the stream in, stream out extensions to OpenACC would enable automation of that programming model.
Yeah, and so we've that's a very good point. I mean, we've thought about mainly FPGAs up at this point, but if kind of what you're doing is putting together a data flow, right? And so anytime you have more information about how the data is going to flow between these kernels, you could make use of that, and it could be between multiple GPUs or multiple devices in a node, where you actually can pre-stage data and have perhaps use some special functionality to special memory to transfer the data between the devices. I think you're right. I mean, we have discussed with the OpenACC technical committee some about making this an extension or a new a part of the standard, but it's not there yet. And so the nice thing too about it is it deprecates really well. You can just easily drop back to the primitives like present and things like that if you want to, but if you don't, then you can make use of this optimized version. And it is a data flow. You could have it be as long as you want and use it through many kernels.
So I'm sure those of you looking at chat notice this, that if you're looking to see what the next session is or what the times are, the website was down. I guess we suddenly went very popular. I don't know what happened actually, but so there is another link to the program on the GitHub, which at least can give you the bare bones information.
Very good. And you were going to start again at what time?
In 1 minute.
Oh, okay. Well, I'm going to take my coffee break here for a moment and go grab something. And thank you again for having me. It's been fun.
Thanks. We'll take maybe 2-3 minutes and to give you that time.
Great. Thank you.
Thanks, Jeff. Good talk.
Yep. Thank you.
Hi, can you guys hear me? I'm just testing out my microphone.
Yeah. Is that Aditya?
Yes,
Yeah.
thanks.
All right. Hello, everyone. Welcome to our session on asynchronous applications. These are all applications that involve some form of asynchrony. Our first speaker today will be Aditya, who is joining us from the Lawrence Livermore Los Alamos National Laboratory. So I will go ahead and hand over speaking duties to him.
Hello, everyone. Can you guys hear me?
Yes.
Okay. Thank you for the introduction. I'm going to share my screen now. Hopefully, it'll be fine. Oh my God.
Is there some issue?
For some reason, I can't share my screen. Okay, can you see it now?
Yep.
All right. All right. So, good morning, everyone. I'm Aditya Pandare from Los Alamos National Lab. I'll be presenting our progress on a compressible hydrodynamics solver, which is written on CHARM++. So it's an asynchronous distributed memory parallel solver. I'm presenting on behalf of the lead author, Joseph Bokoshi. So to begin with, I'd like to share with you what our objectives were when we started working on this project. So we were looking to target highly parallelizable, large-scale computational fluid dynamics applications. So we would be looking at extremely large meshes with which were running on tens of thousands of cores routinely. So the use cases, just to give you a perspective, would be blast loading on blast loading effects on on vehicles, re-entry bodies, aircrafts, and such complex structures. The reason I mention this is because to mesh these kind of geometries, which are complex and 3D, we would need to have explicit meshing over all the detail of the 3D geometry. For example, when there's an aircraft, you would have to mesh the entire aircraft in very detail, like the tails, the fuselage, all the other attachments to the aircraft, the payloads, and all that. That's one of the very important things here, because as compared to internal flows, these external flows requires meshes which are a large magnitude larger than the internal flow meshes. So you would have 3 or 4 orders of magnitude differences in these meshes. So we would routinely see meshes such as tens of millions or even a billion cell large meshes. So that is why we would like to have an extensive parallel capability in the code. To give you an introduction about the code we are using, it's called Inciter. It's an app in Quinoa, which is built on native CHARM++. As an introduction, that's also a compressible hydrodynamics code, which can deal with single or multiple materials. It uses unstructured 3D meshes, so tetrahedral meshes in 3D. So there's a lot of indirect addressing because of the unstructured component. There are a couple of numerical methods in the code. Sorry.
Are you showing multiple slides? We are still on the title slide.
Oh, sorry.
Is it PowerPoint? No, it's somehow not showing the slideshow.
Oh, I'm sorry. Give me a second. How about now?
Yeah.
Okay, so I'll just use this mode. I think the full screen.
Yeah, this mode is fine, I think.
Yeah. Okay. So like I was saying, we have multiple numerical methods in here: continuous finite elements, discontinuous finite elements, and we also have finite volume methods there. And today I'm going to only talk about continuous Galerkin finite elements. The peculiar aspect about this code is that it has adaptive mesh refinement and adaptive polynomial degree refinement. And this is the fundamental reason why we chose native CHARM++ to write our code in, because because of these adaptive refinements, there is load imbalance. And we want to make sure that there is some sort of load balancing strategy to make the code efficient. And I'll show you an example in the later slides to show you the effect of this load balancing. This is an open source code, and it can be found on this website here, quinoacomputing.org. So moving on, I would like to talk a little bit about the numerical method that we are using here. The first set of equations here is the ideal gas dynamic equations, that is the Euler equations, and we are talking only about single material flows in this presentation. The numerical method that we are using is a edge-based finite element method, which is basically the same as in nodal finite element method, but the computations are done, or it's cast in an edge-based way, which then makes it very similar to a node-centered finite volume method, which is very well known in the aerodynamics community. So these equations, these Euler equations, are then discretized using this edge-based finite element form. And here I've just shown you the discrete form. What I'd like to point out here is there are a lot of operations over the edges. So inside the mesh, there is multiple nodes, obviously, and the edge that I'm referring to is the edge connecting one node to the other. So there's a lot of operations between these two nodes, which are called edge-based operations. And we would also have operations over elements surrounding this edge, and elements surrounding each of the nodes that constitute an edge. So there's a lot of indirect addressing is what I'm basically saying when I give you all these details. And this becomes important when we're looking at distributed memory parallel algorithms, because we need to make sure that along the process edge, we communicate all the required data structures in a consistent manner. So these are just a few references which point to the numerical method that we are using here. Most of these come from Los Alamos. So now to verify the numerical method that we have implemented, we try out a couple of test cases, and I've shown a few of them here. The first one is a vertical flow. It just makes sure that in the presence of a smooth flow field, so smooth pressure and smooth velocity flow field, we are indeed able to get second order convergence. Second order convergence is extremely important because when we are trying to, practically, when we are trying to simulate a particular flow, we want to make sure that when we refine the mesh, we get closer to the solution that we want to. That is called Lax equivalence theorem. So basically, we want to make sure that when we refine a mesh, we indeed are approaching the analytical or the exact solution. And this problem shown here actually has a mathematically analytical solution which we can compare with. And on the right hand side, on the top here, we have a graph which shows that the method is indeed second order accurate. This slope here is compared with a dotted line, which is the second order accurate line. So we definitely get second order convergence for all the fields that we're solving for. So momentum, energy, and density. So this is a validation for smooth flows. Moving on, we wanted to check something of more practical importance to us, which is a blast wave. So basically, imagine a spherical domain, and at the center of the sphere, we initiate a high energy region. And when the solution is started, the high energy region starts expanding. And we want to make sure that we capture that expanding blast wave in an accurate manner. What is critical here is the strength of the blast wave. So the peak in this density plot and the location of the shock wave, which is also very critical. And here it might be hard to see, but I'm showing density plots here with 4 different meshes. So this is a mesh conversion study in a way, where we try a coarse mesh, which is mesh 1, and we go through different degrees of mesh refinement up to mesh 4, which really approaches the analytical solution, which is the solid black line. And if you can see, the location of the blast wave is pretty accurate in all these simulations. On the right, I show the contour plots, which basically show density and pressure. On the bottom here, I show another mesh convergence. Here we don't get second order accuracy because it's a discontinuous problem as opposed to a continuous problem before. But the point is, we get first order convergence when we refine the meshes. So we can again be assured that we can get mesh convergence when we refine the meshes. So we are headed towards the exact solution. That's the important takeaway from this graph over here. So moving on, we have another kind of more complicated test problem where there are two things happening now. Here, this vertical line is basically a shock which is going to move over this cavity over here. So the domain is this T-shaped domain that you can see. State 1 is a post-shock state, and state 2 is the pre-shocked state. And this vertical line, that is the shock, is going to propagate towards the right side. And as it moves towards the right, it's going to encounter this cavity. Then that's where some complicated phenomena happen. When the shock moves over the cavity, there is a vertical flow. And then the shock, as it propagates into the cavity, there is some shock reflection and rarefaction waves generated. We want to make sure that the code captures all these phenomena accurately. Here we compare this, the solution obtained numerically on 4 meshes. So these are 4 different meshes. And we compare it with the experimental results. So these black lines are basically the shock locations from the experiment. And on the top right, we have included solutions from the experimental solutions from the paper. And we can see that the shock locations are pretty accurate. They're not exactly accurate because this paper does not mention the timings correctly. There is some sort of ambiguity as to when the shock actually starts. We can try to match the shocks here and there, but there is some kind of ambiguity as to when the shock actually starts with regards to the experimental time. But what I would like to mention here is that the shock becomes more pronounced. You can see over here it's pretty diffused, and over here for the finest mesh you can see that it is very well resolved. And similarly, there is a vortex over here, which the blue color gets deeper as you move to finer meshes, which I'd like to show. This is an indication of mesh convergence, basically. So we can capture these multiple phenomena that are happening in this T-shaped cavity domain. The next test case is a even more practically applicable test, which is the Onera M6 wing. This is a standard test for aerodynamics verification codes. I've shown the mesh here, I've shown only the surface mesh here actually. And on the bottom is the computations on one of the meshes that we have tried this out on. These are pressure contours that I've shown here. And on the next page, what we want to see is whether we can compare with the experiment. So the experimental data has been taken on different locations on this wing, different span-wise locations on this wing, and we are comparing the pressure coefficients. So we would like to compare with experiments and to make sure that we can compare well there. So these are the 6 different locations on the wing, and the drop here. So I'm going to zoom in on one of these. Let's zoom in on this one, for example. So we see 2 meshes here, a coarse and a fine mesh, and the experiment is shown in the red crosses. So you can see how pretty much everywhere the simulation is matching with the experiments well, but near the shock location is kind of off, and that could be due to a couple of reasons. We don't include viscosity in these computations, because of which the shock it's even smeared. As you can see, the shock is not a sharp vertical line, and that can happen because in viscous flows the shock is obviously smeared. And but regardless of that, we get good agreement with the experiments at all span-wise locations. This is another location at 90% of the span, and we basically want to see that we are getting good agreement with the experiments. So now that we have done some basic verification studies and that we are getting good validation from experiments too, we wanted to do some optimization of the code so that it's efficient. And this slide basically shows that most of the heavy computations were happening in the right-hand side part of the algorithm. The computation of the right-hand side takes like 91% of the time. And when you go further fine-grained, we can see that the there are the gradient computations, the domain computations, and the source term computations, which take up most of the part. So this is how we decided which part of the code to optimize to get a better performance. And this slide is basically a summary of what we did to get a good speed up. So basically we got a 6x speed up starting from the baseline code. When we went on optimizing the code, we got up to a six times speed up. And the most important things that I would like to mention is we replaced all the tree-based data structures like maps and all those with flat data structures which could be streamed and which had contiguous access. And basically we changed the loop accesses from maybe node-based loops to edge-based loops, or maybe element-based loops to edge-based loops, and such. And that actually got us a lot of computation efficiency gain. And that's what this slide basically talks about. After this optimization, we did a strong scaling study on Lanel's Grizzly supercomputer, and the light blue lines are the edge-based finite element algorithm that we will focus on. And there are two light blue lines. One of them is the non-SMP mode, which is the one on the one with the hollow markers, and then there is the SMP mode down here. After the optimization, we got really good scaling for both the SMP and the non-SMP modes. After a point at around 28,000 to 30,000 cores, we saw a plateauing, basically saying that, you know, we had reached this the sweet spot and we shouldn't go any further. We are throwing too many resources at the problem. So we definitely get very good scaling. And the other lines here, which are the yellow and the green lines, show the other numerical methods like discontinuous Galerkin and the other continuous Galerkin frameworks, which also show very good scalings on thousands of compute cores. Now, since we have good strong scaling, the next step was to see parallel performance when the load imbalance was triggered. And the way we computed the load imbalance, or the way we induced load imbalance in the problem, was for the Sedov blast wave. So basically, when there was a blast wave where the density exceeded a certain quantity, there was some extra physical computation that was triggered. And this computation caused load imbalance in the vicinity of these partitions, basically. So here you can see at different time steps how the blast wave progresses through the domain. It kind of expands, and because of that, the extra computation, the zones which have the extra computation, that also goes further ahead. And clearly the green line shows the extra computations without any load balance. So the grind time, which we should try to be as constant as possible for the grind time, that goes on increasing. When the load imbalance, when the load balancing is triggered, and there are a couple of load balancing we've tried here, we can see that this is actually pushed down and the load imbalance is eased, and we get better distribution of resources. And just to compare, the black line on the bottom here is without the extra computations, where it's very uniform load, and the other lines basically show how when the extra load is triggered, how the load balancing works to ease the computational load imbalance, basically. So this was actually a very promising result that we saw, and we have good hopes from the algorithm that we have implemented. So with that, I end my presentation. We are working on different fronts on Quinoa basically right now. There is a multi-material algorithm that is being implemented. It has a finite volume and discontinuous Galerkin numerical method for multi-material flows. We have p-adaptation that's going on, which also induces load balancing. There's a productization SBIR with the CharmWorks folks that's also going on. There's a 3D mesh-to-mesh transfer, which is actually what the next talk is about, where there's the target applications there are basically fluid structure interaction type of flows. So basically with that, I end my talk, and I'm open to questions. Thank you so much.
All right, Justin, back to you. Questions?
Were there any questions? I didn't have any immediately.
I have one, but I'm on my phone and I can't figure out how to put my hand up.
That's okay. You can ask.
So what load balancing strategies are you using in this case?
We are using GreedyCom and well, we are using a couple. Give me a second. Let me share my screen again.
Yeah.
Can you see it?
Yep, there it is. Perfect.
Okay.
Thanks.
So we have tried a couple of things. There is a 10x over decomposition, so 10 times more chars than the CPUs. We've tried that, but that doesn't give us as much better performance as 100 times. But then in the 100 times virtualization, or 100 times over decomposition, we use GreedyCom, distributed, and neighbor.
Okay. And can you remind me again how many cell elements you have per char? If I remember correctly, you have multiple per char, but maybe that has changed.
We definitely do have multiple per char. Give me 1 second. So I'll have to look, but it's probably per char at least like 10,000, something like that.
Oh, wow. Okay. Okay. So
hang on, but that's for per char, I would say a few thousands because there is a 100x over decomposition. So a few thousand. Yeah.
Okay.
It's the 100x is very unusual though. So probably we should talk about why you needed 100 and why 10 did not work. And also, is this with SMP or no SMP? Are you using separate for the rest of the people's benefit? Are these charts being run on each core? SMP or no SMP?
I'm not sure about this particular run, but we have tried both, but I'm not sure about this particular run. I'll have to check about that.
Okay.
But to just to comment that 10x doesn't work, it's not like it doesn't work, but the 10x line is over here. It does the job, but it doesn't do the job as well as a 100x over decomposition, if that makes sense.
All right.
Yeah, I wonder. And it's unstructured meshes, right?
Yes.
So some of it could be cache performance, but then that would have shown up even on the left without, yeah.
Right. It would have shown up even with the no extra load over here for the black line, and even before the 100 time steps in this zone. Yes.
And when you say extra load, how heavy does an object become? Have you looked at it? Does it become much heavier?
I think the load was made pretty heavy so that this difference is very pronounced, you know.
I see.
But again, I would have to talk to Joseph about that.
Okay.
He's the one who did this run. But we can talk about this more when.
Okay. No, but I think if the load variation is like that, then one can probably write some math about how much virtualization you would need for different types of this. And in fact, probably in this situation, it may be better to split, dynamically create new chars rather than let's start with a very large number. But interesting options. Okay.
Right. That's a good point. We should actually see what the simulation was run with. And yeah, some back of the envelope calculations should definitely be done. I wonder if Joseph has done this. I'll ask him for sure.
I have another related question. If you have a uniform load distribution, or roughly uniform, so you don't add this extra load, do you know how close the load balancers are able to get you to basically a space filling curve so that communication overhead is really minimal compared to computation? Have you done studies like that?
We have. So basically you are saying no extra load, but turn on the load balancer regardless and see the overhead, right?
Well, no, not the overhead of the load balancer necessarily, but Francois Hébert will talk a lot about this later. But basically, if you to see if the load balancers are able to bring down to put chars that frequently communicate with one another on the same node, whether you've been able to get it to do that in practice.
So now you're talking about SMP mode, though.
No. A regular, even without SMP. There are many chars on each core even. The question is, are they nearby ones?
Okay, I haven't seen that.
Greedy will tend to ignore that communication and they'll scatter them around.
Right.
Yeah, because I don't want to say anything of what Francois Hébert is going to talk about, but this is where we started, and that's why I'm interested if you've had any experiences with it, because we want to make sure that sort of our baseline performance is as high as absolutely possible, and so I'm curious if you've kind of measured baseline.
That's a good question. I have seen some results with I've seen some of this with the DG methods. This is a continuous finite element, but I have seen some results with the DG method, which probably can be extrapolated to this one. It does try to bring different chars onto the same node or closer, basically, but I will have to verify that. It's been a while since I looked at that, but we should talk more. I'll definitely verify that for you.
And we should wait for the cosmology talk from your group, Nils. But I should say that when communication is important, greedy is not a good strategy to use. And there are the other strategies kind of fallen behind a bit, but we need to bring back the prefix-based the space filling curve based ones, or graph partitioning Parmetis based ones, and so on, that actually don't use Parmetis for the mesh, but for the objects. So it's much faster. So there is a variety of strategies possible. And our attempt, I think, in the CHARM community is to try to make that as automatic as possible and increase the suite of strategies. And then remember, I think this is kind of a longer comment than needed, but Harshita's thesis a few years ago used a machine learning model to collect application characteristics and then decide which strategy to use. And that was in operation until recently, but I think with the new load balancing framework, we need to bring all the strategies forward into that and then redo the machine learning calibrations again for it. But the attempt long-term will be, you shouldn't have to think what's the right strategy to use. But in the meanwhile, we need all the nice new strategies.
As a follow-up to your question or your comment, you said parameters. Would that be replaceable with any other domain decomposition software or library?
Yeah.
Okay.
Scotch will be fine, or your Trilinos has
Zoltan
things. Yep.
Yeah,
but
okay.
Remember, it's the object communication graph we are talking about, not the mesh. So
right.
It's much. It's just tens of thousands rather than millions or billions.
Right.
Okay. I think we went a bit over time. Back to Justin.
Yes, we were still within half an hour from the starting time.
Okay.
Regardless, we'll be moving on to the next talk. As Aditya mentioned, it will be by Eric Nikita on asynchronous distributed memory task parallel 3D unstructured mesh-to-mesh data transfers.
Okay, let me just figure this out quick. Okay, can everyone see the slideshow?
Yeah.
Yes.
Okay, so thanks, Justin. Like Aditya and Justin both said, I'll be presenting on the asynchronous distributed memory task parallel 3D unstructured mesh data transfer we're working on in Quinoa. So this has been work with Joseph at Los Alamos National Laboratory, and then from CharmWorks, Eric Boehm is the PI on the project, and then myself and Nitin Bhatt. So we just heard about Quinoa. I don't really need to go over too much of it again. Just a short slide, just reminding you, it's a project from Los Alamos. It's a CFD application developed for Charm++, open source, and this work is part of the phase 1 SBIR, which started in February 2020 to further develop Quinoa in conjunction with Charmworks. And so the long-term goal, which by this point is probably more of a short-term goal that I'll be touching on in this presentation, is combining the CFD with structural mechanics by using parallel collision detection to do mesh-to-mesh data transfer. And this work is still in the fairly early on stages. Unfortunately, we're just now getting to the point where we're beginning to look at performance. So this presentation will be plot free, but we'll give you an idea of sort of where we started and where this project is going. So like I mentioned, we're working on using collision detection to do scalable parallel mesh-to-mesh transfer. We're developing a library that right now we're calling ExaM2M, which is a library for performing mesh-to-mesh transfers on unstructured meshes. The sequential algorithm was originally developed by Joseph, and now we're working on the parallel implementation as a collaborative effort between Joseph and Charmworks. And the crux of the library, the kind of the centerpiece of the library, is utilizing the existing collision detection library that was developed for Charm++, I think in around 2006. And so I'll be talking a lot about that collision detection library today. But the basic algorithm for the mesh-to-mesh transfer is fairly straightforward, broken up here into 5 steps. Basically, for the first step, you're just setting up the mesh data. Right now, it's just a standalone Charm application. We haven't converted it to a library yet, so we're just reading meshes from file and partitioning with Zoltan. But part of developing the library API will be allowing the application to actually transfer the mesh data in. Either way, the mesh data is stored in a worker char array. So again, it's going to be virtualized across processes. There's going to be many worker chars per process, all holding their own chunk of the mesh. And they're going to be sort of the workhorse for the library. The second step, which is the big step, is we pass this mesh data into the Charm++ collision detection library. And so here the source of the transfer is going to submit a list of bounding boxes for each tetrahedron in its mesh, and the destination of the transfer is going to submit bounding boxes for its vertices. In this case, at least right now, 1 vertice per bounding box. Chunking that up differently is something we can look at in the future, but right now it's 1 vertice per bounding box and 1 tetrahedron per bounding box. And just to clarify what I mean here in case I forgot, the source mesh in this case is the mesh where we have the solution at all the vertices, and we want to figure out how to kind of overlay the destination mesh on it, how it intersects with the source mesh, and then interpolate the solution data from the source mesh to the points of the destination mesh. So this collision detection library is going to do collision detection and return us a list of potential collisions. I'll explain on the next couple slides why these collisions are just potential collisions. But once we have this list of collisions, they'll be distributed back to the destination mesh for further processing. The destination mesh splits up these collisions based on the source mesh chars that contain the relevant tetrahedrons and sends it to the source mesh. Then the source mesh does the actual collision detection with the tetrahedrons and interpolates the solutions to the different destination points. So like I said, the step 2 is sort of the crux of the algorithm, and that's where the majority of the work is going to be done. And so that's what I'm going to look at in a bit more detail here. So for the collision detection in ExaM2M, it's using a 2-phase collision detection. Phase 1 is what we call the broad phase, and then phase 2 is what we call the narrow phase. So in the broad phase, we're just doing basically the quickest, dirtiest collision detection we can think of, which is just colliding bounding boxes. Determining whether 2 bounding boxes collide is very quick and cheap to compute. It's also a very general case. So this is what's handled by the Charm++ collision detection library. We pass it a list of bounding boxes, and it determines where potential collisions may lie. So in the small picture below, we see that the trapezoid potentially collides with a triangle. A circle potentially collides with a triangle. Obviously, we can see that it doesn't, but their bounding boxes intersect. So the library determines that's a potential collision. But then the star we can rule out because its bounding box does not intersect any of the other bounding boxes. So in the narrow phase, that's where we take this list of potential collisions and do the sort of application-specific collision detection logic in response to the collisions that we detect, et cetera. So this generally is going to involve probably more expensive collision detection, but because we do this two-phase approach, we have far, far fewer collisions to check because the bulk of the work and the bulk of the paring down this list of objects to collide has been done in the broad phase. So that's where in this small example, the application would detect that, yes, the circle does not in fact collide with the other two shapes. So the broad phase, again, handled by the collision detection library. Like I said, I think it was written in 2006-ish. And it's detecting collisions or intersections between objects scattered across processes. So it's completely distributed. It has applications in computer graphics and animation, computational physics, robotics, etc. And like I mentioned, in our case, what we're colliding is the tetrahedrons of our source mesh with the vertices of the destination mesh to find out essentially which solution points need to be interpolated to the vertices of the destination mesh. So the collision detection library kind of works in 3 large steps. It's based on the idea of voxels. So a voxel is just a 3D cell in a regular axis-aligned sparse grid, or really in any dimensional cell. In the library's case, it's 3 dimensions. In the example on the right, we see a 2-dimensional example, but it's generalizable to any dimensionality. And one of the important parts here is that it's a sparse grid of voxels. So step 1 is we're populating the voxels by telling it what the objects are that we're actually trying to collide. So in the case on the right, we see there's a hole in the middle because there are no objects that intersect with that voxel, so we don't need to concern ourselves with that voxel. And so this is implemented using a char array. Each element in the char array is a voxel. The char array initially starts off empty, and step 1 is the application passes in lists of bounding boxes, and using demand creation in Charm++, these voxels then come into existence. And so for those unfamiliar with demand creation, that's a special feature you can use for char arrays, where instead of actually doing bulk insertion when you create the array or doing regular dynamic insertion after you've created the array proxy, you can actually just start with, for example, an empty array. And as you call entry methods on array elements, the distributed location manager will determine, does this element that you're trying to send this message to already exist? If it does, reroute the message as normal. If it doesn't, first create the object and then deliver the message. So in this case, as we're adding objects, they'll be created as the first objects get added. And then once more objects are getting added to voxels from, for example, other processors, they'll be routed to the correct voxel. The other thing to notice is that, for example, with the larger circle in the bottom middle, that intersects, in this case, 4 voxels. So each voxel needs to know about any objects it intersects. So those 4 voxels will all know about that circle to do potential collision detection. So step 2, once we have our voxels populated, we just run a serial collision detection algorithm per voxel just to collide the pairs of bounding boxes that the voxel knows about. This is pretty straightforward. So in the example on the right, we see there's a bunch of voxels that only have 1 object. Those don't matter. But then I've narrowed it down to just these 3 voxels, which have potential collisions. They're going to run collision detection on their list of objects. And in doing so, we'll determine that there's a potential collision between the triangles in the top left, the triangles in the middle right, but the circles don't collide. And then these voxels all just do a big reduction to concatenate this global list of possible collisions and return it to the caller for further processing. So that's the broad phase of the collision detection. What do we do in ExaMTem to further process these collisions? So like I said, this is where, again, we're dealing with tetrahedrons and vertices, or in the example on the right, triangles and vertices, but it's the same general principle. Here we need to find out which of these vertices actually collide with which actual tetrahedrons, and then we can interpolate the solutions. So we distribute the collisions back to the destination mesh because that's who has the information about the vertices. So each destination mesh will then distribute its own vertices to the source mesh chars that they are potentially colliding with. One thing to note is that there may be multiple potential collisions per source char. So for example, the vertices I've circled on the right, when you're doing just bounding box collision detection, those actually will potentially collide with multiple tetrahedrons, or in this case, the triangles. So what we get back from the collision detection library are multiple collisions dealing with these vertices. So we'll be sending multiple potential collisions to the source chars. But then once the source chars get this information, then we can actually determine what the actual collisions are. And then once we determine the actual collisions, we can interpolate the solution to the vertices based on the vertices of the source tetrahedrons that we're actually colliding with. And at that point, we have our solutions for all of the destination points, and we've accomplished our goal. So like I mentioned at the beginning, we're just now getting to the point where we're going to start looking at performance. So I don't have any cool or interesting plots, but we have gotten initial results on correctness. So we're pretty confident that things are working as expected. We started with some sequential verification and some multi-core verification, scaled up to multiple nodes, increased the amount of virtualization. And so this was a run that Joseph did on just doing a simple transfer between a sphere and a cube. We had two 48 million cell meshes run on 216 cores, 5 compute nodes. I'm not actually sure what machine Joseph ran on, but that was the basic setup. And the right is just showing what's actually 2 lines showing the actual solution and the expected solution, and they overlap exactly. So like I said, now we're at the point where we're going to start looking at how this performs, how it scales, and integrating it into Quinoa. So potential future directions, first and foremost, tune and analyze our scaling experiments. We currently have a lot of potential knobs to tune, the degree of virtualization, the voxel size we give to the collision detection library, different partitioning schemes, etc. The next thing is obviously then to also develop a library interface. So the worker char arrays within the library are going to be bound to char arrays in the calling application so that the data transfer does not require messaging. We can just hand over pointers to the mesh data, have the collision detection library, or sorry, the XM library run and automatically interpolate the solution without having to send any more messages between the library and the application. And then we want to integrate it into Quinoa, and that's kind of the big milestone we want to reach within the next month or so, integrating into Quinoa so that in each iteration of Quinoa, we can call this XM library and do some mesh-to-mesh transfers. We're also looking at some improvements to the collision detection library. Like I said, it's pretty old, so one thing we want to do is modernize the API a little bit, and in doing so, we want to make the post-processing of collisions more easily distributed. Like I said, right now, at the end of the collision detection library, all of the collisions are gathered up in one giant reduction and concatenated into one big list on processor 0. First of all, that's not even customizable where the giant list goes. And second of all, it's a giant list of potentially millions of collisions. So we suspect that might be a bottleneck in processing. We want to improve the API so that the actual collisions can be automatically returned to the whatever parties are concerned with those particular collisions. In this case, they should be returned right back to the destination mesh. And in doing so, we want to make sure that we can map things accordingly so we can reduce the cost of communication there, etc. We also, in the current scheme, our mesh is partitioned, and of course, we're going to have vertices shared on boundaries between chars in the destination mesh. Right now, every char submits all of its vertices, which means we have some duplicate collision detection going on in the library. We want to weed that out and make sure we have a scheme to correctly balance that. Again, tuning our voxel configuration, and then probably also in general some more efficient collectives for post-processing that shows up as a particular performance problem when we're doing all this large, basically all-to-all between the destination and source meshes at the end of the computation. But yeah, that's my presentation on sort of the start of this project. So if anyone has any questions, let me know.
Well, I guess I will ask a question to get started. Not a question so much as a musing, because I hope I noticed some of the former students are here. I don't think Orion is joined here. If he were, he could answer this question. Orion Lawler is the original author of this library. The claim to fame of this library is that it is highly distributed, highly scalable, asynchronous, mainly asynchronous. And so I'm a bit surprised at the fact that the list is being returned to one place. I suspect that this is because the original thing was for collisions between two meshes, which happen in a very few points. Not in mesh-to-mesh transfer, it happens everywhere. Whereas if we just have some kind of a finite element structural dynamics code where in a crash-like situation, the mesh normally doesn't bump into itself, and where it, on a few points it bumps, you're creating this list to send back. So that may be the reason why it didn't show up this problem. But the library is meant to be highly scalable, and we would like to restore that to that by returning the results to the clients. It says, I was looking at the paper while you were talking about it. So it should be returned to the clients rather than collected centrally. I don't know if that's more a comment than a question, but do you have any thoughts on that?
Well, yeah, so yeah, like I said, the whole thing is meant to be distributed, and it is weird because the majority of it is very distributed and asynchronous. It's just that very last step. And the one thing that is also sort of promising is that because of the demand creation and how that's set up, as you're contributing objects and these voxels are being created, there's also a decent chance, based on just the locality, that when a client adds its bounding boxes in library, the voxel or the voxels that's responsible for those objects, you know, if your mesh is also partitioned with some locality in mind, those are probably going to be co-located with the clients as well. Especially if we have, for example, the destination mesh contribute its bounding boxes before the source mesh does. So not only will we avoid that bottleneck of gathering this big list in one centralized location, there probably won't be that much communication in returning the data to the clients as it is anyways, because in a lot of cases, the data will already be co-located on the same PE.
That would require a round of load balancing, I assume.
So again, it depends. Actually, mostly I think it depends on how the data is originally mapped to the chars. Because of the demand creation, if I have some particular set of vertices and I'm the first person to contribute those, or when I contribute those, if I'm the first person that's contributing something for that particular voxel, the demand creation will have that voxel created on the same PE as me, as I am. So in a lot of cases, the owner of these vertices bounding boxes will be co-located with the, or in at least as many cases as possible, will be located with the chars that contributed the vertices to begin with. So once we have that list of collisions with those vertices, returning it to that client won't involve messaging in a lot of cases.
Nice.
And I do think then that will also, again, add emphasis to make sure that we have a good partitioning of the mesh in the first place.
Are there any further questions for Eric then? All right. If not, thank you for your talk. And I think we'll be moving on to the talk given by Lawrence Rauschweiser. He's an Illinois professor, and his talk is entitled Bounded Asynchrony and Nested Parallelism for Scalable Graph Processing.
Okay.
Lawrence, we can.
Yeah, I'm trying to share my
PowerPoint.
yeah. What is a share file?
If you share screen, it should give you an option to pick one of the.
Okay, here it is.
Yep.
Here you go. All right, so here we go. Okay, so I suppose you all see that.
Yep.
I hope so. All right, so this is actually this graph library or whatever that we want to present briefly was actually developed by some students of mine at Texas A&M. And it's in particular, the talk is by Adam Fidel. I tried to convince him to give the talk, but he kind of was, because he's working now. I mean, he is actually gainfully employed, probably making twice as much as I do. He kind of bailed out on me, so I have to give the talk. So I'm not going to do as good of a job as he could, but you're going to just have to bear with me. So about graph processing, you all know, and I'm not going to repeat in this audience, that graph analytics is commonplace, and that today's graphs of interest are very large, actually.
Lawrence?
Yes.
We are not seeing the slideshow. We're seeing the presenter.
Oh, yeah. Okay, all right. Sorry. Let me see the slideshow.
Oh, at the bottom, maybe.
Okay, that's better, I think.
No,
no, it's not.
Now it is actually the presenter view, sorry. Maybe it was better how it was.
Okay, custom view.
Did you try play from current side?
Okay.
Yeah, perfect.
So, do you see that?
Yep.
Okay, because I don't.
Okay.
Okay. Oh no, it's not it. Because when you do escape, it's escape to PowerPoint.
Oh, I see.
It does not do the escape to the Zoom.
So then you can go back to your previous view. That's fine. This is
okay. Can you see that?
Yeah, we can see your slide right now.
Okay, fine. So that's okay.
Well, what happens when you go to the next, we'll see. Okay.
Well, we'll see. Yeah. This is what happens.
Looking fine. Yep.
Yeah. So the problem was some of the problems with current graphs is that they traversally exhibit irregular access patterns, right? You have very poor locality. There are ways, of course, to fix it to a certain extent. Structural dependencies limit the parallelism. So graphs by definition are not parallel almost. The computation is, because it's very irregular, the computation is imbalanced. Partitioning is challenging. And the portability of paragraph processing software, if you want, to different platform is, let's just say, challenging. So in this talk, I'm going to tell you something about some of the work that we developed some time ago about bounded asynchrony. That means in the idea that asynchronous algorithms or asynchronous graph algorithms are somehow perform better. So here, level synchronous, you all know that one, the BSP model, right, is just a little animation that my students always like to do. it's, let's say you take a BFS and you traverse it synchronously, and then you another step, right? And then finally you get it. And if you want, so there are a couple of steps that you have to go through, and it means that there are global synchronization, so you have to pay for that. If you do completely synchronous, right? Then you traverse it in one shot, basically. There is no global synchronizations involved. And that's actually quite useful because supposedly you're going to finish faster, provided that you can do exactly the same work. That, of course, is not really true. And you're going to have some delays because of that, because you're going to do extra work to get a faster execution. So work suboptimal, right? If you would look at it in more theoretical terms. So here we have a little plot, and this is the synchronization cost, right? So if you go level synchronous, right, the synchronization cost is fairly high, right? And as you go completely asynchronous to the other extreme, synchronization cost is very low. However, the redundant work that you will do, because think about the BFS, if you are asynchronous, you're going to have to redo a lot of work because things arrive whenever they feel like arriving at the various nodes. The redundant work is actually going to be more and more pronounced the more the asynchrony is going to basically diameter of the graph. So what we did, since we saw this kind of plot, if you want, we decided that perhaps there is some kind of a sweet spot in between, right? So that would be the sweet spot, that where we can actually do the most asynchrony with the least amount of redundant work, and perhaps that runs faster. And in fact, it does, at least for certain kind of graphs. So here is what we have also provided in this stable graph library is a very simple way of writing the code. So you have a vertex operator and you have a neighbor operator. So if here is a very simple example, right, of what you do to every node, right? And here you go to the neighbor operator, you operate on the neighbors, right? With a neighbor operator, you have to write it as a programmer too, right? Process a neighbor and process the thing. Now, something is missing, but so what you want is to minimize the predicted execution time. So the penalty for the notate, psi gk graph and k, the increasing asynchrony. Execution time approximated by, I'm sorry, something is wrong with the animation. Okay, so we're just gonna have to live with that. Okay, the picture can't be displayed. I don't know why. I had it before.
This has been happening to me lately. What seems to be the problem is that if you store it on some kind of a remote drive and edit it, it loses these pictures. So the only hope is if you have a previous version of it.
Well, I'm trying.
Like, I don't know if it is Box or Google Drive, but my suspicion is Google
It's
Drive.
Box.
It's
Box, because if I went anywhere,
yeah.
Okay, hang on a second. Let's save as, and well, I was in PowerPoint actually, so let me go and save it.
It's very I mean, I lost all those things and I had to redo them.
Yeah, well, that's exactly what happens to me now. So let me go to my. kill this guy. Okay. Now. Okay. So now let's see if I share now. The question is, okay, I'm share screen. And okay. So let's see if this one works. Yeah, this one works. It was not saved on Box or whatever it was. On Box, actually. So are we back in business?
Yep, we are.
Oh, okay. All right.
We're not seeing the whole screen, but that's okay.
Let's see. PowerPoint.
I can see everything. It's not full screen, but I can see the slides fine.
Yeah, I can see it. Yeah. Play from the, yeah, that's the part. Yeah, that's good.
Okay, is that now nicer? Okay, good. So this was the penalty. So we tried to model this so that we can actually optimize for the K, right? So if we go to various levels, right, there are K level asynchronous, right? And the question was, how many steps can we go asynchronously before we have a global synchronization? So here is our, okay. So how many steps? Well, the time to execute, right, is the work plus the redundant work plus the time to do the global synchronization, okay? So we try to minimize this execution time, right? Computing this one is fairly expensive, right? The redundant code, the redundant work. So well, of course, we can try to model it theoretically some more, and it's all written up in the paper. However, there is a more of an adaptive system that we have figured out, which is actually more practical. So that means if the degree that we are, right, is larger than some constant, then K is equal to 1. So if you have a power graph, right, that starts with a lot of edges going out, a very high degree, then it is no point in having, asynchronous computation. Else, if the degree is not that big, then we compare the previous step, the time for the previous step with the current step here, these two. And if it's larger than a certain threshold, then we half the K, else we double it. So basically it's adaptive. If we're doing a good job, in the beginning, then we try to increase the asynchrony. If the job is not very good, it means we're it's going slower, then we try actually to reduce it. Of course, this is very empirical, and I'm sure that there are better models for it, but for us it worked fine. So this is what you can see actually. So this is in red. It is our method, right, up to 96,000 processors. And then if you do the BSP, well, the level synchronous, right, the BSP style, then you kind of get it here, right? So it changes once the number of processor is higher and you're more dominated by communication, then the execution time starts increasing. So it's certainly not scalable. And if you have completely asynchronous, which you kind of would like, but doesn't really work, then of course, higher levels of higher processor numbers, the execution time becomes very high. So the KLS strategy, scales better, and it's a little bit faster. we try to be adaptive to that. What we do that is also BFA. This is one Cray, used to be our Cray. I mean, it still is, but nobody uses it. Various graph inputs, right? And if it shows that our adaptivity or our adaptive scheme, how far it is from the optimal K, right? Because you can run them exhaustively and find out what is the optimal K for us, okay? And this is how with the adaptive system that we told you before, it's actually pretty close to ideal, except this one, and I can't tell you why. We use KLA also in other frameworks. That was courtesy actually of a reviewer who says, can you use it in some other places? Of course, we can use it outside Staple and outside SGL. So we actually did a modified level synchronous work list for Galois, for the system that comes out of UT, to allow for this KLA schemes, right? So these are the improvements depending on the graph type, right? So these are the various types of graphs, and these are the improvement. This is a speed up of KLA over what they are doing without KLA. So sometimes there is no speed up at all, sorry. Sometimes there is no speed up at all, and sometimes there is quite a bit of it, right? So it's basic, there is never a slowdown, so it's actually, there is no reason not to do it. BFS breadth first search from scratch, right? Use distances to compute reachability given, okay, so how much of Twitter is reachable in 3 hops? That was actually and we had some, I see, that was hidden actually in the previous one. So guys, you have to live with a presentation that was not massaged for this workshop, because I saved it the wrong place. This is how it actually looks like, the code, and I'm not going to go through the code here, but this is pretty simple how to write it. And then here is a vertex operator, and here you these are standard step, STL algorithms for each, right? But they are in Staple, they are in parallel, right? And here we initialize the distance. Right? It's not particularly exciting to show in a. There was a demo basically at supercomputing. So you traverse K hops before there is a global barrier. Then this is the result up to quite a few. The way that you change this, right, is that you have this graph paradigm, right, and you have to give the G, right, and it doesn't change very much the way that you express it, right? If you change it to this KLA paradigm, then you just have to specify K. That's all. There is no other modification to your code. Well, to your code, to our code at least, okay? So it's a very easy, what I was trying to show you is that it is a very easy to obtain. Okay, that wasn't working either. It was very easy to obtain basically for free, faster performance asynchronously, and it is very easy to write one, so you don't have to modify your entire software. Another thing that I kind of wanted to show you is that something that we are going to work some more on is the approximation. So shortest path between, the problem is, it's just an example basically, the shortest path between pair of vertices in a graph, right? And there are many applications rely on that. So what we do is that we use approximation to reduce the work that we're gonna do, and in essence also the execution time. So as an example, approximate distances between vertices, right? You have all the unweighted graphs, parallel breadth first search, and so forth. We use the asynchronous BFS right? And we increase the asynchrony by reducing redundant work, right? It is what I showed you before, right? Now, here is a traversal in asynchrony, right? Here there is a problem because you come on different paths and they don't match, right? So what is the approximation? So if we decide, as we have a joining node, that the distance, you know, the old distance from the new distance, right? The ratio over the distance, so the error, if you want, is larger than a certain amount, we will propagate it. Else, we are going to be having some tolerance, basically. We define a tolerance, and we are not going to redo the work. So you can, you know, you can, the work might be done, perhaps, to find this out, but you're not going to have to redo the work from then on. Right? So you come on two paths. That's perhaps a little bit, you have to traverse actually the entire graph. And then when you get to a node where these two are compared, the distances are compared, if they are not, you know, too far apart, you're just going to continue with what you had before. And of course, this propagates, right? So if it's larger than 4, so if you put the tolerance to 0.4, right, then you're going to have to propagate 3. You pick up 3, right? And then this one, if it's 0.6, then there is a problem, right? So you have to redo it. So if you use this approximative or approximate neighbor operator and the neighbor operator, right, this is a difference really. So you see that we didn't change very much from the code, from the one that is, you know, the original code, non-approximate, to the one that is approximate. It's just one line of code. It's pretty easy. It's very clean. And the error now, of course, when you do approximation, the whole trick is that you find also error bounds. So you have to bound your error, because just by running it 1,000,000 times and saying that it was not too bad, it works, but well, to a certain degree, but it's really empirical, and we would like to actually bound it a little bit better than that. So this is an attempt to do just that, right? So this is exact distance. This is distance with some approximations, right? So at the end of the algorithm, or you have a distance of this one right here, k times dv, right? Because it's a number of times that you do approximations. And there is, of course, a proof that is more formal, and is in the paper. Again, the old Texas road network, if you hate it, I mean, we should probably substitute it with Illinois road network, but it's probably, Illinois is a smaller state. So it's a bigger graph, the Texas road network. So the exact algorithm, right, is worse with higher asynchrony. So if we try to actually get it, you know, this is the level synchronous, this is an improvement, and then it goes up, depending for which one. Now, if the tolerance is 0.5, right, it's faster with higher asynchrony, right? But it gives you an error. So the question is, you know, you have to make a trade-off between this. Okay, so you can see here that as the error increases or decreases, right? So here is 0.5, and you go down here. This is execution time, number of hops, right? I mean, sorry, K, the number of hops between synchronizations. So what you ideally want, right, is a very large K. And for any tolerance, also the maximum tolerance that you can actually obtain. And here for K is equal to 5, you get actually quite a fairly high K. I mean, the performance is actually pretty good. But there is some error. So the question is, what do you do with the error? Well, each user will tolerate different errors. All what we can do is model it and offer basically knobs. And you have to actually enter how much you want. And you're going to run that way. You cannot, and hopefully run faster or better or whatever, right? But you cannot possibly decide for the user what error is acceptable because you don't know how it's going to use it. So each algorithm that we are going to have, a graph algorithm, let's say, with a certain error, any tolerance to error, so any approximative algorithm will have to have some input from the user to decide how big it is. Now, how do they compose? That's a different story. This is approximative BFS runtime on the road network on the BlueGene at the time, BGQ, with so many processors, 32,000 processors, and K is equal to 32, that means 32 hops. So you can see here that the tau is, you know, it's 0, right? So there is no, this is exact basically. And this is, as you go down here, then the approximate at some point, 0.1 or whatever, you kind of reach as much as you're gonna, the execution, you reduce the execution time for as much as you can. And beyond that, it doesn't make much of a difference. And here is the relative error, right? It grows from 0, right? From nothing. And it goes up to a point, and then it kind of stays flat for a certain time. So obviously you want to get the maximum advantage out of it without going to higher errors. There's no advantage to do that. Now, this is something that my student added in that I could not, I'm gonna have to go through it because I cannot show what I prepared for this talk. So there is current work, right? We have distributed graph processing, right? And we use Frontier. So this is, well, this work has been actually finished. So when we traverse a graph there and traverse it, say in the BFS manner or something like similar to that, there is an active frontier. How many nodes or vertices are active at one time? So he added this frontier concept that is actually not that new to collect a set of active vertices in a traversal. And what is collecting the frontier into, there are various types of data structures, if you want, that may or may not be the best. And it's kind of a experimental what it's trying to do. High level type information from user to select efficient implementation, right? So how the frontier grows, right? It would be useful to know from the user or some other ways, some information about the graph that you are playing with. And this is another thing that we are trying to figure out to make some kind of a taxonomy or some kind of a statistics about the various graphs and how they would influence the performance of the various algorithms. And here is a result with frontier. So the blue one is toward the frontier in a vector, right? And then without it, right? So depending on K also, the execution time, putting the frontier in a vector only of the active vertices. There is also another system, I have to say, that developed by somebody else that right now the name escapes me, where the frontier is very useful because you can also go backwards in the BFS from the end to the back. Rigorous study of feature for optimal values of asynchrony. We hope that we can do it. It's not very clear that it is possible, right? Non-vertex centric model or edge centric, and the partitioning also of the graph is quite important. In conclusion, I think that I convinced you that obviously synchrony is good for you. Bounded asynchrony is probably more realizable, more realistic, right? And you can trade it off, the asynchrony, with error, So you can actually play between the two, right? Because when you're using synchrony, you still have synchronization points. And at that point, you're going to have to somehow get rid of your error, because beyond that, you are not accumulating error. In between, you do. So the larger the K, the more error accumulation you do. The synchronization point is the time, where you can clean things up. And that's it. Sorry about the mess up with the slides.
No worries. Were there any questions?
So do you say that you have later results in the other presentation?
No,
So,
well, this is the presentation that the student wanted to show, that he didn't want to do any effort, to put any effort into it.
oh, I see. Okay. I was going to say
He
that.
has more because he still has not defended yet. So he has more results.
Okay.
And particularly, he has the hierarchical, I kind of skipped it because it's not completely ready.
Yeah.
It means it's not, this is all on GitLab. And that part is not on GitLab yet. So when it's going to be on GitLab, then it's going to be ready. Then he can also talk about it.
Okay. No, I just thought there's some result that existed. Then you could put a link to it here is what I was suggesting. That's good. Okay.
There is everything that I told you is actually available on GitLab, can be downloaded. There are lots of actually algorithms. Here you are, some of them, right, that are available. Okay.
Right. Okay. Any other questions?
Nice to know. No.
Looks like I don't see any other questions on the Google Doc either. So
okay, on the Google Doc.
There is a Google Doc.
I see. Chat. Oh, I see. Somebody told me there are 5 minutes remaining, but I think that I've done it in time.
Okay. All right. Thank you.
All right.
So I think that brings the session to a close. We're going to take a lunch break, which of course means whatever you want to make out of it. I was thinking if the rooms work, we're going to have lunch tables. Well, by that, I mean virtual lunch tables, which would be rooms. But I don't know. I don't think we can actually close and open the Zoom session. Can we, Jamin?
I think we should keep it open. We do have the breakout rooms available right now. If people want to join.
How do I not see them? Did you figure out those?
Yeah, there should be a button at the bottom called breakout rooms. Do you see them?
No,
right next to.
Do other people see it? Do we need to upgrade?
Yeah.
Oh, I see. So
but there is nobody there.
Well, that's probably okay because they were all attending your talk. Now they will go into the lunchroom. If that's my virtual, that was my idea.
I'm going to my class. Sorry, guys.
Yep. All right. That's okay. Thank you. Okay, I guess I will hang up and update my Zoom and join back again. Is that the solution?
Yeah, let's try that and see if that works.
Yeah. And if not, that's okay. That was just an idea I wanted to try. We start again at 1 o'clock. Do we need to change that? Or that's good enough? Let's start.
It should be good enough, yeah.
For a virtual lunch, yeah, that's good enough.
We'll wait a couple minutes before starting. James, do you have are you ready to go?
Yep.
In the meanwhile, any word on the website? Ronak?
Yeah, I've been in contact with engineering IT, and they've created a ticket, but so far there's been no activity.
Oh, okay. I guess I was just thinking, those of you attending, if you know other people who want to attend, they might be handicapped by not having the link to the website where the Zoom link is. So please forward that to anyone you know is interested, the Zoom link.
Okay, should we get going? Our next session is 3 talks all on astrophysical simulations on top of Charm++. And the first speaker is James Bordner from the University of California, San Diego. He's working on the ENSO-E Cello Computational Astrophysics and Cosmology code. And he and Mike Norman have been working on that for a few years. Go ahead, James.
Okay, thank you. Let me get this set up. Okay, is this coming through?
Yep.
Okay. So I'm working on ENSO-E and cello, and this is shows some of the types of problems that astrophysicists are interested in. These are visualizations of simulations by ENSO, which is the parent application of ENSO-E. And we can see that there's a very wide variety and different physics being more prominent in some than others. And these range over a very wide range of scales. From in the center, we have binary stars, which are modeled at the box size is about microparsec, up through the first stars, galaxies, galaxy formation, and up to cosmological structure formation, where you have box sizes almost billion parsecs. So it's a very wide range of scales. So we begin with the physics equations. Gravity is dominant. Usually, we also have hydrodynamics for modeling the gas, chemistry and associated cooling, magnetohydrodynamics, and cosmological expansion. These are solved by multiple numerical methods. And this forms the ENSO-E layer. We have the linear solvers for solving the gravity, the Poisson equation. We have a modified piecewise parabolic method for hydrodynamics. Grackle library, written by Britton Smith for chemistry and cooling. And we recently have VLCT MHD method implemented by Matthew Abruzzo. The data structures are next. This is the cello layer, and we use adaptive mesh refinement. This is because of the wide range of scales, not just between problems, but within a given problem. We want to be able to concentrate computation where it's needed and not where it isn't. We use an array of octree type adaptive mesh refinement. And the data, we include both Eulerian field, regular arrays of field data and Lagrangian particles. This is built on top of Charm++, the parallel runtime system, which we all know. So if we look at a, say, a cosmological simulation, which is the problem that we've been looking at recently, is we have this adaptive mesh of arrays of octrees, and each node in the octree is a block, and each block contains this field data and particle data. And this is implemented as a char array, so each block is a char. Dark matter, which is a predominant source of the gravity in cosmological simulations, is modeled using collisionless particles and cloud and cell method. It's a particle mesh method where you deposit the mass of the particles into a density field and then solve for the potential. We also want to include baryonic matter, which is just usual matter that we're used to. This is modeled using field variables, density, velocities, accelerations, and so on. And this is, again, with modified ppm hydrodynamics. And we add a flux correction step, which I'll talk about later. So there is, of course, communication involved between blocks. It's typically nearest neighbors. For field data, each block contains keeps a halo of ghost cells around the block of data that's assigned to the block. And these overlap the neighboring blocks. And so we have to periodically do a refresh operation where the data from where you send, the block sends its face data to its neighbors and then waits for the incoming face data from its neighbors. And it just counts the number of messages received, and when it gets the last one, then it triggers the next computation. And particles are also need to be communicated. The particles are assigned to the block based on the position. If it's inside a block, then it's assigned to the block. But these particles are moving around, and they might leave the block. You have to periodically send the migrated particles to the neighboring blocks and gather the particles from the neighboring blocks that are moved into the center block. So I'm going to go through a number of issues that I've been working on for the past year or two. The main one was scalable gravity. So we've had a number of linear solvers previously, including Krylov subspace methods, including the conjugate gradient method and BiCGStab. These are relatively easy to implement, just involve basic linear algebra and matrix vector products and vector updates. But their algorithmic scalability can be improved on. You can use preconditioning, however, to improve that. And communication can be intensive because if you do dot products at each iteration, and you can take hundreds or thousands of iterations, so you're doing a lot of global reductions. We also have a multi-grid method of just a basic V-cycle. It's a little harder to implement because it involves different types of communication and synchronization between blocks and parent blocks and child blocks. So not just the leaf nodes. This has better algorithmic scalability, but it's as our current implementation is only limited to uniform meshes. So our approach to finding a scalable gravity, implementing a scalable gravity solver is to use these available methods in some way. We tried two approaches, HG algorithm developed by Dan Reynolds, which used the multi-grid V-cycle to precondition by CG stab, and a domain decomposition method, which is our current solver of choice. So I just want to go over the DD solver. So it's we begin with a root solve. So this is a solve of the, even though it's an AMR mesh, we're just solving the problem on the root grid. And we've tested this on fairly large problems up to 2048 cubed on 131,000 processors of blue waters with pretty good scaling. It turned up a bit at the end, but for the AMR part, for the domain decomposition part, we used by CG stab, but restricted to subdomains. So when the subdomains are defined by the root level blocks. So it's the array of octrees. So this is the array of octrees. And we have a separate by CG stab solver going inside of each subdomain. And so there's no communication between these blocks, but there might be within blocks in a tree if they happen to lie on different processors. And finally, we do a smoothing operation. So with domain decomposition methods, you can get discontinuities and accelerations at the domain boundaries. So this is just an attempt to kind of smooth these discontinuities to improve the accuracy. And we already had the Jacobi solver available from the implementation of the multi-grid. So this DD solver, we didn't have to write any new solvers, just to combine the ones that we had. This is just a visualization from our favorite performance tool, projections, of a single cycle of the cosmology simulation. This is dark matter only, using this domain decomposition solver. Most of the time in the cycle is spent in the linear solver. So begin with global induction to find the stopping criteria. And we will at some point do adaptive time stepping. So this will not be, won't be a global operation. And we do the adapt phase, where we typically, for cosmologies, adapt to densities. So we have more highly refined blocks at denser regions. We do refresh ghost zones after the adapt. Deposit the mass from the dark matter particles onto the density fields, and to get a total density of field of both dark matter and baryonic matter. And then we begin the gravity solve. So we have, for the DD solver, we have these three steps. We have the multi-grid base root grid solve here. So we see we have two multi-grid V cycles, and they go down, do coarser and coarser grids until we get to a single block, solving the root grid equation prolonged back to the top. Do 2 cycles of that, and then run the by CG stab independent tree solves. And when they are finished, we do a smoothing, the last step to smooth the discontinuities across the domain boundaries. And then compute accelerations and move particles. So this is just a basic cosmology simulation cycle. So in implementing the DD solver, we uncovered some communication issues with the refresh due to, because we were a lot of different types of refresh patterns going on, sometimes getting in each other's way. So I mentioned this earlier, the way we used to refresh is you send data when it's available, and then when it's received, you copy into your ghost zones. But the problem is, if you have lots of different types of refreshes going on, you might not, block might be in some other step, and then some incoming data from some other refresh comes in. So it might not be ready for it. So to correct that, to make it work, before I just added more synchronization, but that kind of defeats the whole purpose of using Charm++ to begin with. So I addressed this by just adding a buffering layer. So now if the blocks still send data when it's available to the neighbors, when a block receives data, if it's not ready yet, then it saves it in a buffer. When block becomes ready, it copies any buffer data into the ghost zones. And after that, we know it's ready, so it continues in the same way as before. Copies it directly into the ghost zones. So a problem we're looking at is cosmology with dark matter and gas dynamics. So we have our scalable linear solver. We tried running this problem, and we found that we can run dark matter only AMR simulations fine. We can run unigrid, no AMR simulations with dark matter and gas. But when we combined dark matter and gas with AMR, it led to the problem blowing up eventually. And this is kind of what it looks like. So this is internal energy. And we noticed this seemed to always be at refinement level boundaries. So boundaries between blocks in different levels. So first thought was maybe this is because we weren't doing flux correction. So flux correction is due to fluxes between fine grids and coarse grids not matching each other. So we end up with fields that should be conserved, such as mass, not being conserved due to these conflicting fluxes between the fine grid and coarse grid. So what's typically done is in AMR codes is a flux correction step, where the fine grid sends its fluxes to the neighboring coarse grid. The coarse grid does a differencing of the fluxes and updates the adjacent coarse cells to take care of that difference. So it's basically the coarse grid uses the fine grid fluxes. So we fixed that. That took a while to implement, but it didn't actually fix the problem. So we had to figure out what else it could be. We had a pretty good idea though. So it was always at block interface boundaries, and we only had available a fairly basic interpolation scheme, just trilinear interpolation. And so this was our main suspect. But we wanted to try a few things, and we also have injection, which is even less accurate, but it is monotonic. So so it actually ran further than the linear interpolation, but we see these grid effects due to the being basically 0 order of accuracy at level boundaries. We thought it might be due to a time centering issue. We solved gravity at between 2 time steps. And there's a known bug in the adapt phase. So I just tried using the lagged value, which I knew was consistent, though maybe not accurate, but that didn't fix it. And also tried reduced order operators. The default is fourth order Laplacian and fourth order acceleration differencing. And that actually did help, but up to a point, it's still, we still ended up with the crashing. So lately I've been concentrating on implementing the interpolation scheme that is in ENSO. So we know that works. We've done these types of problems using ENSO. So the current linear interpolation in ENSO-E just involves these blue coarse grid zones that you want to get values for the green ghost zone somehow. So to do that, you have to extrapolate for some, at least some, if in this case, all of the cells, which leads to non-monotonicity. And so you can end up with negative densities, for example, which is exactly the sort of thing that would cause the crashes that we've been seeing. So we're pretty sure that this is the issue. ENSO's interpolation scheme, which is called second order A, uses an extra layer of coarse cells around the fine grid ghost zones that you're interpolating to. And so we don't do any extrapolation, it's all interpolation. So we know it's, you can show it's monotonic, it's second order accurate, and it's conservative. But it does involve some additional communication because this region overlaps extra blocks other than the two in question. So we have to deal with that somehow. So here we have block I. It wants to send its data to block J to fill in block J's ghost cells. And you have this extra padding of coarse cells around the ghost cells, and this overlaps some set of blocks BK. And this is a representative one. So the problem is that BK needs to know that it's participating in this communication defined by a pair of block I and J. So after thinking about this a bit, I realized there's enough symmetry in the problem that we can deal with this directly. So if we assume that the tree is fully balanced, meaning there's no level jump more than a factor of 2 across any face, including edges and corners, then we know that the block K must be in the same mesh refinement level as block I or block J. And the top, it's in the same level as I, and the bottom, it's in the same level as J. And in either case, we have this dual communication where in the top you have BK will at some point be sending its data to BJ for its ghost cells, and the BI will be participating in that. And in the bottom, the same idea. So we can use this symmetry to answer the question of BK knowing when it needs to participate in the communication. I also added, so the indexing of this got pretty complicated. So I just added a box class to help with computing the indices. I don't want to go into this in too much detail. You just define the neighboring block and its characteristics, and you get the region in question, and then the neighboring blocks can quickly determine whether they intersect that region or not and need to communicate or participate in the communication. So conclusion, we're finishing up the last steps, hopefully before we can run real problems. We have scalable gravity finished, buffered refresh and flux correction, and I'm currently finishing up the this ENSO interpolation. After this, we just have a couple remaining loose ends, scalable I/O. We currently have HDF5 I/O, which works sometimes, usually. It's a bit flaky and it doesn't scale well. So that'll be what I'll work on next. And we also had some questions about the scalability of Charm++'s checkpoint restart, but recently we heard that Ronak has implemented something that we're looking forward to checking out that will address that issue. And lastly, we've one of Mike Norman's grad students, Will Hicks, has noticed that the performance of ENSO-E when run on the same problem as ENSO was much slower. Now this is a concern because the whole purpose of ENSO-E is to be faster and more scalable. So we're looking into that. I think it can be several, there's probably several contributing issues. ENSO-E tends to over-refine relative to ENSO just due to its AMR type. That's octree instead of structured AMR, even using the same refinement criteria. Refresh operations by default are across edges and corners, as well as facets, which ENSO only uses. There's typically less communication in ENSO's gravity solver, and ENSO uses adaptive time stepping, which we haven't implemented in ENSO-E yet. And that's what I have. Thank you.
Thanks, James. I don't see any questions in the chat or the Google Doc, but I'll give people a minute.
Okay.
I have a question.
Yep, go ahead.
Okay, so you're mentioning scalable I/O. This is something that we're also interested in. And currently, we're also using HDF5 and all of the fun pains and struggles that are associated with that. So what we're doing is we're basically writing currently so if we're writing volume data, we're writing one file per node. And then we're writing all of the data contiguously so we're using DG and we write all the data contiguously, and we've found this of course helps, but it's unclear how well this will work. There's obviously, it's not perfect either. And so I was wondering if you've thought about what your plans are, or if there are people from other codes here, what they're doing for dealing with I/O in Charm++. Plus the other thing is, one file per node works until you get to tens of thousands per 10,000 nodes or so, and then the sysadmins start becoming unhappy with you.
Yeah, I've encountered that. Yeah, currently ENSO-E does one file per process, which certainly doesn't scale. Our initial implementation will be, one file per node, have one writer per node, and that will at least be an improvement on what we have now. We're also considering using an MPI library. So Charm++ can interact with, and MPI can run in the same application, and there are MPI libraries available. So we're planning on at least investigating that as a possible option.
Right, I guess something like because HDF5 I think has parallel I/O. I have no idea how well that works. I think that's MPI based. So is that one of the things you're thinking of?
That's
okay.
Yeah, I've only used the serial part of HDF5 so far, but yeah, using the parallel HDF5.
Okay. Thank you.
Okay. Thank you, James. I don't see any other questions.
Oh, I have a quick question.
Okay, go ahead.
I remember there was at some point some talk. I think I overheard it, ENSO-E discussion of implementing the fast multipole method for gravity solve. Is that happening, or
That's in the plans. We hope to
Okay.
get to try that. Yeah, the current our DD solver is it's okay. I think there is certainly room for improvement, both in the performance and the accuracy.
Okay, thank you. We'll go to our next talk then. Our next speaker is Philip Chang from the University of Wisconsin-Milwaukee, and he'll be talking about Changa, which is an astrophysics code that's a product of a collaboration between the Parallel Programming Lab, Tom Quinn's group at the University of Washington, and Philip's group at the University of Wisconsin. Go ahead, Philip. We can see your slides now. You're still muted if you're trying to talk, Philip. We can see your screen though.
There we go. Okay, can you hear me now?
Yep.
Okay. Right. So my name is Philip Chang, and I'm at the University of Wisconsin-Milwaukee. And I'm going to talk about moving mesh hydrodynamics in Changa. And this has been work I've been doing for the last 4 years in collaboration with Tom Quinn at U Washington, James Wadleys at McMaster. And I've also accredited a few other people along the way. The people highlighted in red, Logan Proust and Alexander Spaulding, are my students at UWM. I'm also doing work currently with Zachary Etienne at West Virginia University, Shane Davis at the University of Virginia, and Yanfei Zhang at the Flatiron Institute. Okay, so I'm going to give a brief outline of my talk. I normally give this talk to astronomy audiences, so I apologize. There's going to be a lack of deep numerical discussion here. But I'll begin with a discussion of basically how numerical simulations are done for astrophysical phenomenon, right? And basically, there are essentially 3 schemes, right? And for a large part, for most of the time, there's only been 2 schemes. So there's Eulerian grid codes, smooth particle hydrodynamics, and now this new arbitrary Lagrangian Eulerian code, right? And I'll talk about pros and cons of these things, right? And well, basically the code that I've been working on called Manga, which is just a module built upon the SPH code Changa, right? And I'm going to discuss basically 3 problems that we've been looking at this, actually 2 problems, okay? So the first is common envelope evolution. The second problem I'm going to talk about is tidal disruption events. And then basically I'm going to talk about basically work that's ongoing on basically adapting the moving mesh hydrodynamics to general relativistic hydrodynamics, in the hope of basically eventually studying neutron star mergers and stuff, right? And the results of this work, I actually put my original paper, Chang, Quinn, and Wadleys, 2017. But basically, here's a list of some of the papers that we've written over the last few years on this. Okay, so to begin, let's talk about basically the basic equations that we're after, which is the Euler equations, right? And so I wrote down 2 of them. It's actually one more, which is conservation energy. But the first is continuity, which is mass conservation equation. The momentum equation, which is the conservation of momentum, right? And when you write this out, all right, there are 2 ways of viewing these equations, right? Okay. And in particular, if you look at the continuity and the momentum equation, right, you can break it down into basically a partial respect to t plus a velocity dotted with a gradient, right? And that can be thought of basically as either Eulerian view, right, or Lagrangian view, okay, where basically Eulerian view you take the partial time derivative, and the Lagrangian view you take the total time derivative, right? And the idea is pretty simple, right? So in the Eulerian view, what you're doing is if you're thinking about flow, all right, you're laying it down as some fixed grid. And on that fixed grid, basically stuff goes into the cells and comes out of cells, all right? This is thinking in terms of the fine volume methods and whatnot, right? You're essentially tracking how the fluid flows, right? But there's another method, which is Lagrangian method, which is popular for smooth particle hydrodynamics, where basically rather than thinking about how the fluid flows, you imagine yourself embedded in the fluid, or you are a fluid particle, and you basically are just basically flowing along, subject to basically F equals ma forces. All right, so let's talk about a little about smooth particle hydrodynamics. I got this little picture from Wikipedia because it's nice. All right, so you model the fluids as a number of discrete particles. You can, in principle, you will get the accurate approximation of hydrodynamics when you go to infinite number of particles, but that's not possible using present-day computers, right? And so you have a bunch of these particles which are subject to F equals ma, just basically Newton's second law. All right, now the issue is that the F part, some of the F part comes from pressure forces, and pressure is something that depends on continuum values, right? So like density, for instance, and so you need some estimate of these continuum values, right? Okay, now we have a bunch of discrete points. It's not, in order to generate an estimate, what you do is basically you do a weighted count over some volume. Okay, so you include a weighted count over the nth nearest neighbors over some volume, and you get some idea what the density would look like, okay? And so the mathematical challenge, meaning computational challenge actually, is doing a rapid search over the nth nearest neighbors. But it turns out that we know how to do this already, right? With n by tree codes, right? So this smooth particle hydrodynamics maps extremely well with n by tree codes. And so for that reason, a lot of the main large scale cosmological codes, like Gadget or like Gadget, for instance, or Gasoline, or even Chang'e, right, basically started out as SPH codes because it's actually very easy to put in smooth particle hydrodynamics once you have an n-body tree code. Okay, now the other way of thinking about this, all right, which is the stuff which I think most of us are working on, is the Eulerian scheme, right? And so what you do is you basically break up space into a number of discrete points, right? And again, in the approximation of infinite number of grid cells, you get accuracy. You basically recover continuum dynamics, right? But again, that's not possible, right? And so what you can write is that when you write the equations for hydrodynamics, right, you can write them as a flux conserved equation. What that means is that basically, if you think about these cells, right, there's some stuff in these cells, right? And if you integrate all that stuff, there's some total charge in that cell. Like it could be the total, like if you integrate over the density, over the cell volume, it's like the total mass. Integrate basically over the momentum density in that cell, integrate over the volume, that's the total momentum, right? And that charge basically has stuff coming in, which is the flux, and stuff leaving it, which is also the flux, right? And so basically, all you're looking at is essentially a flux conserved equation, which is basically the change in time of some quantity is equal to the divergence of flux, which is basically the flux coming in versus flux going out, plus basically an extra source term, right? And that's basically it, okay? And so basically a lot of this stuff is basically solved for the fluxes, is solved using some sort of usually approximate Riemann solver, okay? Now, there's one last scheme which was not really done in astrophysics for a long time, but is used a lot in basically solid mechanics and whatnot, right? And this is the so-called arbitrary Lagrangian Eulerian scheme, right? And it turns out that basically what you can do is that like you can actually move the grid along, right? And usually this grid is vector as something like a local quote unquote flow velocity, all right? So this is used in continuum mechanics a lot, all right? I'm going to go back in, so I'm going to start the movie again. So the top picture is basically a piece of steel cutting into another piece of steel, right? And you can see the action only occurs at basically essentially one point, right? Everything else basically, the steel is quote unquote just a vectoring along going along for the ride, right? In the bottom picture is basically a bullet that's hitting some liquid stuff, right? Just basically just spewing stuff around, right? So a lot of times these arbitrary Lagrangian Eulerian schemes, the meshes are unstructured, they have strange arbitrary boundaries, right? Because it's basically mainly for fluid-solid interactions, right? And if you do it right, okay, sometimes there's big speed improvements, especially if the flow velocity is much, much higher than the local sound velocity, right? So I didn't realize this until I started working actually on this topic, right? But arbitrary Lagrange Eulerian scheme is used heavily in the defense industry, like tremendously so, right? So I'll show you a few pictures again. So in the top picture is basically a 3-point shock, okay? You have a shock wave moving in from the left, and it's hitting basically a lighter fluid on top and a denser fluid on the bottom. And because of that, it induces vorticity as it goes around, right? Okay, and basically you're trying to follow this, you're trying to cause the mesh to basically follow the fluid flow, right? As go, and you see what happens. Basically, the mesh starts to get really, really distorted, right? And so basically to correct this, right, you need to usually remesh this stuff. And there are lots of literature basically associated with, especially in defense and the national labs, discussing how you do this remesh, right? Okay, but the basically idea is you let things flow, the mesh starts to get tangled, all right? And once the mesh starts tangled, you basically want to remap it. And you can remap in one way, two ways. One is that you could just lay down a new mesh and remap all the points. The other way you could do is basically you could have the mesh relax basically back to its original phase, right? And so this remeshing typically is a numerically pretty diffusive action, all right? And so that sort of defeats some of the purpose of basically these arbitrary Lagrange Eulerian schemes, right? And for in large part, basically, this was not widely used in astronomy until about 2010, all right? And the key development was basically a development of numerical hydrogen on Voronoi meshes, which basically not solves the problem, but basically allows the problem of remeshing to basically happen in a continuous fashion, right? So let me talk about that briefly, okay? So let me talk about Voronoi tessellation, right? So suppose you have an arbitrary distribution of points, right, in space, and you want to basically divide up space in via using these arbitrary distribution points. So how will you do that? Okay, so it turns out there's a tessellation known as the Voronoi tessellation, where in order to do this, what you would do is you basically pick 2 points, right, any 2 neighboring points, and then between these 2 neighboring points, you would draw a perpendicular bisector between them, right? In the case of 3D, it'll be a plane then. Whoops, where's my mouse? Sorry, it'll be a plane, okay? If you draw a perpendicular bisector, and then you basically continue this operation. So you basically pick the next 2 points, draw a perpendicular bisector between them, draw the next 2 pick perpendicular bisector between them, and so on. And when you do so, right, you will get a tessellation of space, right, where every point in that cell is closest to the point that is defining the cell. And the tessellation has 3 unique properties, which is important, right? The first one is that the tessellation is unique, right? There's only one way of drawing this tessellation when you do this. The second important thing is the cells are convex, right? Which essentially means that basically everything in the cell is closest to the point that's defining the cell. And thirdly, the most important thing actually is that as the cell deforms, as the points move, the cell will deform continuously under small perturbations, right? And you can see this basically in this picture I have on this on the left. We have a small blue dot moving across this Voronoi tessellation, and the tessellation doesn't change every time the dot moves. It basically slowly evolves as it goes across, right? And so these well-defined faces, well-defined volumes, and basically slow evolution of these phases and volumes allow finite volume methods to apply this. And this is what Volker-Springel basically discovered or rediscovered in 2010, right? And so what's also interesting is that basically any flux conservative equation can be solved using in these moving unstructured meshes, right? And so there's been a huge explosion of basically moving mesh codes based on this methodology in astrophysics, at least. REPO is basically Volker-Springel's code. There's also RICH, all right, Rockout Institute Computational Hydrodynamics by Sternberg. There's TESS by Duffel and Mafagian, and then there's MANGA by myself, Tom Quinn, and James Wasley. Okay, let me talk a little bit about pros and cons of Voronoi hydrodynamics, right? So there are a few great things, right? So because the mesh can move with the flow, you don't have to have so much advection, right? And so basically you get better advection than Eulerian, right? Just because you don't have to do so much, okay? In principle, you can have better conservation of angular momentum compared to Eulerian schemes because you just don't have 3 special directions. The directions are arbitrary, right? You definitely have superior shock capturing compared to SPH. SPH tends to basically smooth out shocks over several smoothing lengths, right? In this case, basically, if you use a Riemann solve, you can just capture it basically in one cell, right? You potentially have better capture of interface instabilities. This is in principle. This is a debatable point because it's not entirely clear that like moving meshes are actually better, but they certainly look better in a lot of basically comparisons, right? You can do MHD, right, in the moving void nodal mesh, unlike SPH, though that point would be debated depending on who you talk to. Those people, unfortunately, I believe are wrong. Okay. You have continuously varying resolution. So rather than basically having jumps of basically factors of 2 and 4 between cell boundaries, the resolution can vary continuously. Okay. And almost anything that's solvable on Eulerian grids maps to void nodal methods. Right. That's the pros. The cons is that basically they're far more complex. All right. The combination of Lagrangian schemes and Eulerian schemes plus computational geometry make the codes a little more hard. You start to force yourself to think about the grid now. Unfortunately, you got to think about basically how you want to map things onto a grid, which has plus and minuses. This forces you to think a little harder. On the other hand, basically, it also basically opens up a whole other can of worms. It's quote unquote slower. I put that in quotes because basically in my testing, comparing to SPH, it's not necessarily slower, right? The heavier computational side is offset in large part by basically higher resolution per point and also a larger Courant time stepping typically. The other thing is that like MHD is usually divergence cleaning space schemes or vector potential based schemes, right? So no stag of CT scheme, which is like the gold standard for MHD, exists in these methods, right? And finally, there might be overkill for some of these problems, right? However, I would say that like the advantages in vection, shock capturing, and basically conservation law make it great for dynamical stellar problems. Basically, stars hitting each other, stars basically getting ripped apart, that kind of stuff, right? It's also used for galaxies, but that's not my forte, so I'm not really discussing that. I'm going to talk a little. Manga is a void nodal hydrosolver for Charm++ n-body gravity, or the Changa code, which is n-body SPH code. It basically uses the Charm++ programming model. Everyone knows what Charm++ is. This is there because usually you give this talk to astronomy people. Like, what's Charm++? I have no idea. Like basically, it makes it easier to write hybrid codes essentially. All right, and Changa. All right, this is a very old plot now, like 2014. All right, but it's still true. Changa still is pretty well in pure gravity up to about 500,000 cores, 93% efficiency. Right. Okay. Here's a little bit of basically some of the physics that we have in Manga now. So we have, oh, this is all messed up. All right, so I got to talk about. So in the left top thing is actually should say hydrodynamics at the end, but this is what happens when you use Linux presentation software. So this is a Sadov explosion. Okay. On the top right is self-gravity. Okay. On the bottom one is a stellar equation state. So we have different equation states for this one. This one's an interesting equation state. If you are eagle eye and you look in the bottom, you will notice this star is only about 10, 15 kilometers in size. This is actually a neutron star. And the equation state here is a nuclear equation state we adapted basically from literature, and we put it in Manga. So there we have a bunch of different stellar equation states in Manga, including basically, well, like stellar equation states for white dwarfs and for regular stars and for planets, etc. Okay, there's some other physics that we have involved as well. One is radiation. Manga is in fact a full radiation hydrodynamics code, right? And for those of you who can see this, right? You will notice that basically what I have is I have two light beams basically crossing each other, right? And this turns out to be a really hard problem. And it's actually most radiation hydrodynamics codes will fail at this task, okay? Mainly because a lot of times they either use methods called flux limit diffusion or moment one methods, right? Which basically do not either in the flux limit diffusion do not allow basically beams to exist, or in the moment one method only allows basically one beam in one direction to exist, right? And so basically you have crossing beams, that's kind of nice, all right? So what we have is we actually solve the full time-dependent radiation equations, but using in the reduced BLI approximation in order to keep the time step from going crazy. And the other one that we are able to do is basically we can do some GR hydrodynamics in static spacetimes at this point, right? So this is basically work that I recently did with Zach Etienne. Okay, all right. So let me talk a little about some of the current features. This is basically was highlighted in the previous slide, but then a little more detail here. We have hydrodynamics on the Voronoi mesh, self-gravity. So with self-gravity, we have either entropy or energy solving, depending on your choice, right? We have a multi-stepping scheme, so every single cell has its own time step, all within a factor of 2 of the global time step. We have a all within steps of factor of 2 with the global time step. We have different equation states, including Mesa equation state. We have basically what's called moving and reactive boundaries. I'll talk about that later. We have radiation hydro. We have GR hydro on the moving mesh as well. Okay, in static spacetimes, right? In terms of near-term goals, we're basically hoping to get open source version out by early or mid 2021. There's no showstoppers here. It's just that I'm just lazy. The other thing is that we're also working on constrained transport, all right, for MHD. And we also are working on basically moving mesh GR hydro, hopefully for binary neutron merge. This basically involves adapting a dynamical spacetime solver and putting it into Manga. For longer term goals, we're hoping to basically do higher order spatial reconstruction methods, right, in the not too distant future, perhaps core collapse supernova or moving meshes with neutrino radiation, and for point source radiation as well. That one's like, that one's actually more straightforward. It's just that it's not on my immediate to-do list. Okay, let's talk about a little common envelope evolution, some of the applications of this. All right. So what's common envelope evolution? Since most of you are computational people, I'll just talk a little about it in terms of astronomy. So you look up at some of the most interesting systems in the universe. These are basically stars that are really close to each other, and they're usually like compact stars, like either white dwarf, white dwarf, neutron star, neutron star, white dwarf, or black hole, black hole. Like these are stars are really close to each other, and when they basically are close to each other, they can do interesting things, right? Now, the problem is that how do you get them close to each other, right? Because stars, when they start out, they're actually relatively big compared to white dwarfs or neutron stars or black holes, right? And one of the leading ways of thinking about this is that basically what happens is that they undergo something called common envelope evolution, where basically a star, hold on a second, I need to tell someone not to call me. I don't know why. I'll kill it. Okay. Sorry, I apologize for that. And so what happens is that as a star evolves, basically it can it goes to the red giant branch, and if this neighboring star is close enough, it can actually basically fall into this envelope. And when it does so, basically the star basically interacts with the envelope and basically expels that envelope, and in doing so, it basically converts its gravitational potential energy of the orbit to basically expelling the envelope, and in doing so, it basically reduces the orbit of the two stars, right? Such that they can get close to each other. And these pairs of binaries are perhaps very important. They can basically produce supernova, they produce millisecond pulsar, they produce basically binary neutron stars and binary black holes, which is very interesting for people who are gravitational waves right now. Okay, so here's basically an example of what we've been doing with Manga. So you have two cores, which are denoted by the X and cross, and then the big star is the center mass of the system. And what happens is that basically we start out basically a red giant star with a 52 solar radii and a 1 solar mass secondary, right? So we treat it as basically a dark matter particle, and we basically let these things orbit each other, and we run this for basically 240 days, not in computer time, but in basically system time, all right? And basically 110 of these days is shown here. Right, and the question is basically, does the envelope get ejected, and how close does it get at the end? And the answer is that basically what we find is that in large part we can eject most of the envelope, assuming that we can basically take account of the internal thermal energy. So basically, if we take account of the internal thermal energy, we get something like 66% of the envelope is ejected, which is great. Okay, and the envelope and the orbit shrinks substantially. It goes from basically 52 solar radii all the way down to about 3. Okay, so that's pretty good as well. All right. Now, there is a question here, which is basically, can you actually include the thermal energy? All right. And the argument against it is that basically, well, if you try to include thermal energy, what happens is the envelope expands and then it can cool. And then basically it cools, all that thermal energy goes away as radiation and actually act as a way of expanding out that envelope, right? So we're basically working on that problem as well, thinking about basically ways of including cooling effects in the envelope to see basically how much of this envelope ultimately actually ends up getting ejected, right? The other thing I want to talk about, this is work mainly done entirely by my student, right? Is that if you think about it, all right, you have a red giant. The red giant is kind of big and poofy, right? And then you have a solar mass star like sun. And relative to the red giant, the sun is like a big, dense object, right? And so if you think about it, you can think about basically, what if you place a big, dense a marble and have a circulating rising around this star, okay? What happens? Well, right now, we've been treating things as a dark matter particle, which basically it doesn't interact with the matter at all. But if you think about it, what happens is that the gas can basically hit the secondary star and bounce off, right? Okay, so and that hydrodynamic flow is not really accounted for in current models of common envelope evolution. And so that's basically one thing that we want to think about, was that basically, can you basically put arbitrarily shaped boundaries, right, with arbitrary boundary conditions inside the simulation, right? And so this is one thing that we've been doing, which is called moving reactive boundary condition. The secondary star itself is itself a boundary condition, a reflecting boundary condition, and that reflecting boundary condition basically realizes the forces that are acting upon it and basically moves the second star with it. Right, and so basically, this is an example of this problem right here. What I have is basically a wall hidden basically between position x equals 3 and x equals 5, and then I just set off a quote unquote a Sadov 1D Sadov explosion on it. Okay, and then as you can see, what happens once it hits the wall, right? It's going to bounce off the wall, send back a reflecting shock, right? But the wall will basically move and basically send a forward shock basically through that material as well. Okay, right. And so we've been doing this basically common envelope with a hard secondary. So basically moving boundary condition run with the same initial conditions that we did earlier. And we get basically a somewhat different in spiral, though right now, as given the stuff that we've done much more work since this time, we don't really think it makes a huge difference for the common envelope evolution, all right? But more analysis remains to be done, okay? All right, so I'm gonna talk about my next problem. Let me see how much time I have. Am I out of time? I might be. So I'll skip
a couple more minutes, yeah.
All right, so I'll skip this thing. All right, so tidal disruption is like stars get ripped up by black holes, right? And then let's show a movie. Here's a star, it gets ripped up by a pole. It gets basically spewed out, right? This is interesting. And then you have accretion onto the black hole as well. And so what we've been finding is that basically what we're interested in is basically how is this material distributed in energy space afterwards as a function of how deeply penetrating it gets in. And basically what we find is that basically it rises for some period of time and then basically gets cut off, right? And that cutoff is known as frozen approximation. And so we have a pretty good understanding of how this thing works. Now, this is important based understanding what the accretion rate onto the black hole is going to look like. All right. Last thing we'll talk about is general realistic hydrodynamics on the moving mesh. All right. So as I talked about before, any equation can be solved on the moving mesh that we've written as a flux conservative equation. And so basically on the top, I have what it will look like for hydro, and the bottom I wrote what it looks like for general realistic hydro, right? So it looks almost the same, all right? Same in quotes, all right? And so you could basically solve it using the same methodology as before, right? And so this is basically what we have done. So this is a Tolman-Oppenheim-Volkoff star, which is essentially a neutron star on the moving mesh, right? So we model this thing with about 1 million mesh generating points with basically 1 million more filling the atmosphere, right? And we have a fixed basically metric, and we just run this for basically 24 dynamic times. You can run it for longer if you'd like, right? And what happens as a function of resolution, this is shown on the on the right plot. As a function of resolution, basically, there is a difference in terms of basically how much the central density drifts as a function of time, right? And as a function of resolution. Namely, at higher resolution, basically it drifts less. Now, this is understood, right? And so we get a 2% drift with 1 million particles or so, right, over 24 diameter. This is terrible compared to basically what grid codes are able to achieve, right? But we know what the problem is actually is basically these single star evolutions are extremely sensitive to spatial reconstruction. And for these moving mesh methods, thus far, the only reconstruction method that's been really developed is second order. And so you probably need to go higher order basically too, right? So this may be fixed in the near term with developments in unstructured higher order methods, which I don't know much about, but I'm hoping to learn more about it. Okay, and basically this is another thing that you can do, but just to test it out. You can reduce the pressure of the entire star by 10%, and the star will just begin to oscillate radially at the fundamental mode. And we can compare that to basically a known solution from a known code, Illinois GRMHD, shown in a dotted line in the right column. And you can see basically the fundamental mode is more or less recovered for all different things, either in multi-stepping or in single time stepping, right? So in the future, we're going to basically try to include a dynamic space-time solver and a Mongoose for full moving mesh binary neutral star simulations. All right, these are my conclusion slide, and I'll just stop here.
Thanks, Philip. We do have one question in the chat from Mike Norman.
Okay.
He asks, do you use a fixed or variable number of generating particles for your Voronoi mesh? If fixed, how do you deal with the very low density regions, which would be undersampled?
I'm not sure what he means by fixed or variant. I think we can use an arbitrary number of particles, and what we do is basically we don't fix them anywhere in space. We change the resolution as we go outward. So the key with these moving mesh methods is that not to have sudden changes in resolution. And so as we move away from the point of interest, we basically increase the spacing between these particles so that basically so that you don't spend too much time like computing stuff you don't care about, all right, with too many particles, but you also want to avoid basically sudden changes in resolution as well. And I saw someone raise their hand, but I have no control over anything. So,
Tom Quinn, you can go ahead and ask if you can unmute.
Hey, Phil.
Hey.
Great stuff you're doing. So, do you have any scaling plots? I mean,
I don't. Scaling is a slight issue right now. So why is that? So so the thing is that like for every computational step, all right, I have to do, I think right now is 3 nearest neighbor searches, all right? Whereas basically in SPH, you got to do just 1, right?
Right, we actually 2 actually. But
you're actually doing 2? All right. Okay, so I got to do 3, okay? So that I think is the limit of the scaling. Haven't done a huge amount, and part of the reason why I've been focused much more on implementing different physics into the code right now. All right.
Mm-hmm. No, it's great. You're doing that. This is wonderful. Yeah.
One last question from Neil Stepp. He said current codes use an atmosphere treatment. Is that still necessary? And if so, how low of an atmosphere can you use?
So the answer is that any Eulerian code will need an atmosphere treatment. So yes, we still need atmosphere treatment. No, any grid-ish code will need atmosphere treatment. You can't have vacuum basically. So yes, we do need that still. So I believe for the so there's 2 answers to this. So for the star, when like tidal disruption or common envelope, we can go about 15 orders of magnitude difference. Okay, for the GR hydro right now, I think I'm down to about 7 orders of magnitude difference. All right, between the central density of the star and the atmosphere. All right, maybe it'll go lower than that, but it starts becoming unstable actually after if I go much lower.
Okay. Yeah, I think you need about 16 orders of magnitude
For
for the relativistic case. Current
well,
state-of-the-art codes use
yeah.
about 10, and that's still not quite enough.
Right. Okay. Well, okay. So I mean, like, I thought you were about to say there's a code out there that can do 16 orders of magnitude difference in the relativistic. I was like shocked. But yes, you're right. Yeah. So yeah, you do need that.
There is a code that can do 16 orders of magnitude.
Oh, really? Which one is that?
It's by David Radici.
Okay.
So they basically use a flux limiter, a positivity preserving flux limiter.
I
and so
see.
they don't. So I'm trying to
Interesting.
remember if they were able to do magnetic fields with that or not. But without magnetic fields, at least they can do 16 orders of magnitude.
I see. Okay. All right. That's interesting. All right. So I know you're part of the Spectre group. Is that right?
Yeah.
And how many orders of magnitude can you do right now from their center?
We're trying to do DG, and that's even harder. For DG, we've basically given up on using DG for high order hydro because you basically can't go beyond second and third order, right? So it seems to be good for sort of where the solution is smooth, but basically all the limiters in the literature to handle discontinuities are basically worked out for Newtonian hydrodynamics on Cartesian grids, and we want to do curved meshes with relativistic hydrodynamics, and it turns out they just don't translate. So we've basically switched to a finite difference DG hybrid method. We have not tested the relativistic case. In the non-relativistic case, so the Elaine Emden stars were able to do 24 orders of magnitude.
Right. Yeah.
But how that translates to the relativistic cases is to be determined, hopefully soon.
Right. Okay. Well, thank you for that note. That's interesting. Flux.
Yeah. No,
flux
I mean,
limiter.
I was just curious because
Yeah.
I have not personally. I personally have no experience with these like truly moving mesh, right, where like you follow the fluid. So we use a moving mesh, but we basically it's basically to capture the rotation and shrinking of the orbits as the neutron stars orbit each other, but it's not to track the fluid motion. So
yeah, it's the same as the old spec code, basically, right?
Yeah, exactly. Yeah.
All right.
Yeah. The big difference is we're treating the Einstein equations and the hydro equations on the same grid, as opposed to in spec where they're on two different grids, and that interpolation adds an enormous amount of computational overhead. So that's sort of the big difference.
I'll ask that you take more conversation into the chat or offline, and we'll move to our next talk. Thank you, Philip, for the presentation.
Thank you.
Okay, our next speaker, the last of the session, is Francois Hubert from Caltech. I believe he's a postdoc there. And today he'll be talking about the Spectre application, which we've been hearing about for the past couple of years. So go ahead, Francois.
Sorry, I'm trying to show my slides.
Yeah, are you able to screen share?
It seems I may need a Zoom reboot before it will let me. Yeah, sorry, I have to quit the meeting. I'll be right back.
Okay. Yeah, there's a permissions issue there where you have to restart Zoom sometimes in order to do that.
All right.
Okay, we can see it now.
And can you, let's see. So is that still visible?
Yep, looks good.
Okay, great. Sorry for the snafu there. Okay, so yes, I am Francois Hébert. I'm a postdoc at Caltech. And I'll be sharing some updates on the development of the Spectre code, and in particular focusing on our work towards simulations of binary black holes. This is work done with many folks in the Simulating Extreme Spacetimes collaboration. So to provide some context here, I'll first start by reviewing the role of these simulations of binary mergers in astrophysics. I'll review some of the current methods used in codes today and the challenges that these codes face, which will lead into how we hope to improve on these methods, both in terms of the algorithms and the scalability in our new code Spectre, and then I'll show some results. A main motivation for these simulations is, of course, the discovery recently of gravitational waves. So LIGO and Virgo are gravitational wave observatories, and they've measured signals from merging binary black holes many galaxies away. And in order to process their data, they rely on accurate waveform models that are produced by computer simulations. So this enables them not just to characterize a signal that they see, in other words, say, oh, this looks like it came from two black holes that were this massive and were spinning at this rate, but it also allows them to look inside the data stream for weak signals. So on the left here is a visualization of the LIGO data where you can see how much power is in at different frequencies as a function of time. And there's a very loud signal here that you can see by eye, but sometimes the signals are much fainter and you need to do matching techniques to find correlations between the data stream and a predicted signal that you have in hand. So we give them these predicted signals. But looking to the future, these detectors will become much more accurate, especially space-based detectors on sort of decade timescales. And as these become more accurate with less noise, we will need our waveforms to also become much more accurate so that we don't contribute systematics in the analysis pipelines. For the matter case, we've also got some really good results coming in recently with observations of merging pairs of neutron star in telescope recently, actually directly imaging an accretion flow around a supermassive black hole. The simulations here are our best tool for getting a model for the matter dynamics. So what is really happening as the matter flows around. It lets us understand how heavy elements are created in these extreme environments, where heavy here in the context of astrophysics is really everything beyond helium. So everything we're used to interacting with in our daily lives, it's still not completely clear how and where it's formed. These simulations also give us a great tool for understanding the radiation that comes out from a merger event and relating it to observations of infrared, visible, ultraviolet, etc. Unfortunately, these hydrodynamic simulations in particular are very expensive, and we struggle to reach the accuracies that we're interested in. So let me give you a little bit of a feeling for what these simulations actually are doing. Here is a very nice visualization of a binary black hole simulation. So you can see a big heavy black hole in the center and a smaller black hole that is orbiting it. The black hole, the small one, is spiraling in as it loses energy to gravitational waves. And these color contours are a visualization of the curvature of the space-time that is carrying the gravitational waves out to infinity where we might see them. So the thing to note here is that the space and time itself are the thing that's dynamical and being evolved. The black holes themselves aren't an object in the space-time, they're just a mathematical feature of the curved space-time. So we're evolving the space-time. And in the cases where we have matter, we still have to do all of that work of evolving the space-time. But on top of that, we now have very dense nuclear density matter, for example, in the case of a neutron star merger, that is flowing around, gets disrupted, it collides with itself, creating shocks, heating, turbulence, and all kinds of very complex dynamics. So to formalize a little bit what I've shown here in nice pictures, we're looking here to solve a large number of coupled PDEs. There's 50 of these for the space-time dynamics, and on top of that, there's a whole bunch for the GRMHD. The general form of these hyperbolic equations is given here. We have some vector of fields U that we're evolving, so this would be the 50 to 60 PDEs. And the time derivatives are given by some flux terms for equations that can be written in conservative form, or some non-conservative products relating to derivatives of U and sources. The complication here is not just the number of PDEs, but also the fact that they have some annoying features. So Einstein's equations that describe the evolution of the spacetime, for example, you have to worry that because the space itself is what you're solving for, you have to make sure you have a good set of coordinates that is a good representation of the features of the curved spacetime that you're interested in resolving. And you need to worry as well, of course, about the singularities inside the black holes. The methods that we use typically don't like infinities, and so we want to make sure we have a strategy for handling those when they come up. And for the relativistic hydrodynamics, you've got turbulence and shocks, as with any other hydrodynamic situation, but you also have to worry about your neutrino and radiation transport, nuclear reactions, and any other physics you may want to add in. So all of this put together is what makes this a challenging problem and why these simulations are long. The majority of codes that are in use today employ finite volume or finite difference methods to solve these PDEs. So I'll just sort of summarize a few key points here. We represent the solution as values at grid points. And typically the grids used are Cartesian grids, probably overlapping. If you're doing mesh refinement, you would overlap grids of different resolutions. A main reason that these methods are favored is that they have a robust collection of schemes that have been developed for handling shocks or other sharp features in the solution, like the surface of a star. So they're well suited to the hydrodynamics in that sense. The accuracy is what we call polynomial. In other words, the error between your numerical solution and the true solution decreases polynomially as you increase resolution. And here on the right, I'm showing some, not just the grid structure itself, but also this idea that once I partition up my grid onto multiple processors, and I need to make sure that the simulation remains causally connected across the domain, I need to send information to the neighboring grid patches. And I need to fill in this sort of little buffer region all around my grid patch, which is called the ghost zone. And unfortunately, this ghost zone has some depth to it, which means that I can't arbitrarily reduce the size of my grid patch because the volume of the communication is sort of unfavorable to that scaling. So these methods are used in the majority of binary black hole simulations today, as well as all of the matter simulations. Another class of methods that is used is what we call spectral methods. So here we represent the solution as an expansion over a basis. On the right, I'm showing an example, a very simple case. The grid patch is a square, and I'm going to use as a basis probably a tensor product of Lagrange polynomials or something like this. And we can often map these shapes to take advantage of any symmetries in the solution. One side effect of this basis expansion is that we really want to be using these methods for smooth problems. Otherwise, the basis will not provide a very good representation of the data. But when the problem is smooth, you get an exponential convergence. So the errors decrease very, very fast as you add grid points, which gives us really good accuracy and efficiency. To talk to the neighbors in this scenario, you're only sending boundary data. So the orange points at the edge of my little figure here show the data that gets sent out to the neighbors in each corresponding direction. So this is you let your neighbor know what the flux is through your interface, and then you can apply corrections to connect the domains together for the simulation. So these methods are the state of the art for binary black hole simulations, giving the best accuracy and the fastest simulations. To run these simulations on big computers, most codes today use message passing, MPI, with some threading. Typically, a finite volume or difference code will scale to ballpark 10,000 cores. I'm going to say a little bit more about SPEC, which is the code of our collaboration that we use the spectral methods in for doing simulations of black holes and spacetimes with matter as well. So here we distribute one spectral element onto each core. And if we're also doing hydrodynamics, we have ballpark 100,000 cells per core. But our code really scales only up to about 50 cores. And part of this is the number of spectral elements and is really a reflection. This statement applies to the finite volume as well. These scaling limits are really a reflection more of design choices that were made some number of years ago, maybe 10, 15 years ago, before we really had to worry about exascale computing, rather than fundamental limitations about the PDE solving methods. So I've opened by saying that we would really like our codes to be producing more accurate simulations, but unfortunately, we're already sort of at the limit of how patient we can be. So simulations of binary black holes will take maybe a week to multiple weeks for hard parts of the parameter space, if one black hole is big and the other is very small, or if you need many, many orbits. Simulations of binary neutron star mergers will take a month to multiple months. And so to get the improvements in accuracy that we're looking for, but not stretch the limits of our patience, we're really looking here to improve the not just the numerical methods to solve the PDEs, but also the parallelism algorithms to get better scaling. So this is our motivation for having started work on our next generation code, Spectre, for relativistic astrophysics in particular, but it's a PDE solver more broadly. We're going to improve the algorithms by using discontinuous Galerkin. So we've heard already a few statements, but I'll say a little bit more myself. And we're using, of course, task-based parallelism with Charm++ to enable more flexible workloads, really, because these astrophysics problems are not very homogeneous. And so one struggle that we have is making sure that the load is well distributed across the computer. So in the remainder of this talk, I will be showing a little bit the methods that we use for our binary black hole simulations. And I'll be giving some preliminary results for the binary black hole, as well as some load balancing experiments we've just started doing in Charm++. A big focus of Spectre has also been to think more carefully about the hydrodynamics algorithms. So this was actually just discussed in the Q&A of the prior talk, but that will not be in the scope of this talk today. Discontinuous Galerkin is a generalized spectral method for solving a PDE. So it has most of the features that we really liked about spectral methods. For example, it has the basis representation of the solution, which enables really good exponential convergence when your solution is smooth. It maintains the geometric flexibility. But on top of that, it sort of gives you a framework for thinking about how to fall back to shock capturing schemes where that may be needed. And this enables you to think of this method to handle both the space-time and the hydrodynamics together in the same scheme, sort of unlike what we've been doing in our codes in the past. As per spectral methods, the communications are typically nearest neighbor boundary data only. So this is a lightweight and efficient. And you can formulate AMR and local time stepping in here as well, which will really let us put the resolution, not just the spatial, but the temporal resolution as well, where it's most needed to get the accuracy we're looking for. So to show you that this all works, here's a simple code test of an evolution of a single black hole. So there's an exact solution for this space-time. So we can do our numerical simulation and compare it to this exact solution and check how well we're doing. So that's what is done in the plot on the left, which is showing the error in the space-time as a function of time. And you can see that as you go down through these curves and we're adding more and more grid points, the error drops by, in fact, more than an order of magnitude every time you add one grid point per dimension. So this is the exponential convergence I was just talking about. So this is a great result. And then on the right is a plot showing that this is stable. This is just one resolution, but now evolved for 100,000 dynamical times, and it's perfectly smooth. So the code is nice and stable for single black holes. We've also tested the convergence, sorry, the scaling. So this is a result from a couple years ago now on Blue Waters, where we're showing weak and strong scaling of Spectre. The green lines here are the strong scaling, where you divide the problem into more and more processors, and you hope that the runtime will linearly go down, and we find that it very nearly does. And the blue dashed lines are the weak scaling, where we solve a bigger problem on more processors, and we hope that the runtime stays constant, and again, it nearly does. So this is going up to about 100,000 cores. And so this makes us feel pretty good about our choice of Charm++ as scaling really well to large numbers of processors. Now, from here, I'm going to outline a few of the ingredients that are necessary to do a simulation of two merging black holes. The first is, of course, you need initial data to start your simulation from. And we can't just evaluate some function because we don't know what the space-time is at an arbitrary time. That's why we're doing the simulation in the first place. So typically we'll take an initial guess, perhaps the space-time of two black holes, and we just sort of put them next to each other and superpose that space-time. And then because that's not a valid solution that satisfies the constraints of Einstein's equations, we have to solve some elliptic constraint equations to make that be a valid initial solution. So we have a code and development within Spectre to do this, but we can actually, for now, just read in initial data written out by our prior code, spec, and start from that. So that's what we'll be doing here. I've discussed the solving of the PAEs using discontinuous Galerkin, and we couple that with a time stepper to actually do the time integration. So for example, something like Runge-Kutta. And then I had alluded previously to this issue that you need to make sure you don't have the singularities on your grid. So let's say a little bit more about that now. We use a technique called excision, in which you really just cut out the interiors of the black holes from the simulation domain. You probably know that nothing escapes a black hole, and this applies in the simulation as well. So we can cut this region out, and no data was coming out from within that region, so the causality of the simulation is perfectly fine. So the upper panel here is showing what the computational grid looks like in the coordinates in which we're solving the problem. And so you can see these two regions that have been cut out. The problem is that the black holes are orbiting, they're moving around each other. And so we need to constantly shift where these excised regions are so that they line up with where the singularities are to make sure we keep cutting out the singularity. So we're using the same kind of moving mesh prescription that was described in the previous talk. Well, not the Voronoi, but we're moving the mesh. And this requires a little bit of sophistication because as the black holes are orbiting in, they get closer, the orbit accelerates, and the black holes are going to get distorted by the tidal forces on each other. So we have a control system that measures the positions of the shapes of the black holes, updates these maps that rotate the grid, and then from the moving mesh, we add some corrections to the time derivatives. And so this lets the whole thing hang together. This as well is currently in development in Spectre. But Spec uses the exact same approach to handling the singularities by rotating and adjusting the grid. And we can read the moving mesh data from a Spec simulation of two black holes with the same parameters into Spectre, and then just use that. So I'm going to show now a movie of our sort of initial attempt at a binary black hole evolution in Spectre. This is a cut through the equatorial plane, which is colored by the lapse. The lapse is one of the space-time curvature components associated with the rate of flow of time. So what you're seeing here in yellow is the idea that time flows closer if you're closer to the black hole. And I'll just play it now, and you'll see that the black holes go round and round, and the manually excised regions that we're imposing in Spectre are exactly being matched by the dynamics of the black holes, which is a really good confirmation that Spectre is doing the same evolution that our prior code Spec was doing. So now I want to switch gears a little bit and talk about how we're using Charm++, and then a little bit of exploration into load balancing. The different components of a Spectre computation map nicely onto the chars of Charm++. So the elements are represented by a char array, and they're responsible for storing the solution on that little patch of the grid and computing time derivatives, doing time stepping, and sort of really managing the data. And then when we need to do other tasks, typically we will send data to some other chars where they will, for instance, do some data processing. Maybe it's for I/O to make a movie, or we need to interpolate the data to get it on different sets of grid points. We will do this typically on groups and node groups. And then single computations like measuring the position of a particular black hole or computing a gravitational wave as it would be extrapolated all the way to infinity, these we do on singletons. So the elements or the array chars are constantly talking to each other in this nearest neighbor communication pattern to keep the simulation in sync and exchange neighbor information. And then we've got these sort of sends out to other more special chars. So the PDE structure here is imposing causality, which forces the entire evolution to remain roughly synchronized. But for this to be efficient and to not have any idle processors, we really would like to make sure that the load is uniformly balanced across the simulation. And this is going to become much more important in the near future when we start thinking about AMR, local time stepping, and things that could really cause certain particular regions of the simulation to be much more computationally expensive. So we're approaching load balancing here with a couple of sort of naive questions because it's our first go at it. For example, if I have a bad distribution of chars onto nodes, can the load balancer improve it? So to clarify what I mean, say I have a char and all of my neighbors live on a different node of the supercomputer. Every communication I have to do to exchange fluxes and do the time integration of my PDE is going to be a slow communication because it has to go through the network. However, if I have a very good distribution where all of my neighbors are on the same node, so we can have very efficient communication channels. So this might be a good distribution as obtained by a space filling curve. And then I use a load balancer. Will the load balancer preserve my good distribution? And of course, we'll also be thinking about load balancing in the context of inhomogeneous loads in the future. We've got a pretty straightforward implementation. This is sort of our first pass at this, where we've added global synchronizations every n time steps into the code. We call at sync, then we resume time stepping after the load balancer is done. The subtlety here was our array elements have to register with the groups that they send data to, for example, for I/O, because the group needs to know when it's done waiting for data and when it can write the file, for example. And so when we do migrations to load balance and the array is moved off of that processor, we need to make sure the group knows not to keep waiting for data. So we need to add some deregistrations and re-registrations as you move, as you migrate array elements from processor to processor. Here is a very small test showing one way that we were looking at the load balancing results as a function of sort of the initial distribution of processors, of the array chars onto processors. So on the left of this plot, every communication goes to a different node. So every communication is slow. And on the right side of this plot, every communication, or the majority of them, are local. And only very rarely do you have to talk to a different node, which is slow. And you can see that when I use the dummy load balancer, there's a huge spread in the runtimes, a factor of 7 actually, where the case where you've got good locality of the chars is significantly more faster. So what this tells us, communications really are an expensive operation in our code. And then I've also picked out a couple of other load balancers just to show that these are the communication aware ones, and they clearly are converging each of them to some state. where independently of what I gave as my initial distribution, they seem to converge to something. And the one here that's most interesting is this recursive bipartition algorithm that is all the way at the bottom, and which gets to within about 20% of the performance of the manually tuned case. So this is pretty encouraging, especially faced with this sort of huge spread of possible runtimes. But that last 20% may also be worth chasing with something like a space filling curve or aware load balancer. But this is really a tiny problem with 1,000 array elements on 2 nodes. We're trying to understand now what happens if we scale up, and we're seeing some slowdowns that we don't yet quite understand. So the curves here are showing the recursive bipartition load balancer as I go from 2 to 4 to 8 nodes, and it takes more time to do a time step. And we're not quite clear at this point if this is just the expected increase in the computational cost of the load balancer as a result of scaling up the problem. So the graph it's trying to partition is larger. It's not quite clear on the run this short, so we're going to have to test longer runs, whether this might be an issue with the load balancer actually slowing down versus time after repeated upload, whether this might be a performance issue in Spectre that we aren't aware of yet. So we need to benchmark that as well. We've also been looking at checkpoint restarting. From the global synchronization point we had to add for the load balancer implementation, it was quite straightforward to add a start checkpoint function. And the data here on the right shows that in this first example, the restart works perfectly. So the orange curve that starts at time of 3, it just picks up from a checkpoint that was written and has the same evolution as the full run that it's starting from, with deviations varying only at the level of round off, which is actually not unexpected for Spectre because some of our operations depend on the order in which Charm++ messages are received. And so we can't guarantee the bitwise reproducibility. We have to generalize this to work on, for example, restarting on a different number of nodes and other things like this. So going through this, we've come up with, maybe I'll call this a wish list of things that would have been good to know while we were thinking about load balancing and checkpoint restarting, things in particular related to documentation and how it's not always clear which load balancer should be used, or how a load balancer makes its decisions, or how it would scale as you increase the complexity of the problem, as well as some thoughts on the initialization sequence for a checkpoint restart. That last 20% in speed between the recursive bipartition and the manually tuned case is also interesting and makes me wonder whether a load balancer based on a space filling curve might be worth pursuing, though it might need to be made aware of, for example, the connectivity of the domain of the simulation that you're using. And then finally, our checkpointing is writing a number of items to the disk that are really not necessary because they're temporary caches. So a context-aware pupper would actually be quite useful here. So these are just some things to think about. Can come back to this after, but for now I'll summarize. So I've described some of the reasons that we're interested in these simulations of binary mergers. I've said a little bit about what the struggles are for current codes and how we hope to improve on this with Spectre. And then I've shown some preliminary results from a binary black hole evolution and our first sort of stab at Charm++ load balancing. Thank you.
Thanks, Francois. We do have one question from the Google Doc, and that is, what exactly do you mean by rec by part plus dummy? Does that mean you're alternating those balances?
Yeah, good question. So we're using here the feature where you can specify 2 load balancers on the command line, where it would apply the first one, the first invocation, and then it would switch to the second one thereafter. So what this means here is that the first time the load balancer was applied on the left side of the plot, it's using the recursive bipartition. And after that, it's the dummy load balancer. And so this plot here, the comparison between the green and the red curve, so the one at the top and one of these at the bottom, is the difference between applying recursive bipartition many times or applying it just once.
Okay, yeah. Do we have any other questions for Francois? I don't see any others in the chat or the Google Doc.
I had a follow up just from that. So I was going to ask the question originally, but one thing I was also wondering is if you've done anything with graph partitioning load balancers, because you're saying that communication time is really important.
So here, one of these curves is the graph by partitioning, I think. Is that what you're asking?
No.
That's what I'm asking, but I don't think any of these really does that.
What's graph BFT? I don't recognize that.
It's one of the ones that was suggested to me when I typed plus balancer help, and and it sounded promising, so I used it. So yeah, so it's.
Ronak, do you know?
I don't know off the top of my head. It's one that I think is rarely used, so it hasn't been around in a while. But I can look at it. It might do something similar, but the ones I'm talking about are more in the vein of what Metis does.
Oh, we've tried using the Metis ones, and we have found some reproducible, but that we can't understand error messages and seg faults. So we're not quite sure what's going on with the Metis load balancers, but we would definitely be interested in trying to work out what's going on.
Okay, yeah, that's something we'll follow up on with you guys on later.
Yeah, great. Yeah, I mean, any insight into how to best choose and use load balancers would be very helpful, because the initial experiments make it not always clear what the best strategy is.
This seems like an excellent use case for us to use for the load balancing research, and just even to test various things. Is that something that can be made available to us?
The code that we have here?
Yeah, I mean, configuration code, whatever. So we know exactly we can test different load balancing strategies.
Yeah, probably. I mean,
yeah, I mean, that's all on a public fork.
There's-
And to be honest, I don't see why we
Yeah.
probably can also get you accounts on the exact systems, HPC systems that we're running, because they're ones we own.
Okay. In addition to what Ronak mentioned, there is a strategy that Kavita had implemented called Graph Refine that can preserve, like it migrates only among near neighbors. So I want to see what the status of that is, and we'll get back to you.
Oh, that sounds potentially very useful, yes.
Yeah.
Do we have any other questions for Francois?
So I had just a naive load balance question. So the rec bipart, or is that one of the default, or sorry, is that available in the Charm distribution, or did you write that yourself?
Yeah, sorry, I should have said this. All of these are from the Charm++ distribution.
Okay, thank you.
Some of these are compiled not by default, but by adding a different flag. So I don't remember which is which. The recursive bipartition might be one of the fancier ones that you have to enable by compiling every LB or something like this.
Okay, if we don't have any other questions, we'll go to break then. Okay, yeah, not hearing any. Thank you again for the talk, Francois. I think we want to take a quicker break since we're a little bit over. Should we say 5 or 10 minutes, Sanjay?
10 minutes sounds, 5 or 10 minutes sounds fine. 10, let's say.
Okay, 2:55. Let's meet back.
Test my mic here. Looks like that's working. Am I audible?
Yeah, I can hear you.
Great.
Hey, Eric, this is Johannes.
Oh, hi.
How are you? Hey, yeah, so I'm going to do about, what, 12 minutes or so, then you do 12 minutes?
Yeah, that's the basic plan.
Okay, perfect. Thanks. How are you doing?
Yeah, pretty good. We just submitted a bunch of grant proposals yesterday, so that was taxing, but we're past that now. So
Yeah, I'm working on one right now. But it's always something. And by the way, can I be on any of the channels, or do I have to be on a specific one in order to be able to share my screen?
yeah, I think you just need to be promoted to co-host.
Okay. Can you do that? Or Sam?
I've set you as a co-host, so you'll be able to share your screen.
Oh, yeah. Okay, thanks. We're good.
I think we may be able to stay close to schedule so that will actually go off in an hour. We shall see. All right. I think should have completed our 10-minute break. And we're going to resume our sessions with a talk on quantum chemistry from a longstanding collaborator of ours, Dr. Glenn Martina from the Pimpernel Science, on projected augmented wave-based Kohn-Sham density functional theory in open atom with n² log n scaling. Thank you, Glenn. Go ahead and begin when you're ready. I'm not currently hearing you if you're speaking.
Can you hear me now?
Yes, yes.
And you can see the screen?
Yes.
All right. Thank you for inviting me, guys. I'm going to talk about a long-term collaboration with Sanjay and Eric and the guys, in particular, a former postdoc of theirs and a former postdoc of mine, Raga and Chi and Eric. Okay, so the goal of our collaboration is the study of complex heterogeneous systems with the goal of discerning new and emergent physics and creating impact in the field. So we've done things to invent new transistors that are based on pressure switching. We've looked at antimicrobial peptides and how to design them. We've looked at DNA sequencing and solid-state nanopores. And we've looked at advancing the technology in solar cells. Our approach is basically coupling hardware, software, and new methodology coupled to physics-based solutions for complex systems. Pretty much like all the talks we've heard, there's this melange of opportunities that this synthesis creates. So we have a code called Open Atom, where the key for us is not to do small systems that we minimize, but to do large systems where we are worried about atoms and molecules moving at finite temperature in complex environments to understand the physics. So if you think about an antimicrobial peptide near a membrane, it's not a single configuration that matters. It's fluctuating. How it interacts with the membrane or enters the membrane is highly fluxional. If we think about pollutants, we need to worry about linking a dye molecule to the pollutant, worrying about what the spectra is, and that will require some new capabilities in Open Atom. And if we want to understand chemical reactions in dense arrays, for example, to understand failure modes, then in novel solar cell materials, we need to. So this will be done by Open Atom, as I said. So it's a long collaboration between myself, Sanjay, and more recently, Sarab Ismail Begay. And we built electronic ground state and excited state parallel software and methods to take these configurations that the code generates and also calculate spectroscopy. So without any one of the underpinnings, we're in more trouble. So we do have a long-standing collaboration. So we have lots of what I would say exciting results. We've taken a rather large system, a metal organic framework, and we've scaled it on BlueGeneQ. We've taken, again, a rather large aqueous system on BlueGeneQ and scaled that down with markedly improved performance compared to other people. So again, that's electronic structure, atoms moving on the electronic ground state, and we can do it faster than other people. We've also done some methods development to reduce the scaling of things like exact exchange. And I'll tell you about our new projector augmented wave to allow us to study metallic systems. The electronics excited state work, which is led by Sarab, you'll hear about next. We've done a highly scalable calculation on, again, Blue Gene. That's led by his group, where we achieve much higher scaling compared to other people. And we've also recently developed an N cubed method, where N is the number of electrons in the system. And that paper just came out in this year on the method, and the parallelization will be presented next. So, and that software will be released, and you'll hear all about that next. So when we talk about solving electronic structure in physics, one of the big workhorses is Cohen-Sham density functional theory. And Cohen and Sham were two famous gentlemen. Cohen won the Nobel Prize, though he's a physicist. He won it in chemistry. And what he showed was an existence proof, is that if we have the electron density, we can in fact find the electronic energy, and the ground state energy is simply the functional minimization of the kinetic energy of non-interacting electrons, the electron-electron interaction, the external potential, and the sins, which take into account the fact that electrons are fermions, so we have exchange, and correlation basically corrects the self-interaction in one of the first terms, and the fact that we use the formula for non-interacting electrons. We typically, in our code, we have an exchange correlation function, which is where all the sins are hidden. That depends on the density and its gradient. So it is an approximation because Cohen gave us an existing proof. What we use in our code is a plane wave basis set. And what's great about plane waves is they're everywhere, and they're pretty unbiased as to the position. They're unbiased as to the position of the atoms. However, since they don't know about the atoms, this approximation can cause difficulties. Nonetheless, what we've able to do is take every single routine except orthogonalization and get it to scale as n squared log n or better, using Euler exponential spline interpolation, which I'll explain. N is the number of electrons. So it's highly parallelizable, as we discussed before, under Charm++, and we have lots of capabilities to move the atoms around under the forces produced by this ground state approximation, and we can also treat spin. So the disadvantages I hinted at is that because it doesn't really know, plane waves really don't know about the atoms. They're simply delocalized waves in which we expand the electronic state. You require a very, very large basis and very large memory. And if I have atoms with cores around them, say iron or nickel or copper, you need an intractable number of basis functions. So what we've used the code for very successfully is first row, second row elements that don't have giant cores. So if we want to move on and study more metallic and complex systems, we need to do better. So in the 90s, Peter Blüchel wrote down a projection operator based approach, where what he tried to do is introduce the core, and we'll talk about that in detail. So we split the states into a localized piece, which is new, and a delocalized piece, which we treat with plane waves. So because we now have a core, we can do NMR and linear response theories that require the core easily. And it reduces the memory requirement because we have an explicit treatment of the cores. So what we had to do, as we did for the plane wave code, is get all the methods except for orthogonality down to n cubed, down from n cubed to n squared log n, improve the parallelization, and improve the accuracy. And we'd like to implement that in OpenAtom. So as I said, Blukhal's genius here was to take the electronic states and divide it into two parts. The smooth part, which is the plane wave part, and some core part, which really does know about the atoms. And the core really only lives in a small region of space around the atoms, and these regions don't overlap. So here's your plane wave part. We expand this smooth part in plane waves. It lives everywhere, even inside the cores. And then we have a projection operator based approach, which preserves the rotational invariance of the wave function, which is a fundamental property. So it's related to the overlap of the projector with the wave function. And what it effectively does is it switches out the soft plane wave core with a real core here, but through a subtraction, which is why this projector is written as a difference. So what you end up with is Jello and fruit. So you have state I, he's in atom 1, state J, that's for atom 2, and so on. And then you have the smooth part that lives throughout the box. So that is a big improvement because we have an explicit representation of the core while keeping the joys of plane waves in their very nice unbiased convergence. And we preserve through the construction the basic properties of the wave function. So what we have is a functional that looks like the non-interacting electron kinetic energy, which is just del squared on these states. We have the Hartree term, which is the interaction of the density exchange correlation and some external interaction, which here we just write as Coulomb's law. So all these terms will now have three parts. We'll have a smooth part, a part that only depends on the stuff in the core, and a part that depends on the interaction between the smooth part and the core part. And that's true for all these things. So we have a smooth exchange correlation function and then an exchange correlation function which depends on things in the core. So what we have is a mixed basis set with a delocalized piece and a localized piece. So in some sense, it's a natural multigridding. That said, there's no truncation scale for the long-range interactions. If you notice these sums, they go over all the periodic images. And 1 over R, that never can go away. You need to choose a boundary condition and do things properly. So we use two tricks, two things from mathematics. An algebraic identity from Ewald, where 1 over R is equal to the ERF over R plus the complementary error function. This splits these terms with Coulomb's law into two parts, a long-range part and a short-range part. We can take the long-range part into reciprocal space, and all these terms can now be evaluated with error control based on one parameter alpha, which is simply the splitting of 1 over R into a long-range bit and a short-range bit. So this was left out of Blukhal's original formalism, and you didn't have the accuracy control you would really like. So how does this work? We have a long-range cutoff and a short-range cutoff. There's a relationship between them. And if I look at a plane wave cutoff and what kind of distance I need to compute the short range interaction, I can get very, very high accuracy with a very small plane wave cutoff. Now this is only useful because in effect, what we've done is we have an explicit representation of the core where I can do all these core integrals with a very small cutoff. So there's a cutoff for the plane waves to understand details of the wave function, which we've truncated, which we now have core parts, so it doesn't need to be as big, and we have accuracy control. So that's a beautiful new feature that we've added to PAW, which really helps the cause. And it's important that both the cutoff radius and this G-space cutoff are relatively small. So there are two tricks you need to understand plane waves. So the first is that we work with a finite cutoff, and therefore we have a discrete variable representation. And what that means, if I want the Fourier coefficients of the second power of a function in real space, I can just take the number of points equally spaced. I could square the function, take the FFT, and that gives me the exact result. I can also go back and forth between real space and G space with FFTs exactly because my basis is finite. So that's called the discrete variable representation, and that's been known forever for plane waves. Everyone uses it. The more new wrinkle is not really new, but it's by Euler. And what Euler said is if I have a plane wave evaluated at a point S, which is not a grid point, I can express it as an interpolation from the equally spaced grid with a controllable error. So this will allow us to do things like take our plane wave and put it into a little sphere of points around each atom with a controlled error. We'll also be able to calculate our overlap integrals, which require the positions of the atoms, which define the coefficients of expansion of the core parts with high accuracy. And because we're using FFTs, we can do them in reduced order. Now, this is going to be a multi-grid problem. We have a grid to do Euler exponential spline to calculate overlaps. That's one grid. To compute the density as for per point one, which is the square of the wave functions, the sum of the squares, we need a density for that. And to calculate the Coulomb interactions in n squared log n, we need a density Euler exponential spline. And we have those first three grids in open atom. We need one more for the discrete spherical polar grid around each atom, which is all new. And it's all going to be computed with Euler exponential splines. So once you've done that, and you've done 100 pages of LaTeX to get all the derivatives and everything else, you can compute everything in n squared log n, all these complicated terms. So what we need is we take the Fourier coefficients of our wave functions, we just multiply them by this d function of Euler. We go back into real space, and this can be used to interpolate the wave function at any point in space. We can do the same thing with our density. We start with our states, put them in real space, we can square them. We can calculate the density and get Fourier coefficients exactly, as we discussed before, in G space, due to the fact that we're working with a DVR. And if I want to do Euler exponential spline interpolation for this, we can equally well do that in order to calculate Coulombic interactions in n log n once we've computed the density in n squared log n. So this EES is really provided a key, and it's part of the speed and parallelism of open atom. So if I want to calculate my my wave function on a little grid, fine grid inside the core of the atoms, I take the density that I've defined, multiplied by the d factor. I divide it into n little bits, where n is the number of atoms. Okay, I can do the same thing for if I want the density inside the little cores of the atoms, and then I can simply do a B-spline interpolation. So these End partition operations are now part of the CHARM FFT world. There's still some cleanup work to put in periodic boundary conditions right. But I can produce the wave functions and the electron density very efficiently on a very fine grid inside the atom cores, so that I don't need so many plane waves to describe my system. So in order to implement this, I need to do all these things. I need to create the KS states in real space. That's done. We create the smooth density in real space. We've done that. Just part of normal DFT. Create the smooth density around the ion cores. We know how to do that. That's new. Create the smooth Z matrix. That's already in the code. Create these core densities, which I'll explain to you. So again, we've derived these things. It's a big bunch of derivations, but many of the software packages that we've heard about today are in fact going to require, underneath the hood of the nice bullet points everyone shows, is quite a lot of applied math. So let's just review getting the smooth density. So I take my density in G space, I multiply it by the D factor, IFFT into real space. I do an end partition, so I get the number of the points I need to do the interpolation on the grid, only those little squares, and I do the B-spline interpolation, and I can get the smooth density around inside all the ion cores on a very fine grid. And that simplifies matters greatly, and the computational complexity is n squared log n. So we can also create these Z matrix elements, these overlaps. So we take the D function, multiply it by the projector, FFT into real space, do a B-spline interpolation, and then we have the smooth Z matrix for ion type. So again, it's an n square log n operation. There can be many different types of atoms in many channels, and we can handle that. So once we have that, we can construct the core density inside of the ions. So we can create this guy, which is simply the core-core interaction, which is going to take these Z matrix elements, square them, multiply them on the fine grid by the difference projector, and that creates the core-core part of our interaction. So if this sounds like there are many terms, there are, and there's even more derivative terms. However, we can do them. So the core density inside the atom, again, it's the same thing. We take our G space, we multiply by our D factor, we go into real space. We get the weighted sum around the atoms. And that gives us what we need, this thing we call core 1 on the atoms. And again, because it uses FFTs, and we can effectively construct everything in order n squared log n. So we have made progress. We have char arrays defined, communications patterns established, and we have the beginnings of the FFT library that we need. We have the flow chart for the energies and the forces, which, if you notice, every term splits into 3 parts. And then with the long range, short range, that takes those 3 parts and splits them into 2 more. And then the forces give you a whole bunch of terms. So we've done some modeling outside of OpenAtom to test the fine grid spacing, the Coulomb clutches, alleviating Coulomb cusp conditions, convergence with real space cutoff, which is complete. And again, this CHARM FFT library is being expanded. So we're ready to begin integration into OpenAtom, maybe with new funding. So what could we do? Yep, this is the last slide. I see you. So if we look at a perovskite solar cell, it has lead in it. Lead is a heavy atom. And what's exciting about them is they reach the solar cell efficiency of silicon, but it's a much cheaper material. So it's high efficiency, low cost, but there are problems: instability with air and water, with light, with interfaces, with toxin, and there's toxic compounds like lead. So people are trying to handle all these things, and simulations can help. And we'd like to get into that game. So given we can handle heavier atoms, we can understand the mechanism, we can search for non-toxic high-performance materials and design new interfaces with longer lifetimes. Okay, so that's my conclusions. I'll let you read that, and I'll take any questions if I have time.
Thank you, Glenn.
Virtual clapping.
Didn't see any questions in the Google Doc.
Maybe there's a point, since you're involved, Eric, maybe there's a point you want to emphasize about the computer science.
And so on the computer science side, it's helped us to develop some additional communication patterns in CHARM to manage this essentially grid-to-grid communication patterns for subsections of the computation, which we haven't quite formalized to general schemes, but have been implemented in the application. Oh, we have a question from Nils. Goal is to study solar cell materials without having to build them.
So these solar cells exist. So let me see if I can go back. So these perovskite solar cells really do exist. So there's problems in manufacturing, which I don't think we can help with, but there are. But there are also problems with degradation with time and light, and degradation with water. And you'd like to play around with the structures and coatings to try and prevent that damage. And then it would be cheap and low cost. So the problem with solar cells is getting a manufacturable material that will last a long time, 25 years, I think is what you need at low cost, so that it can replace at least some of our electrical capability. You know, light, it depends on the time. It depends on, if you live in Alaska, there are times when you see no sun. If you live in an area with lots of rain, you don't see the sun. But it could be, in effect, a big improvement.
Okay, yeah, so I know very, very little about sort of the details of the state of the solar cell field. So I guess the big problem right now is still that the return on investment is takes roughly the length of the lifetime of the solar cells, and so it's sort of quote not profitable enough. Is that trying to?
Yeah, it's cost.
Okay.
People have developed better materials as this, which were in principle cheaper, but then they have problems like silicon. People know what to do, but it's simply too expensive.
Right.
So it becomes
Okay,
a cost problem. It's not like they don't work. They in space. You just use silicon solar cells and you're a happy man, because the cost of the launch to get the thing in space is much more expensive than the solar cell. So
Right. Once you have a rocket involved, everything else is
everything else is some change, right? But if you want to have them on every house, and you don't want it heavily government subsidized, you have to bring down the cost.
Right, right, and the government subsidy at least is maybe an initial thing, but it's not long-term economically viable. Okay, right.
Yeah, I mean, that's always the fight, you know. If the government has infinite money, all things would be possible.
Right, right, right. Okay, and so basically here you're saying the sort of the takeaway is trying to leverage Charm++, the scalability, parallelization, and use that then to sort of try to tweak some of these solar cell designs to get some idea of, before you start trying to do everything in a lab, which presumably is not cheap to build all of the different tweaks and variants, you can get some idea of what is worth investigating by using these computer simulations.
Yeah, if you will, it's a kind of discovery project. And maybe you can find a mechanism that's general enough. In other words, you can find some physics. Oh, this thing goes like that, and therefore if I sort of design something like that, it'll be better.
Okay. All right, cool. Thank you very much.
No, thank you for asking.
All right. So any further questions we should table for the next break, so we can move to the next talk by one of our students and one of Dr. Beiji's. So Kabitha Chandrasekhar and Kayahan Saritis will describe the current state of the scalable GPU software for excited electrons using OpenAtom.
Yeah, I think I'm going next. So like, should I share my screen now?
Yeah, yes, please.
Okay.
Okay, seeing your screen.
Yeah.
And your presentation. All right. No, over to you.
Yeah, good. How are you? So should I start now, or like, is there a couple minutes break?
There is no break.
Okay. Yeah, sorry.
Begin as you
hi, yeah, this is Kayahan Saritas. I'm from like Yale University, working as a postdoc in Saurabh's group. So like, these are also the list of other like our collaborators. I will be giving some introduction and basically talking about the like method and the physics, and I will leave it to Kavita, like who is the person that did the heavy load on the like the Charm++ implementation. So as like Glenn talked about a bit, like this, the electronic structure calculations. So our aim in here is to calculate or perform simulations of ions and electrons at the atomic level using quantum mechanics. So hence the Schrödinger equation. So this is inherently a many-body system. It's a many-body problem, but we assume that the ions like are too slow, and then they're assumed to be frozen. So basically, you are interested in like the interactions between multiple electrons. So this is a very hard problem, like to solve it exactly. So that's why we use approximations. And as Glenn mentioned, the DFT is a popular approximation for this to simulate the electron-electron interactions, which basically turns this problem into a one-body problem. That like what you're doing here is basically showing all these like electron-electron interactions into this VXC, which is the exchange correlation term in here. And so this basically becomes an eigenvalue problem that where you solve for the epsilon j's, which are the eigenvalues, and the psi j's are the eigenvectors of this differential equation. So there are various methods that you can use to get the same result, like to perform electronic structure calculations, but all of them come with different accuracies and speeds and scalings. So the exact like Schrödinger equation is like is an NP-hard problem. But the DFT method that we use is that has been used in the field routinely can simulate systems that are like hundreds of atoms. But the GW method, which I will be talking more on, like is able to simulate systems that are tens of atoms basically. So this is like the scale of the systems that you can simulate using these two methods. So although both of the methods have like similar scalings, the prefactors for these scalings are considerably different. And so being able to simulate like hundreds of atoms with density functional theory makes it quite attractive, like in the materials science field to be used it basically hundreds or thousands like different groups in the world. So, but there's one drawback with the density functional theory, and it is coming from the exchange correlation functional, which is used to simulate the electron-electron interactions. So the Kohn-Sham theorem that Glenn talked about is an exact theory with the condition that if you have the exact exchange correlation function. But if you don't know what the exact exchange correlation function should be, then there are basically plethora of different approximations which may look like alien language to like people outside the field. So, I mean, basically, if you're trying to simulate a brand new material where there is no experiments, then you have to like cross your fingers to hope that like your results should be like good enough. Like the only thing that you can hope for is like the relative energies or like the qualitative like agreement between like different things that you're interested. So this what we are interested in the electronic structure calculation side is to get the right band gap. So the band gap that, so we can define the band gap in this following way, because the band gap is essentially important for the optical properties of a material. So once you have the density functional theory expression like this and you solve for the epsilon j's and psi j's, basically the eigenstates, as we call it, are put into this like ascending order, and then the electrons start populating those states. And once you reach this, the highest energy electron, and then if your system is insulating, then there's a separation between this epsilon n1 and epsilon n states, where like in this region you no electrons are allowed to exist. So this defines your band gap. So basically, once you have an electron in here and you want to move this electron across the lattice, so that like you want that electron to conduct basically. So you need to excite this electron to this conduction band so that you can, for example, like use it as a solar cell that can help you like move electrons from one place to another so that you can generate useful like work from a material like this. But the problem about the density functional theory is like coming from this issue, which is the derivative discontinuity. So the gap, so you can define the gap as the del E, which is the total energy versus the density. So this is the exact physics of this term is telling you that this should be only piecewise continuous, like you can see in the red curve in here. But the DFT is often giving you this green curve, which is the local density approximation, as like one of the approximations in DFT, that you're always kind of underestimating this, the E gap value in here. So that's why you need to use a method that can give you band gaps more accurately and more like reliable way. So we mentioned about this band gap, but why is this important? essentially this will tell you whether the material that you are interested in is metallic, semiconducting, or insulating. So you can do more fancy things about like getting the light matter interactions. And this also has a lot of engineering implications, being on the side of photovoltaics, lasers, or like luminescence of the materials. And if you look at the band gaps of these 4 different materials using different methods and comparing those to experiments, basically what we are seeing again is that the DFT usually underestimates the band gap, but the GW is usually in a good agreement with the experimental values in here. But what are the challenges for the GW method? So it's memory intensive as a method, that it requires a lot of empty conduction bands, much larger than what you need for the density functional theory. So by that, it requires large and dense matrix multiplications, and the method itself, the naive implementation of the method requires order n-to-4 scaling, which is unfavorable compared to the n-cube scaling of DFT. So what we want from here is the efficient and scalable GW software, and hopefully get it to like n-cube scaling so that we can be able to work with much larger systems in size, which were previously inaccessible to the GW method. So what are the main elements of GW method, and like what are the most expensive steps is, so we can summarize it using this diagram, but the main thing that we want to get is the inverse dielectric matrix, which is epsilon inverse in here. So from here, you can get the screened Coulomb interaction, and then you can get the dynamic self energy or like static self energy, depending on whether your energies are frequency dependent or not, so that these self energies can be used to determine the band gap of your material. But the most expensive part of a GW calculation is getting the polarizability matrix. So this can either be done in the G space or in the R space. That what we do in the, like practically people do in the field is that they typically get the energies and the wave functions from like, or you could say eigenvalues and the eigenvectors from DFT, which are often in the G space. Then you can convert this to R space using FFTs, which have this kind of scaling. And within the R space, you can calculate the polarizability matrix and then convert it back to G space using inverse FFTs. So why you have this like additional step of going FFTs and inverse FFTs is that what we find is that when you want to calculate the inverse dielectric matrix, so it can converge much faster, like using even decent small real space grids, so that it significantly saves on the costs by a factor of 2 in terms of the grid spaces. So there's that's why like this additional step is involved, but still you need to perform a lot of FFTs to get the wave functions in the R grid. So let's go back, and so we are saying here that the polarizability matrix is calculated with an order n⁴. But what can we do in order to reduce this order n⁴ to n³ so that we can achieve better scaling? So what we can see in here, the operations here are basically matrix multiplications. And here what we can see is that in the polarizability, there is this term in the denominator, which is EC minus EV, which are the conduction and valence band energies. So these two terms are like together with the numerator. So what you want to achieve is that if you can come up with a form that is separable, so that this EC and EV are like can be like separated from this expression, then you can relieve you can be relieved from this quadratic interaction between those two terms and then make it more into like the addition between the unoccupied and like occupied levels. So such that the main idea is finding a way to express this denominator in the separable form such that this like quadratic term is reduced to a linear term. So what we do in that end, for that end, is to use the Laplace transform, and by using the Laplace transform on this denominator, we get the EC and EV in the exponential terms, then which can be separated using this form. And this, the integral for calculating this term can also be discretized using the Gauss-Laguerre quadrature, basically where like you have the function as a like positions of the nodes and the weights of all the like nodes that you're interested in the Gauss-Laguerre quadrature. So in the final term, you get the n-cube scaling, but you also have this nq term in front. But we are going to show in a bit that this nq is system independent, so it only comes as a prefactor to the n-cube scaling. So rewriting the expressions in the previous page in here, we can see that we can achieve this separable form, that the valence and conduction band like calculations are obtained in this in this way. But what we see here is that a large number of NQ is needed to accurately integrate over the wide time domain made by the EVs and ECs in here. So what we can use for that end to use windows over ECs and EVs so that we can minimize the range of the time domain, which is defined by the gap for that window and the bandwidth of that window. So the scaling between those two becomes closer to each other so that the range of the time domain is reduced for every individual window that you're interested in. So the final step of getting the GW energies also involves getting the self energies, and for the dynamic self energy, the expression in here that we have is quite similar to the polarizability, although some of the terms in the denominator are different. But we have mentioned that the separable form of the denominator is possible as long as you have an expression in this form, so that the same methods that we explained for the polarizability is also applicable for the dynamic self-energy. But what we are seeing for this case, because of the presence of this frequency and the energies in here, what we know that this denominator can often or occasionally can be zero, so that it requires a better treatment to be able to use it with the Gauss-Laguerre quadrature that we defined. So for that end, our group has developed a Hermite Gauss-Laguerre quadrature, which is similar to the Gauss-Laguerre quadrature, but has a different weighting function so that it is better behaved around zero. So the final results that we have in here are for the gaps of silicon and magnesium oxide. So we have studied systems that are of the modest systems with 16 atoms. And the comparison that we do in here is the in-house versions of the n-cube and the n⁴ codes. So we are seeing that the performance of the n-cube code depends on the accuracy of the quadrature. So the more points that you use in the quadrature, more accurately you calculate the integral. So that's why we are seeing multiple values for the band gap in here. And depending on how close you get to the n⁴ result, the ratio of the computation, basically you are using more quadrature points, and then your requirements for the calculation is increasing. But if you can be more relaxed about the accuracy that you want, you can basically perform the same calculation with a much reduced cost, basically. So the similar results are obtained for both of the systems, that the performance improvement is close to order order n, but much better performance is obtained using windowing, which is the red lines in here, that requires much smaller, like quadrature grids. And comparing the R code to the existing and to the fork codes in the literature, what we see here is the Yamba code, which uses Terminator. Basically, this is a method to like eliminate the number of conduction bands, but while still being accurate, like relatively accurate, but this is still essentially order n to the fourth code. So what we see in here is that the performance of our code compared to that code is again nearly order n, considering the size of the system that we are interested. So the code is available like in this address that is getting like routine updates. And with that, I wanted to leave to Kavita to give more updates on the the OpenAtom implementations in the code.
Thank you.
So I'll just continue from Kaihan's presentation and talk about the OpenAtom GW p-matrix and cube method computation that we recently implemented and the parallel scaling results for the same. I'm a PhD student, Kavita Chandrasekhar, at UIUC, and this work is done with collaboration with the OpenAtom team. We have been working on the GWPSC parallelization for a bit now, and the primary computationally expensive phase is the p-matrix computation in R space that we had previously done in NPAR4 method, and now we have an NCube method implementation, which is also complete in parallel. We also have other steps in the GW computation, which are smaller in terms of computation. They include the FFT-UFP, integer space, inversion of the epsilon matrix, plasma and pole calculation, self-energy calculations. I'll primarily be speaking about the NCube method in parallel. The overall gist, we start with the Charm++ implementation for p-matrix computation. Both the NPAR4 and NCube method have a similar layout of the char arrays. We have the state vectors, which consist of both the occupied and the unoccupied state vectors, which are 1D char arrays, and then we have the p-matrix, which is a 2D decomposed char array, and the data is also 2D decomposed into tiles. So in terms of the input state vectors, it's a very straightforward implementation in terms of how the occupied and unoccupied states are stored in nodes. We currently have a node group which caches the occupied and unoccupied states as needed. So currently all the occupied and unoccupied states are broadcast to all the nodes, and only portions of the state vectors are used in the computation. So the computation of p-matrix itself consists of primarily row and row bar matrix when it comes to the NCube methodology. It uses a windowing technique, as Kaihan mentioned, which are smaller portions of the computation. So there's the outer loops that you can see in the pseudocode here, which consists of windows of occupied and unoccupied states. So primarily, the most computationally expensive part is computation of the row and row bar matrices. And then P matrix itself, as we can see, is formed by the element-wise multiply of the row and row bar matrix. So move on to the pseudocode for the computation of the row matrix. Primarily, it is done with the input occupied states. So we represent occupied states and unoccupied states with psi vectors. The number of occupied states is smaller, and we represent it here by L. So the total number of occupied states can be represented with a matrix or a 2D array of L cross N elements. So row matrix itself is computed by adding the elements of outer product of the occupied states. This is what we can see on the left side. So we have an outer loop consisting of all the occupied states, which is represented by L, and the row matrix is computed by the summation of the outer product of each of the occupied state vectors. So we can represent the same computation with a ZGEM, as you can see on the right side. So primarily, row matrix is nothing but a matrix multiply of L cross N occupied states with the with another matrix L cross N transpose of the same set of occupied states. The computation of row bar is the next part of the computation. It's more expensive primarily because of the number of unoccupied states M, which is much greater than the number of occupied states. So this is essentially again the sum of outer product of the occupied states, and pretty much translates to a ZGEM call of an M cross N and N cross M matrix of the unoccupied states, represented as row bar. Just a general pictorial representation of what I just mentioned. Right now, the occupied states are primarily L cross N and N cross L by transposing it, and that's what we can see on the left side. This is a tiled implementation of P matrix. So we only have on each char, we'll only have portions of occupied states that are read in, and only portions of the row matrix that are computed. Similarly, we have tiled representation of the row bar matrix, which is computed with unoccupied states. Again, only portions of the unoccupied states are used in this computation. But the overall size of the unoccupied state matrix multiply would be an N cross M into an M cross N matrix, resulting in an N cross N matrix of row bar. So finally, we have the output of N cross N matrices for row matrix and row bar matrix, and we perform an element-wise multiply of the two matrices to obtain the final P matrix. So in terms of performance of this method, we find that as expected, N-cube is much faster than N power 4. And at the very least, we find that it's an order faster for the medium-sized data set that we use silicon 1 at 8 atoms. The output here for the N cross N is 20K cross 20K matrix. We find that it scales well on both Intel KNL and Intel Skylake nodes on Stampede2, and in both cases, it's much faster, an order faster than the N power 4 method that we had previously computed. Our future goals here are to find the scaling for larger data sets as well, primarily the Silicon 432 atoms data set. I think any questions?
Thank you. So I'll take some questions here for either section of the talk. Because I want to have you had a chance to look at the weak scaling behavior.
So we're yet to do weak scaling. We're primarily looking to generate some data sets that we can use for weak scaling as well. But my guess would be that it would have good weak scaling, given the strong scaling also is pretty good.
Yeah, it's pretty good results. So the schedule doesn't give us a break before the next session. Is there a general desire for a break? We can include one or transition immediately to the next session.
Well, not sure, but I think if we take I think at least we should take a short break. And if you want to take a long break, that will be justified, or that will be good to do if we're going to have some side room meetings or something like that. Does anyone want to say anything about that in the chat, or just speak up? Otherwise, let Eric decide, I guess. Our option being we end early or we, but I think there might be some confusion too about people who are joining just for one talk. So
I think maybe we could keep to the schedule unless people feel compelled to have a break. It's not crazy to go that long without a break. Yeah, so I suggest we transition to the next session.
a short bio break, and then we.
Oh, you want a short bio break? All right, so let's call it 3 minutes. So 2 minutes. So 4 o'clock.
Okay, we'll do.
All right, it's just after 4. Let's continue with the final session for today. The topic of the session is adaptive MPI and parallel tasks. And the first presentation will be given by Johannes Westerink and Eric Bohm from Notre Dame University and the University of Illinois, respectively. And the title of their presentation is Hurricane Storm Surge Analysis and Prediction using AdCirc-CG and AMPI.
Everybody hear me? And
Yes.
do you see my screen?
We can, yes.
Okay, perfect. All right, so just I'm just going to give a little bit of an overview, and then Eric is going to take over with some of the implementation details that we've been going through. So essentially, this is coastal ocean modeling work. The models that we're working on are used by FEMA as well as NOAA for forecasting systems and by the Army Corps of Engineers. And by the way, all the people in green are currently working on this particular implementation. So it's a collaboration between Illinois, Notre Dame, UT Austin, and Ohio State. So the kinds of problems that this class of models looks at is predominantly coastal flooding, but also wave forces, inundation of sinking deltas, wetland degradation, fisheries, and even things like oyster and other larval transports. So here we see the general spectral energy content of the ocean. And there's actually quite a bit of energy in this long wave, what are considered long wave zones, and quite a bit of energy in the short wave or wind wave zone. And this is not really resolvable on any kind of large scale. So we tend to use energy transport models versus we use derivatives of Navier-Stokes equations for this range of energy here. So these are really coupled together through 2 different classes of models. And the one that we're predominantly working on in this project is AdCirc. And then there's a wave energy model called SWAN. And
we're still on the title slide.
Oh, am I?
The share hasn't moved past the title slide.
Really? Let me try again. That makes it a lot more boring talk. How about now?
That worked. Okay.
I guess it was trickery. I have multiple screens, so I moved it so that it would be a little bit easier to present. So anyway, this is the spectral energy in the ocean that I was talking about. So you have the long wave over in here and the short wave. Are we now on evolution of coastal ocean hydrodynamic models, the recent past?
Yes.
Okay, perfect, thanks. Anyway, so we're coupling 2 models here. These go back and forth. I'll talk a little bit about that. And they get a one-way connectivity with a global atmospheric model and giving us winds and atmospheric pressure. And AdCirc in itself uses METIS-based domain decomposition with a halo overlap. We have very large domains with it. And most of the resolution is actually overland. So that's reflected in this static load balanced depiction of the domain decomposition. So these all get assigned to their own core and they communicate at the interfaces. Again, the larger domains here are in open waters. And when you get to the smaller domains, the smaller decompositions, i.e., which balance the number of computational points there, they're overland. And this gives a little bit of a motivation of the work. So the bottom line is a lot of this remains in the classic implementations that we've traditionally done. This remains dry. So obviously rebalancing the load is pretty critical, and that's why we're using AMPI. In of itself, the code is quite scalable. Here you see some different examples on different systems. This is the past, and this is using some of the older systems. In terms of scaling, we scale up to about 30,000 cores, and of course it's weak scaling. So the bigger the problem, the better it scales. So this is a typical domain, just to give a little bit of background. This is the US East Coast, Gulf of Mexico coast, Florida, etc. And you use a big chunk of ocean like that, but you pile a lot of resolution on in the nearshore areas. So if we were to zoom in on one of those areas of interest, this would be, for example, Mississippi River Delta with New Orleans in the background there. And this is the representation in the unstructured mesh model. So you have enormous detail of the geometric complexity as well as the hydrodynamic features of the model. That's represented, of course, by using very targeted high resolution and pretty sophisticated meshing methodologies to capture that. A typical simulation goes like this. You have the winds over here, hurricane winds, for example, and this is used predominantly for hurricane modeling and big storm modeling. You have the waves over here up to 10 meters, and then you have the storm surge piling up within the geometrically complex system. And that's how the model is used. Now, moving forward, what's the future and what are we working on just after that background? So what we're going for in our collaboration that we're talking about today is really being able to rebalance the physics as well as being able to rebalance the computational load. And of course, those two are intertwined. Down the road, we want dynamic, and we've been working on this for quite some time, dynamic mesh resolution, as well as to choose from a variety of order of interpolants in more advanced finite element implementations, such as discontinuous Galerkin. So we really want to develop these frameworks that allow for dynamic and coupled physics and have the much more sophisticated load balancing as compared to the current implementations of the model. So the multi-physics really comes into coupling not only the long wave circulation model that I talked about before, as well as the waves. This is a little bit different wave model, and have that coupling coupled to the atmospheric model, weather model. But we also want to pull in global ocean circulation models, sea ice models, and hydrology models as the first order, and we've been working quite a bit on this. So just for example, the background ocean climatology, which you see over in here, this is surface water elevations as they would be observed from a satellite, but here computed by ATCIRC. It looks something like this. The reds are higher water levels, and the blues are lower water levels. And there's quite a bit of variability there, 3 meters. So it turns out that, for example, the water along the East Coast is 1 meter lower than further into the Atlantic due to the current systems and how Coriolis interacts with those. And so a visualization of the East Coast of the United States looks like that. And you can see that higher water pop up, but you can also see the ephemeral nature of the many eddies and complexities in the ocean. So the current system, for example, that we were seeing over there is the Gulf Stream, as well as the loop current. And you have many of these systems around the world. And here it's visualized. And that, of course, impacts water levels as well. So this is bringing in more physics into the system. If you were to look at comparisons to mean water levels averaged over a running 30-day average, you would see that these systems which have the coupling in red match the measured quantities in black much better than the uncoupled systems in blue. So basically the coupling of the physics leads to better results in terms of predictability of the models. The spectral content is also significantly better in this example over here. If we were to look at this picture here, where you have a spectral between the year range and about the 5-minute range, spectral energy density of the system. So now the next step is really to pull in physics into the ATCIRC framework itself, not the coupled models that are running simultaneously, but within the core of ATCIRC. And the main thing that we're working on is to change the hydrologic components that couple in with larger scale hydrology, i.e. the rainfall runoff. And that is with these two sets of equations that are essentially simplifications of the shallow water equations that are typically run much cheaper and much better for the hydrology. So the idea here is that you can pick clusters of elements that run more complex physics, a simpler set of physics, and an even yet simpler set of physics, and have the boundary of where that physics gets applied change depending on the hydrodynamics. So the simplest example of that would be, for example, here. And you see that there's dry land over in here that's depicted. The light blue are the wet areas, and then the green and white areas are dry areas. And so there's basically no computations in the current implementation being done. So this would beg for, again, rebalancing. And a very simple example is over here, where again, you have a much higher resolution on land than in the ocean. The line being the beach that separates things, and water going up and down, past and forward and backward of that line. So a much better decomposition is this, and then the one to the right, and it needs to be dynamic. And so we have seen with Zoltan improvements in efficiency that way, and we're working now to implement AMPI. So an example of where this is all going is here, and you see the incredible complexity of the very dendritic network of channels, depending how well you resolve them, 30 or 120 meters for NOAA's operational models, really determines how much resolution you have on that coastal floodplain. So this, again, these are dendritic channel systems penetrating the floodplain. And so you have the ocean side, the land side with a lot of nodes, and a lot of those nodes are either going to have hydrology, which is much cheaper to run, applied to them, or are simply dry and don't need anything. So that's what we're working on. And so instead of having this very simplistic one directional flow structure in terms of how things work, we're envisioning a much more interactive system where the physics, the numerics, as well as the how the computational implementation works are interactive. Eric, it's over to you.
Thanks.
And that was, I think, 12 minutes.
All right. Is my screen visible?
Yep.
All right. And change slides. Have we changed slides?
Working.
All right. So this is the AMPI specific side of the talk, presented by myself, Eric Bohm, Senior Research Programmer with the Praslin Programming Lab, presenting the work done by myself, Dom, Dylan, Sam, and Justin. So we look at AdCirc-CG as a software target. It is a Fortran-based MPI code, mature, a lot of features, over 100K lines of code in total, most of those in Fortran. And as an application, as previously described, it essentially has this two forms of cells that we're looking at: the wet cells, which have different kinds of real physics depending on the cell. That's where all the real computation actually happens. And the dry cells, which are just there in bookkeeping mode until they actually become wet enough to have real physics. This creates a dynamic load imbalance that emerges from the simulation and changes over time. And so this is a perfect target for the kind of thing we want to look at with adaptive MPI. And the challenge that we face is in adaptive MPI, I'm not going to, this is just the highest level description of it. It has virtualized the MPI rank so that it runs the user level instead of which also makes assumption.
Eric, you're breaking up. So I think it's
and
internet connection maybe.
Not sure what to do about that. Am I still breaking up?
Okay, now it's better.
Oh, I didn't make any changes, so but all right. So I deal with the fact that change the one process assumption, and this creates a problem with respect to global mutable state, which in many programs there's associated with a rank or at least with a process. And now that we have changed the ranked process model, we also have to deal with the process-based variables now being thread-based variables. And so in many cases, this is handled by a privatization approach where we take what was global state and we localize it to user level thread. And API has a variety of approaches to this. The one that we looked at as being most appropriate for EDCIRC is the TLS privatization technique, the thread local storage technique. This is supported in Fortran by adding the OpenMP flag. And within Trump plus usable threads, we can also take the translation of a TLS pragma and localize it to the actual user level thread. And that is achieved by adding the TLS globals flag to the AMPI CC compile line. And then adding the exclamation $OMP pragma for thread private for each variable after it's been declared in the Fortran code itself. So per variable, that's fairly straightforward. However, when you look at a mature Fortran code like EDCIRC, there are over 2,000 dual variables. And so that creates an incentive to handle this in some automated way. And as we look at Fortran global state in general, there are some additional complexities that have to be managed. So as noted, the module available variables need to be handled. But if they have the parameter attribute, they are constants and must not be handled with TLS. Similarly, in a subroutine with a save attribute, those become global and need TLS. In a subroutine with initial value are implicitly saved and need to be handled with TLS. But variables declared a subroutine otherwise are local and should not be given the TLS pragma. Likewise, the old classic common blocks promote variables that they list to become global. And so the common block itself needs to be declared TLS, but the variables within the common block do not. And so, although this is a slightly long list of things to keep track of, they actually represent a fairly straightforward set of rules to apply. And so it is something that we can definitely organize as a process for transformation. Similarly, for Fortran IO, this uses something called the logical unit number, and a LUN is referenced in every IO statement. For the people from the C and C++ side, this is equivalent to a stream or a file identifier. However, it is part of the global state and part of the Fortran runtime. And therefore, in order to manage this sort of safety issue that we have with mutable state, we have to manage these LUNs. And so we have to transform each of these when they are actually file operations. And here, Fortran throws us a little bit of a curve because all of these things that are written as file operations can also be used to apply to strings. And so these transformations must only be applied contextually based on whether or not the LUN in question is operating on an integer and therefore a file IO-based operation, or not an integer, in which case it is essentially a string operation and local to the string address space, and therefore does not require any transformation. So again, a set of rules that we can automate. So we wanted to figure out the best way to do this and looked around at a bunch of projects that might help us to do this. At the time that we initiated this early this year, Flying was not at a state where it could do that. And our most recent examination, it's still not quite there, but we are hopeful that it will get there soon. So we decided to move forward with a proof of concept implementation, just setting up a script to parse the Fortran source code directly using regular expressions, apply the rules that we previously described for variable declaration and IO statements, so that we prioritize where necessary, and integrate a application level module called CKLun, where we simply arithmetically add a rank-based CKLun variable to each integer lun, so that it becomes, in fact, safe to operate on in a thread level way. This creates an additional challenge in that when we actually migrate a rank, we have to close any of the open luns and reopen them after we've completed migration. And the implementation of that was accomplished by Dom, one of our collaborators from Madrid. And that process involved implementing the about to migrate callback, and where he just records the open file in its current lun data state, and then close, and implementing the just migrated callback, where you reopen each of those files and restore the previous lun state. And we have to register those callbacks with AMPI with these two calls, so that when a virtual rank is migrated, it automatically triggers the appropriate callback, and migration can be handled robustly. So current status is that we can run AMPI with AdCirc. We'll compile AdCirc onto AMPI and launch it in both using SMP or non-SMP versions of Charm. We had an initial issue where there was a bug in MPI weight sum that was found and fixed. So we were able to move past that. And we are currently, as we are still only in the very first year of this project, in the finding the problems phase, not the producing results phase. But we are moving fairly well along in tracking down instability in these long runs and coming up with a way to manage support for the NetCDF input form. And our experiments so far have found that the virtualization approach has been negatively impacting performance. Our detailed analysis shows that it is a performance problem related to MPI all reduce being done on the subcommunicators that are used in AdCirc for the ranks that are not IO ranks. And SAM is working on a solution to that. So future work is that we are going to implement the transforms that we have manually scripted in Flying or Flying as augmented by supplements that may be necessary, so that this kind of approach can be applied to other projects more easily, and to avoid having a sort of cumbersome alternate version of the code. We're going to integrate meta balancer use so that we only trigger balancing after a sufficient amount of imbalance has been automatically found. The aforementioned improvements to AMPI's subcommunicator collective performance, and integrating application-specific balancing hints. And some of these have already been designed and in process in the work that was based on using Zoltan as a balancer, as there are some fairly straightforward applications of simply looking at the elevation to help fine tune when one is going to open a list of dry cells to see if they have become wet, and that way you can avoid a fair amount of overhead by not exploring things that have no chance of needing the actual hydrology physics. Furthermore, we're going to be exploring graph-based partitioning due to the connected nature of the operations along the mesh. With that, I'll open the floor to any questions.
All right, thank you for the presentation. I think we have two questions on the Google Doc. The first one by Phil, it's probably for Johannes. What's the distance between those low valleys and high ridges of sea level of the US East Coast?
What's the difference between what?
What's the distance between those low valleys and high ridges of sea level?
You know, that's, I would guess it probably extends out maybe about 100 or so kilometers. So,
okay,
100 to 200, depending on where you're at.
I guess just looking at the picture you showed, I was curious about, you know, effectively like a slope on the ocean surface. But at that distance, it seems like it'd be pretty unnoticeable.
Oh yeah, you wouldn't notice it.
Thanks.
Yep.
And the other question I had, I guess directed to Eric or the other folks on the project is, was there any consideration using ROSE for the Fortran transformation, since there was existing code to do some of the AMPI privatization for both C and Fortran using a ROSE-based tool way back
We
when.
did give it some thought, but the current status of ROSE and future of ROSE was somewhat foggy. And I think Sam's experience with ROSE didn't leave us enthused about trying it again.
Yeah, I won't necessarily disagree with that decision. Even having worked on that code. Thanks.
In the XSpec Center, we had issues with ROSE being able to parse their main Fortran code. And I'm not sure what the status of that is, of ROSE is now as a project. If that's
I think Dan was the only one working on the Fortran aspects. The rest of the team was not. And I think if I'm not mistaken, that project's funding got reduced, so the number of staff is probably small now anyways. But the Fortran, and then now I think we have this new hope on the horizon in the form of LLVM Flang project. And so we are hopeful of that and the lib tooling to do more things automatically. And yeah, I guess that's enough on that. And I think you will hear more about AMPI in the next talk. I suppose we should reserve some of this for that. But I was tempted to say more, but I guess we should do it in the next talk.
Are there any other questions? I think Francois had a question here in the chat about the images Johannes showed. What sets the spatial distribution of the grid nodes?
Oh, so we go anywhere from about, in the operational meshes, from 30 meters, and then they extend out in the deep ocean to about 12.5 kilometers. And then the global meshes go as large as about 24 kilometers. So we're somewhere between 30 meters and 24 kilometers. And in the global operational models that we're building for NOAA, they cover all the world oceans, including the entire Arctic Ocean.
I was wondering about the sort of the refinement. Is that it looked continuous, I guess.
Oh yeah,
what sets that?
So that is done on a lot of functionality that we have pulled out of graphics type of algorithms. So for example, there's medial axes that are computed. There's rates of change of directionality of the boundaries. There's bathymetric depth functions. There are topographic gradient functions. So, and then we put it into a framework that essentially controls the variability or how fast an element can grow or shrink. And that actually is important because you degrade the formal order of accuracy of the algorithms, obviously. And so we set very high controls of that. And because of that complex nature of the channel systems on the floodplain, you get enormous numbers of nodes on the floodplain. And then there's also geometric and topographic complexity on the floodplain. So the ultimate idea is that the ocean is still a simpler place than the floodplain. So right now, whereas the meshes I was showing you are balanced 50-50 between ocean waters, even covering the globe, and land waters, which can extend to, for example, all US coastal floodplains. In the future, we would probably have 90% of the meshes on the coastal floodplain and 10% of the mesh in the ocean. So there's an enormous lob of nodes in the floodplain that, unless it's raining or flooding, are never being used. So that's the whole idea of the load rebalance.
That's fascinating. Thank you.
All right, I think we're right on time for the next presentation. So thank you again, Johannes and Eric. And the next presentation will be given by Sam White and Evan Ramos.
나도 이제 갈 거야. 우리 거 끝났다.
They will talk about recent progress on adaptive MPI.
Can you see my screen?
Yes.
Okay. I'm Sam White.
The slides.
What's that?
Can you try moving the slides so that we?
Yeah.
Okay, it works. Thanks.
Okay. I'm Sam White, and I'll be giving this talk, splitting this talk with Evan Ramos from CharmWorks about adaptive MPI. And so I'll be giving a high-level overview or introduction to adaptive MPI, sort of how it works, a little bit of the inner workings, and then we will talk about recent work. I'll talk about collective communication optimizations, and Evan will be talking about global variable privatization tooling support. So the motivation behind AMPI is generally that we know task-based programming models like Charm++ can help mitigate variability in its various forms. So that can be software or hardware, things such as faults, load imbalance, differing latencies. Can be difficult to tolerate in an MPI bulk synchronous program. But the challenge then becomes how to adopt a new task-based programming model. So for many of the people at this workshop, the answer has been to adopt Charm++ or another task-based model and develop a new code from scratch. But there's also a lot of existing code out there that's already been written on MPI, or people are already trained on MPI and don't want to give up that comfort. So AMPI is our attempt to actually implement MPI on top of Charm++. And so this gives you some of the benefits of both. You get the API and the familiarity of MPI. You can also always take your code and run it on a different MPI implementation, but you get some of the dynamic runtime features of Charm++. The way that this works in practice is AMPI virtualizes the concept of an MPI rank. So when you typically in an MPI library, when you launch your program, you specify the number of ranks, which is equivalent to the number of processes. And so if you do MPI run -n 64, you'll get 64 processes and 64 ranks. In AMPI, we separate those two notions of the rank and the process so that you can have more ranks than you have processes. And these ranks become user level threads in AMPI rather than processes. So in this picture, we show kind of like we usually show char array elements in Charm. We have AMPI ranks that are situated on a different PE. And so you can have multiple ranks on each PE. Here you have ranks 1 through 3, or 0 through 3, all sharing the same PE. And in SMP mode, you even share memory across the whole node or the socket. This gives AMPI some opportunities to optimize things. The benefits are things that are familiar to any charm programmer. So over decomposition, asynchrony, you can overlap one rank's communication with another rank's computation, and migratability. These ranks are actually migratable at runtime, similar to char array elements. And so we can do load balancing with that. Some of the other benefits are, with virtualization, we can take advantage of communication locality. So if you have hundreds or thousands of ranks in the same node, we can take advantage of that user space shared memory. I already mentioned dynamic load balancing and fault tolerance as well. To give an example of what AMPI virtualization looks like, here we have Lulesh 2.0, and on the top we have a projections timeline view of a run without virtualization. And this mini app has a configurable amount of load imbalance. So here we've turned that up some. So you see in the AMPI all reduce purple sections here that some ranks are getting to that all reduce much earlier than others. And the ones that get there later, the ones that get there earlier end up having to wait for the later arrivals to complete the all reduce. On the bottom, we have the same run, but we show a single PE with 8 times over decomposition. So at the bottom, we see this red bar, and that is what's currently happening on the processor. But above that, we see all of these other ranks that are sharing that same processor running in a cooperative fashion. We don't see the purple all reduced time on the main PE bar because we're actually able to overlap that idle time with useful computation. The way that migratability is achieved in AMPI is a little bit different than charm in that we have tried to automate the migration of ranks fully. The way we do this is with a special memory allocator that we call isomalloc, and that reserves a globally unique fraction of the virtual memory space in each process for each virtual rank that could possibly migrate there. The illustration on the right shows that we have this, we have space reserved on each process, but we don't actually have to allocate that. It's just reserved in name only. We are able to migrate both the user level stacks and heaps using this method. And so users don't have to write pup routines for AMPI. We've thought about extending this to Charm++ generally, but haven't quite gotten there yet. It's also worth pointing out that this works on almost all systems we care about now, since BGQ has gone away. The next thing I'll talk about is communication optimizations. This virtualization model of AMPI exposes lots of shared memory between all the ranks and located in the same node, as this picture shows. So if you're messaging from rank 0 to rank 62, those ranks actually share the same address space, so you don't have to worry about crossing process boundaries. That affords us some ability to optimize those transfers. So typically in an MPI implementation, you'll have to, the MPI implementers put a lot of work into optimizing within node transfers via kernel-assisted interprocess copy mechanisms. So there's various forms of these, XPMEM on Craze, KNM, Limerick, other more generic ones for Linux. What we were able to do in AMPI was just use user space shared memory. So we don't have to actually have any current special kernel support to do fast messaging between ranks on the same node. These this work also motivated the creation of a more generic Charm++ communication interface that we call the zero copy APIs. And these now work for both point-to-point and collective routines. But using this, we were able to optimize the MPI to use the full memory bandwidth on a node for messaging, something that no other MPI implementation was able to do on the system Quartz. Looking at how that affected overall application performance, we looked at the XPAC Center's PlasCom2 code. XPAC is a center for exascale simulation of plasma-coupled combustion, and their code is essentially a stencil code at heart. And they've put some effort into optimizing the MPI and OpenMP versions of the code. But we were able to actually see much better performance, almost a 2x improvement using AMPI compared to the normal MPI version. And this was due entirely to the shared memory optimizations that we implemented. For collective communication, this is more recent work. We've been looking at the Charm++ messaging semantics have both in different ways like hindered and helped AMPI. One thing that we looked at was reducing the amount of memory copies we have to make. And because the previous implementation of AMPI would basically copy out of the application's memory buffer into a charm message and then send that every time. We want to avoid those intermediate copies when we have larger messages. So one thing that we've done is optimize for no-keep broadcasts. No-keep is an entry method attribute that says that the application isn't going to modify the buffer or need it around after the entry method. And so the runtime system can take ownership of that. We're able to optimize that to use a single copy per node. So now when you do a broadcast over a char array, there's only one message created on each recipient node, and then all of the char array elements get a pointer to that message rather than a copy of it. We also added zero copy broadcast support, and this allows us to match MPI's buffer ownership semantics. And for reductions, we're now avoiding CK reduction message creation and copies into and out of that on the sender side. So typically, before you would, every time you contributed to a reduction, you'd have to copy that data into a CK reduction message. But we've avoided that now for reductions that are streamable. Another thing we're working on is revamping sections and the CK multicast library for collectives over them. And this will enable us to more easily generalize our work for AMPI communicators of all kinds. So we have some optimizations implemented now for MPI COM world, but we'd like to generalize those to apply to all subcommunicators. The first series of optimizations were for small messages. And so what we did was avoid the CK reduction message creation and copies. And then further, we looked at how to use a shared buffer per node per communicator to avoid having to dynamically create and use memory for reductions. And so we were able to get down much closer to Cray MPI on Cori for a single node reduction here. Whereas previously we were almost 10 microseconds, now we're down to about 3 for 16 times virtualization. For large messages, we switched to using this optimized no-keep broadcast feature, and we also are using the zero copy communication APIs for large messages. So these plots don't actually have the small message optimization in them. I just realized, so you can ignore the smaller messages under 4K here, but for large messages, we're now doing much better and avoiding the per rank copies that we had before. The last thing I'll talk about is memory usage of AMPI. We looked at multiple kinds of memory used inside of AMPI and how to lower our overall memory footprint and reduce the amount of per rank memory that we're using. So one thing is with these zero copy APIs and our fast shared memory communication, we've been able to lower the rendezvous threshold lower than most MPI implementations while not trading off latency, because we're avoiding this kernel-assisted interprocess copy mechanism and its overheads. We've also lifted a lot of AMPI's read-only memory storage from the per rank level to the per node level. And this includes storage of built-in things like data types, reduction operations, and groups. The last thing is we've extended the zero copy API from just communication to the PUP migration interface. So we have a new zero copy PUP API that allows you to migrate a char. You could use it for a char array elements, large buffers. You can migrate those in place. So what this looks like in an actual AMPI application, this is Jacobi 3D looking at the memory used on a single PE for a one node run on Stampede 2. We've reduced the baseline memory usage of AMPI by lifting things to the node level. We've also eliminated the smaller spikes that you see here. Those were communication phases, but now all of the memory that AMPI uses for messaging is either pooled in the common case or things are done in place, so we don't actually dynamically create memory for them. The largest spike that you see there is for load balancing, and the spike has been reduced in its height because of the use of the new zero copy API for migration. So we've limited the amount of memory that is needed during a migration phase. Next up, Evan will talk about privatization techniques.
Okay, let me share my screen. Okay, can you see the slides?
Yes.
Okay, so I'm going to talk about automatic privatization in AMPI, and that has to do with global variables. So global variables are the foremost obstacle to running existing MPI codes on AMPI. Anyone who has made a reentrant shared library is familiar with having global variables in your code, but if you need to open more than one instance of it, that will cause conflicts as illustrated by this example code here. Now, new MPI codes can be written with coding standards that avoid the problem entirely by not using global variables. But as far as legacy codes, getting these codes to work is something that's very important for us. So you can see here in this example, each rank in this MPI code would get its rank number into a global variable, have a barrier, so there's some kind of control flow change. And if these were all virtualized ranks in an AMPI program within, say, one process, then the result you get from this print statement is not going to be correct. And that's what we want to avoid. So the first thing you can do if you want to get rid of global variables is to manually change your code. But that is difficult. It can be a lot of time and effort in order to pinpoint all the variables and restructure the code. so that you have this extra data that's going from place to place. But one benefit of doing that is that it's completely portable to any system you want without any of the potential drawbacks of the other methods that I'll discuss here shortly. So if we don't want to go through the process of manually privatizing your variables, there are some goals that we would want to keep in mind, and some of the methods we've developed over time have not met these, so we've kept on researching to find new ones. Basically, it comes down to, is it easy to use? Can we cut down on how much work the programmer has to do as much as possible? Is it portable? Does it work no matter what your operating system is or your compiler, or even what version of system libraries are? Sometimes some things require patching the system libraries, and we want to avoid that. That's an extra burden on users that they shouldn't need to do. And as well as, do they also support all the nuances of code, such as all kinds of global variables, all kinds of linking, and most importantly, the ability to migrate at runtime, which is AMPI's killer feature. So we've had some older methods that we still have around. I think the oldest one still in existence is called swap globals, and that's a trick that looks at the ELF structure for your program at runtime and will change all the pointers to the global variables. But unfortunately, this is deprecated now because the GNU linker has broken it, and reinstating it would require some extensive changes to it. It never migrated or worked with static variables in the first place, and it also has a context switching cost that's linear in the number of global variables. So we've deprecated swap globals. And the other first generation one we have is called TLS globals, which uses thread local storage in order to store all your global variables. So all you have to do with this one is add the tag thread local to your variable declarations and definitions. That works for C11 and C++11. Older ones can use __ thread. And in Fortran, you can use the OpenMP thread private directive. This is well supported on Linux and Mac OS, has a constant time switching cost, but it does still have the side effect or the issue that some effort is required. You have to go in and identify variables and make sure they're all tagged correctly. So besides these methods, we also considered, what if there's some kind of automated tooling that can change your source code so the global variable problem is fixed in that way? And we have looked at some tools such as Camfort and Fortran and done some work on rows, as we've talked a little bit about already today. But the one we're really looking at is CLang and libtooling. It's a very robust infrastructure for making changes to code. We do have a prototype using libtooling that can add the thread local tag to code automatically, which can make TLS globals more attractive to users. And we are interested in building one that can use the encapsulation method so that there's no dependencies on runtime support, it just works right. Recently, we saw that FLang, or F18, as it was previously known, have been merged into LLVM as of version 11, and we're very hopeful at hopefully being able to extend the support to Fortran in addition to C and C++. So besides those, we've also had some bespoke scripting efforts. Eric talked about his script for privatizing variables and ones for the AdCirc project, and that's another option we have at our disposal as well. More recently, we have a second generation of methods, pip globals and FS globals, that take your MPI program and will build it as a PIE shared object, which stands for Process Independent Executable. And what makes those special is that they store and access global variables relative to the instruction pointer. So if you use these calls, as our friends at Riken did, DLM open is a GNU extension to the C library that takes a namespace index. And if you increment it and pass it a new index, it will create a second copy of the program in memory, which will privatize your variables. It will have, if you call DLSym, it will give you a different pointer and to whatever entry point it is, and whichever one you jump to is the one that is the context that will activate the global variables, so to speak. So pip globals use DLM open, and file system globals is more of a hack. We just copy the shared object on disk per rank, which is a little bit inefficient, but it has some uses still. And these are being tested nightly on production machines like Commodity Linux, Mac OS, and some Cray systems, and so on. But you can imagine these do have some drawbacks. For example, the DLM interface that pip globals uses is has a limit inside libc, and it ends up being about 11x over decomposition, which is okay, but we wish we didn't have this cap, especially because it's per process and not per worker thread. So in SMP mode, this level is quite low. You could patch glibc to get over 300, but again, we want to keep user effort minimal. File system globals has its own issues with copying, and it doesn't support shared objects, so that's more of a proof of concept. And of course, neither of these support migration because the location of the code and data segments is handled entirely by libc and the system. So if we wanted to resolve these drawbacks, we could patch the Linux loader. Again, we don't want to do that. Or we could try a new method we've been working on called PyGlobals, which does some things on its own. So it takes the infrastructure from pip globals and file system globals. It opens the object once and then uses a different GNU extension to locate all the program segments in memory and make copies of the program for each rank to our isomalloc segments. Then there's a step where it has to scan through the data in order to update function pointers. This is it's a naive scan, just does this look like a pointer between point A and point B? And if so, do some math to fix it. That has a little bit of an issue. We'll come back to that in a minute. But other than that, we have, without any changes to the user's code, it can become privatized and migratable. So we've demonstrated success with this with Minighost and with Neckbone. And we are working toward OpenFOAM and MPI for Pi support, which is very promising. But the method does have some drawbacks of its own, some things to be aware of. For example, there is this overhead at startup. If you went through the effort of privatizing your code manually, you could just run your program, but we do have to do this processing at the beginning of every job. Debugging can be a pain because we are just moving the text segment around in memory. The debugger doesn't know what it's doing anymore. So we recommend debugging without the method if you have to. And then if you really have to, we provide a method compiled into the code you can call from GDB that will take an opaque pointer and try to match it back to where it came from, which might give you the name of a function or a symbol, something that may be a helpful detail for you. The scanning that I mentioned earlier, where we have to find pointers to the code or data, like self pointers, and change them, that can have false positives, particularly in code that does a lot with C++ global constructors and the heap. So OpenFOAM actually runs into this. It opens a lot of script files at init, and it actually falsely matches a pointer. So we want to fix this issue by augmenting our scanning. So it will use the DLM open from pip to open two copies, scan them pairwise, and if it is a true pointer, then the content should be different between them. if it's a false positive, then they should be the same, assuming everything else is deterministic. There is a slight performance issue compared to perfect manual privatization, and that's that the code is duplicated in memory, which causes instruction cache bloat and is also extra overhead at migration if it's being transmitted over the network or to disk. And we do have potential solutions to these in the works for the future. And this method does require Linux and a GNU userland. So in conclusion, some of Sam's results showed that AMPI is increasingly valuable to different applications, even without load balancing. And we've also made it easier for users to bring their existing codes to AMPI and get some results. We've been working on all parts of AMPI top to bottom, including conformance to the standard and how other MPIs like OpenMPI work, improvements to the communication and memory, making privatization easier, and also reaching out to new application developers. And as Professor Kale mentioned this morning, we are going to rebrand AMPI as Charm MPI to better emphasize the underlying technology and sort of start a family of different projects that are all uniquely identified as Charm. So with that, if you have any questions for Sam or myself, we can take those now.
All right, and thank you for the presentation. I think we had 2 or 3 questions on the Google Doc. Phil, do you want to start with your question?
Thanks, sure. First question was for Sam about the reduction optimizations and the comparison to Cray MPI. How much of the remaining overhead of virtualization is just the actual added arithmetic loops of running 15 times more actual reduction computations?
Yeah, so the table that I showed was for a single integer sum.
Okay, so it should be pretty trivial then.
Yeah, so the most of the time there is likely from the scheduling of 16 ranks on each PE, switching between those.
Okay, thanks. Yeah, if I'm continuing, I guess the other question for Sam or Evan, both, for the various privatization techniques you mentioned that potentially involve patching system libraries, are the functions involved amenable to sticking in an LD preload? So you just get, AMPI's version of those functions and the rest of the standard library stays the same?
I think I tried doing that by intercepting mmap, and it would not intercept. The library is internally linked, so you can't do that kind of thing.
Okay, thanks.
And we had one final question by PK Goodla. Do you want to go ahead and ask your question? I can also do it if you want to. So he's asking, are there any performance benefits for developing applications with Charm++ as opposed to going the route of MPI plus AMPI?
Yeah, there's a few considerations, but if we're talking about just performance, I guess the biggest difference would be in AMPI, you're relying on much more on our implementation of things versus in Charm++, you can, in many cases, optimize things more on your own. So if you want to add a group or node group, for instance, to a Charm program to aggregate some sort of messaging within a node, it's a little more transparent in Charm to do that. And there's also a little bit more of what I would call like expressivity in Charm for asynchronous applications. In MPI, you're using the regular MPI programming interface. And there's ways to optimize things by creating communicators via like MPI COM split type that are routed to nodes, but it's a little bit, I guess, a little bit more work at the application level to do that.
If I can add just a little bit to that, I mean, this is a decision that's to some extent subjective. It's a mix of subjective and quantitative decision. So many people, especially in our group, right, think that if you're starting to write an application afresh, they would prefer CHAM++. But that's because they're used to programming in CHAM++. The MPI has had many people are exposed to it, many people know about it, and so if they might have a subjective preference for it. It has this somewhat anthropomorphic feel to it, right? I mean, I'm a process, I do this, I send, I wait for something, and that's also appealing. The other thing is, I mean, Sam already mentioned some of the other reasons, but the other thing is that you might, for example, think that you are taking a smaller risk by developing it in AMPI, that you or that you want to keep the option open of reverting to regular MPI. That's another reason why you might use AMPI. So I think that pretty much covers it. Anyone wants to add anything? Maybe Phil, do you have a thought?
I think at this point I'm far enough out that I don't get to pontificate about it anymore.
Okay. All right. So I think this is a very important question that we need to address for people about which technology to choose. And you might also ask, why not CHAM for Pi, the Python thing, the same kind of issues. Underlying runtime support is common in all of them. Then a lot of it depends on what programming system methodology you like.
All right. There was one final question by Celso Mendes. He's asking if Pi globals can only be used to G-Fortran. Is that correct?
So it doesn't have to be compiled with G-Fortran. If you have a compiler that can output as PIE, that should be all it needs. But what you do need is a GNU userland, so like glibc and the GNU tools and that kind of thing. But G-Fortran is not a hard requirement, no.
All right. I think we're already over time. So let's continue with the next presentation. Thank you again to Sam and Evan. The next presentation will be by Mike Robson and Kavita Chandrasekhar. Flexible hierarchical execution of parallel task groups.
All right, thanks, Matt. If you can let me screen share, I'll put my slides up. There we go. It's just like teaching my course on Zoom earlier this morning. All right, hopefully everyone's able to see that. Can I get a thumbs up or a nod from someone just to make sure?
What's the black screen for now?
Black screen, what about now?
Better.
Okay, cool. All right, so thanks for that introduction, Matt. Like he said, I'm Michael Robeson, former PPLer, now an assistant professor at Villanova University. So I'm going to be presenting work that I did as part of my dissertation on flexible hierarchical execution of parallel task groups, and then a continuation of that work by current PPLer, Kavita Chandrasekhar. So people who give keynotes love to talk about trends in architecture, so I'm going to copy them. So this is a slide from Sanjay's presentation at Solishan 2 years ago with data compiled by a former student, Nikhil Jain, on injection bandwidth versus CPU speeds. So you can see kind of as we move forward in time, you know, things like BlueGeneL to Summit, right? We've decreased the bandwidth versus CPU speed. So basically this means while we've been increasing performance on the nodes, the actual network capacity has not kept up, right? We saw this last year. So this is a recreation of a slide from Steve Plimpton at the keynote of last workshop that basically replicates the same idea with, increasing LINPACK performance and an increasing number of flops that have to be covered memory movements either from local data or remote data, right? So sort of as we go forward in time, networks become more and more of a constraining factor. So general idea is we have these deeper nodes, thinner pipes. There are a lot of reasons for that. I only caught a bit of Jeff Vedder's talk this morning, but talking about heterogeneity and accelerators and GPUs, right? And so this is contributing to it, but it's not really solving a lot of these problems. So, in general, the picture kind of is, we find ourselves with these nodes that are connected by an internet that are getting deeper and deeper, and we need to find a solution, right? So one possible solution that we're going to examine in this work is the idea of combining OpenMP with Charm++ and the idea of spreading, right? So the idea of spreading is flops are really cheap. We have these very powerful nodes. They have tons of cores. They can do complex calculations very fast, but we need to, in sort of the Charm++ vein, inject communication as early and often as possible, right? The network is going to be our most constrained resource, and we want to use it wisely. And we'd like to have sort of a steady, continuous trickle of data and packets and information onto the network flowing everywhere, as opposed to these big bursty dumps of information that then make the network the critical path, right? So what we're going to look at today is using OpenMP to speed up individual compute loops, and then combining it with the Charm approach to get better communication computation overlap. So what might this look like in graphical form? I think this is the best way to explain this concept. So here we have two axes. One is the spreading factor. So basically the number of cores that an individual task is going to run on, compute loop, an object, whatever you want to call it. And then that's on the y-axis. And then on the x-axis is the amount of over decomposition. So basically the number of objects per core, right? So, our traditional approach here would be, basically one giant object that runs on all the cores, right? We know this is OpenMP. This is basically, shared memory parallelism. So we start out here, right? We also have the idea of MPI, which is sort of the other side of the coin, where we basically divide the data we want to compute into separate processes or separate ranks, right? Each of those are on an individual core, but they're only running one thread at a time, right? So, OpenMP and MPI, and MPI plus OpenMP exist, of course, and we'll get to that in a second, but these are sort of our two major paradigms, right? Then we have kind of the Charm approach, which introduces the idea of over decomposition, right? Instead of having just a single object per core, we can now have multiple objects. Keep in mind, this is the same computational problem, but divided up with various timelines. So these maps here are supposed to represent sort of what a projections view, an idealized projections view would look like. So in this Charm case, we take our same, two-dimensional stencil, for instance, or whatever your problem is, and instead of dividing it into one object per processor, we now have two objects per processor, right? And obviously Charm is known for, big over decomposition. This axis, extends kind of off the screen here, but it demonstrates the basic idea. So what I'm focused on is kind of this area here that's left unexplored, right? So, what happens when we have not only multiple objects per core, but also we then, use those objects to run across several cores at the same time, right? So via OpenMP. So this is kind of the, MPI plus OpenMP area. And then now we're getting into over here, the, spreading Charm++ OpenMP combination, right? And so you can see by taking this same division of labor, right, these same 8 objects, and now by running them on 2 cores at a time instead of 1 core at a time, we're injecting data, twice as often, right? So we're hopefully going to have a little bit smoother of a curve and improve our performance, right? And this now kind of allows us this new axis of optimization, right? So, as before, Charm provided this idea of over decomposition, which hopefully, by now you're familiar with, but it also allows us to, dial in how much resources are assigned to a specific task, right? So, over decomposition is not a, one size fit all tuning parameter, right? So now we can also kind of say, okay, maybe my, grain size makes sense at a certain size, but I want to have it execute faster to be injected on the network more regularly. I can't make it any smaller, but I instead can spread out that work across multiple cores. As we'll see, it has a couple ancillary benefits like better cache utilization, but this is the general approach. So to test this hypothesis, we set up a basic Jacobi application in Charm plus OpenMP, ran it on a couple of machines, and then examine the performance, right? So in this case, these were built with non-SMP mode. So because of the way this prototype was set up, we had to have a separate process, and then each of those processes spawned their own version of OpenMP to distribute the work. We'll actually look a little bit later in the presentation about the work Kavitha has done to extend this, where we sort of get rid of that, but that's the case for now. All the normal optimizations, and then sort of the numbers if you're interested. This is run with a grid size that's approximately 90% of the total memory of the node, depending on the actual node. And then various block sizes so that we have a large number of chars. And we average this, for 100 iterations in most cases across 4 nodes, although we do scale it up. We also use a variety of OpenMP pragmas. So we use a static schedule to examine the performance, right? This is a regular application, right? There's no big variance in load. We will talk about load balancing at the end, and it's one specific advantage that Charm has, but not something we're examining here. And we also try the collapse parameter, which we saw give increased performance occasionally and various chunk sizes. So like I said, we ran this both on Bridges, which is at the Pittsburgh Supercomputer Center, right? It's a 28-core Haswell machine with each node having 128 gigabytes of memory, as well as Summit at Oak Ridge, right, which has a 44-core Power 9 chip, along with 512 gigabytes of DDR4. I mentioned this because we actually see really good performance with big objects, right? If the objects are too small, if there's not enough work to spread out, sort of this technique isn't as effective. So if you have a lot of lightweight objects, spreading isn't as helpful, but if they sort of have, a computationally intense object, then it's worth kind of spreading it out and making that trade-off with OpenMP. So on Bridges, we ran a couple experiments. So as a baseline here, we have Charm++. Charm in this case has a single thread, right, per core. So this is the non-OpenMP case, and that gives us a baseline to compare against. And then we have a couple of different OpenMP experiments. So the default static decomposition, which is giving each core the total number of iterations divided by the total number of cores. So a big chunk of work at a time versus one chunk at a time in the static one version. And then we also add in the collapse parameter. And you can see we kind of get a distribution of performance here. So by increasing the number of threads we assign to the objects, going from left to right here, with 2 or 3 threads, we're seeing in most cases worse performance than Charm++. And then we sort of hit our sweet spot around 4 to 8 threads, right? So each object is executing when it's running using OpenMP to run that compute loop across 4 cores. So this is on, let's see, 40 or 28 core machine. There are 7 processes, and each of these 7 processes has 4 threads. And then we are, kind of set up that way. So you kind of see there's a sweet spot here, and it will change based on, application characteristics and machine characteristics. So if we move to Summit, we see similar gains of about 20 to 30% over the Charm baseline. So in this case, we run various block sizes. So here, Charm is represented by the blue bar in all of these experiments, and then the OpenMP approach is represented by the other colors. So you can see kind of independent of problem size decomposition. So this is, controlling for grain size or decomposition. Here we still get mostly improved performance. Cases like 19,000, it's a little less of an improvement in the best case versus say, 29,000, we see some really good improvements, right? This gap here. But in general, it's a pretty effective approach. We also examined the effects of various schedules. So in addition to, a fixed single iteration per schedule or the default number, we picked 16 and 512, and again see a similar approach where we have our charm values here with the various block sizes that were the most performant, and then comparisons with all these schedules here. And again, kind of based on a matrix of these parameters, we see the best performance here with 7 threads in this case on Summit, a bit bigger machine, a little bit more memory, and we're able to spread out a little bit more and see more performance. We've also tested to make sure the scale, so all these experiments were multi-node, but just on 4 nodes to be able to test them quickly. But it does scale, up to 256 nodes. So this top line up here is the default OpenMP, and by default, I basically mean MPI plus OpenMP style, one big OpenMP kernel running across all the threads, and then using charm for sending messages for the data. Then we have the default charm approach, which you can see is much better. And finally, 2 of our best performing versions of our spreading idea with either 7 or 21 threads are able to scale pretty well, in fact, better than either the 2 versions that we have above, and also still get us that better performance, jumping down from 35% to 35-second iteration times to 28 seconds. All right, so might ask yourself, okay, well, is this some rearrangement? Is it just cache benefits, right, that a single node would get? And the answer is not really. So we reran this code on Summit without any send. We stripped out basically any of the communication parts and then looked at the performance. So in this case, here we have OpenMP, which is without any of the charm baked in, and then also blue here is charm, and then yellow and green are our spreading approaches. And you can see we do a little bit better. We do get some performance improvements, but they're on the order of 5%. When we actually reran this using PAPI, we actually looked at performance counters and saw we were getting better cache performance. So we kind of attribute the speed up there to just better cache behavior, right? So by spreading out the work, each of these objects is now being, subgrids of it are being computed on separate cores, so we can be stored in smaller levels of cache for faster access and less cache misses, which leads to a small amount of speed up. However, it doesn't account for, the nearly 30% amount of speed up in the other experiments. So, we're pretty confident that we're having a good impact there. And in fact, to back that up, we actually looked at the communication performance using projections. So we again ran these same experiments, collected the same data with trace projections turned on, and then looked at sort of the various time profiles. In this case, all of these are for the same experiment with different spread factors, and their timelines have been normalized, right? So I'm basically showing you over roughly the same amount of time, what does the communication volume look like across our different approaches, right? So OpenMP, not so surprising, there are these huge bursts of communications, right? We finish one iteration, everyone tries to send out and receive a bunch of bytes on the network right at the same time. And then we do another iteration, and because maybe receives happened a little off, we're now sending and receiving a little bit earlier, a little more dispersed, but still this huge spike. And then again, a third iteration here, you still see it spread out, but these peaks are really high, right? So we're kind of really doing this bursty communication that's really, making our network a bottleneck and making this a really important part for the network. And then otherwise it's totally silent, right? Like we don't care about what it's doing at all, which we've learned is not great for performance. To compare that with the charm version, you can see just by doing over decomposition, we already ameliorate some of that problem. you know, you can kind of see there are spikes as iterations come and go, but, you know, nowhere near the same highs as the previous OpenMP only approach. But it's still really bursty, right? It's like not totally perfect. We're still, you know, kind of going in patches of injection. We want to smooth that even further. So by actually, you know, sort of continuously injecting, having objects that are running as quick as they can across multiple cores, we can smooth that even more. And now you see an almost perfectly smooth timeline, right? You can't even really tell where the iterations begin and end. I mean, there are little rises and bumps, but now it's a sort of approach where the information is sort of constantly flowing over the network. It's really being used at a low level all the time, which leads to this improvement in performance, right? And we can kind of see these all stacked together. So as a reminder, this is the CHARM approach, right? Which is better than this OpenMP big bursts, but is not as good as the, you know, spreading approach, right? So you can see here kind of the peaks of the blue versus the peaks of the CHARM, and then the peaks of the OpenMP. Okay, so that was the basic prototype idea. We got pretty good feedback, saw that improved performance, and so we started moving into integrating it into the runtime. So this is work I'm now presenting by Kamitha. This is kind of where the handoff point was, and she started taking over. So one thing she started looking at was automating this configuration of teams. So teams is a concept in OpenMP that allows you to sort of have a hierarchy of parallel task pools. And so, you know, previously when I was running these experiments, I had to run them by hand, you know, set up the OpenMP threads and the processes and invoke them, you know, manually and rerun them and get all the different experiments, right? But, you know, we're CHARM, we're an adaptive runtime. We want to make these decisions automated, and we want this to be easy for the user to understand, right? So now, in addition to how many OpenMP threads am I running, we need to think about how many teams, how many masters and drones should there be, right? Basically, the number of CHARM schedulers versus the number of threads that kind of run underneath them. How does this play effect with cores per processor, the total number of processors and the processes in the node, et cetera, right? So there's a lot to take into account here that we don't want the user to totally be swamped with if they're just starting to use this. So what we ended up doing here with this approach is basically fire off OpenMP to create a master thread on all of the cores. So basically have OpenMP set up a master and then spawn subthreads when we needed to do the work. This is the idea here is we want to integrate this into the load balancing framework such that, you know, as the program evolves and executes, if we have, you know, a dynamic case and maybe you need more or less threads per object as the program executes, you could actually sort of rearrange these master threads so you could increase or decrease their counts, right? So we can use this OpenMP nested parallelism to sort of change the ratio of masters to drones and use P threads, you know, to kind of update the affinity of those threads as the configuration gets updated at runtime. So the idea here is that the runtime will select the best configuration after testing a couple of different combinations, basically one per load balance step, and then run with that for the rest of application. And in fact, you know, if the application was really dynamic and evolved over time, it could retest and sort of reallocate these resources to further improve performance. So an example of this, using OpenMP for nested parallelism. So this is, again, just using a static configuration schedule for OpenMP. This is on the same Bridges machine, and it compares the OpenMP performance of SMP and non-SMP modes. So if you remember previously, basically this is my approach here, where each CHARM scheduler, right, each PE, each master thread is a separate process, and then all of the threads running underneath that master process, you know, spreading out that OpenMP loop inside an object, are spawned, you know, inside the process. But, you know, within node communication, across node communication is all inter-process, right? This is especially important locally. By switching to SMP mode, where instead of having a separate process for each PE, we now just have a separate scheduler. This gets improved performance, right? So you can see basically dark blue here is CHARM only. Basically there are 24 CHARM schedulers, 24 PEs. And by increasing the number of threads assigned to each PE and decreasing the total number, we can potentially sort of shift that ratio. But since we're running only on a single core here, we don't see much of a difference, right? Which is basically what I expect. And in fact, on the high end, when we're running with just a single scheduler and 24 threads, we kind of see decreased performance, showing that over decomposition kind of somewhere in the middle is the best approach, right? So then taking this approach further, where we're using a single process in SMP mode, and then spreading it out using this Teams approach, we can look at its performance on Stampede. So this is now a multi-node sample. So this is on the Skylake nodes. It's a 4-node run. And now you can see where the Charm++ approach here is in dark blue is pretty good. And in fact, is better than just the OpenMP approach in dark orange, but is not as good as this light blue approach where we kind of hit the sweet spot, right? So with right about 6 threads per PE, that, the ratio of 4 master threads in this case and 6 worker threads, that gives us the best ratio of performance and is able to, again, decrease our runtime from on the order of, 50 seconds per iteration to 35. So pretty big improvement there. So how do we do this? So this is some sample code that has from the OpenMP implementation we're doing in Charm right now. So basically she modified the machine.smp file, machine-smp file to, have each thread to have each scheduler go ahead and spawn a parallel section, right? And so, we set the number of threads based on some input number to create here, and then we, get our thread number and then call the start function to actually begin execution. But now the entire program is basically nested inside a parallel section. So our workers are already created. And when we hit an OpenMP block, like this OpenMP parallel 4 inside this Jacobi example that we've been running, we can automatically farm those, loop executions out to these already created threads, right? So basically we have these master threads started by the runtime at the beginning of the program. And then when they encounter these blocks, they can automatically assign the work to their sort of sub drone threads or their worker threads as needed. So this configuration has both a static and dynamic option, where the static option basically uses OpenMP style affinity to, in this case, if there are 8 cores, set affinity and then bind those processes in a spread fashion. Whereas we'll look at in a second, we could in fact instead do dynamic configuration via the pthread set affinity call. So the pthread affinity, if we look at that performance, so again, this is process-based approach. The OpenMP, so this is using the standard GOMP style affinity, and then pthread affinity gets similar performance to the process-based and OpenMP-based implementations, or OpenMP affinity implementations, barring some NUMA effects. So the reason we want to do this, though, is that with OpenMP, nested parallelism can't change the configuration dynamically. Basically, if we want to grow or shrink the number of master threads and worker threads, that's not something we can dynamically change. Instead, if we use pthread affinity, when we change the number of masters and workers, we can actually reset their affinity such that they're correct for when we grow or shrink those pools. So with Charm and OpenMP, pthread affinity sort of lets us do this update over time. That's kind of our ultimate goal. Right, so here we can select the best configuration, which is this one here. So next steps and things that we're working on now are basically integrating this approach into the load balancing framework so that it's fully automated. So right now we can dynamically set this configurations at runtime based on the user input. And it lets us, it's better than the static configuration, which I showed earlier, because we can change this at runtime, but it's still not totally automated, right? We can't change this in the middle of the execution without intervention from the user. We also plan to look at the CK loop implementation, right? This is sort of the Charm native approach to spreading out the work of loops. as things execute and see the performance differences there. So in summary, the idea of spreading, right, taking an object and spreading it out over more cores to inject more often offers a new optimization parameter. And as we saw, kind of early prototypes showed it increased performance on the order of 20 to 30%. This spread factor now in Charm is controllable at runtime. And we're ongoing efforts to basically integrate this more deeply into load balancing. So it's totally automated and just another thing that sort of Charm delivers to the user without their intervention at all. All right, so I think I'm about on time here, and I will wrap up now and take questions. And so this is both my and Kavitha's emails. In case you have a question, don't get to ask it now. Thanks for listening.
Thanks, Michael. I think we had a question by Phil, if you want to go ahead.
Hi. So first, a quick one. Which OpenMP runtime implementation is this using? The native one from like the compiler or the one that's built into Charm++?
This is the native compiler OpenMP runtime. So this is like a orthogonal work to Jamin's OpenMP tasking Charm library stuff. That's yeah, good
Great.
clarification.
Yeah, and you mentioned that you can, control your spread factor dynamically at runtime, but it sounds like you're tying that to load balancing activation at like a per time step kind of boundary. For more sophisticated applications like NAMD or Changa or OpenAtom that have like lots of different computations in any one time step, would it make sense to change that factor even like within a time step, depending on what kind of work is predominant?
Potentially. So if Kavitha is here, she can chime in with her thoughts as well. I mean, it's just not something we've studied about the overheads of how quickly we could, spawn new master threads and thread pools and reassign the work. But if assuming the overhead is low enough, yeah, no reason you couldn't do that. I mean, the other thing is you could, if it doesn't make sense to spread it to extra cores, say you want some to go on 4 cores and some to go on 8 cores, right? You could spawn, enough master threads so that you have 8 threads available at any time for an operation. And then, per entry method, right, you could assign it, okay, this one only needs 4 cores, but then you're losing out some of your computational units as it executes. So yeah, I mean, it's definitely an interesting idea to explore and like a good next step of how quickly can we do this and reassign work and improve performance.
Cool, thanks.
I can add something, Michael, to that.
Yeah.
This method when you change the number of masters, you basically are performing an implicit migration of chars. Not implicit, I mean implicit for the programmer, but they are actually migrating to these master threads. And then they have a domain of drones to spread their work to. That's the way by which this current method works. What you want can be done with CK loop easily. To do with OpenMP is a bit tricky, and we haven't thought. I mean, basically, I would even, and then Harshita's method of task stealing. So those are competing ideas there. And then, of course, using, you said, Jamin, I think it's Sun Myung's OpenMP LLVM implementation, kind of the same way Bolt does it, is to use user-level threads and trick LLVM into thinking of those user-level threads as P threads, and then use our runtime to spread that work to different cores. So there's a kind of collection of methods there that we need to find the right combinations to explore.
Are there any further questions?
You had a performance data that didn't look good. I think when you had, like, if you can go back to the thing which said compared the dynamic set thread affinity method.
I think this one here.
Yeah, you have that red circle on that first of all. So then the optimal is at the charm end of things. That doesn't sound good. It should be in the middle. But even otherwise, all the bars on that right set are worse than the bars on the left two sets. So there is something.
Yes, you're not wrong. I would answer your question, but this is data Kavita gave me, so I don't totally know what's going on here. I mean, other than I think this is kind of what we had discussed privately about using p-thread affinity lets us have more flexibility at the cost of some overhead.
I think that maybe, I mean, you can say that, but I think the real answer in my mind is that we need to look at this more and to see where this overhead is coming from and fix those sources of overheads so that it can match or do better than the one on the left. And then we can claim, yes, we have flexibility and we get performance.
Yeah.
Kavita,
my other idle speculation or wild guess here is that if we changed the block size, basically the over decomposition, like maybe the objects are too small and so the overhead is eating into our performance here. So we had less number of larger objects, we might see a different trade-off. But yeah, no, it definitely bears, this is what Kavita gave me yesterday. So we're still, very fresh numbers that still need more examination, like you said.
Yep, that's what I wanted to bring forward. This hopefully should get better.
Any other questions?
I don't see any, so I think this concludes the session. Thank you again, Michael, for the presentation.
Thanks for having me.
And
So
this concludes the first day.
Well, any questions or announcements or discussions? I have one thought. I wanted to say one announcement, but maybe I'll get feedback from you guys. I was thinking tomorrow after one of the keynotes, maybe after the first keynote, we could do a traditional photo session for the group. This needs a previous warning because then you wouldn't be in your pajamas. And then we'll do a Zoom picture of that screen, or actually maybe a small video, record a session of everyone saying hi. That sound okay? If there is a way of voting, vote. Otherwise, just consider that to be a suggestion. And yeah, oh, good. There is actually a thumbs up there. A response, I guess. Reaction. Reaction.
There's a reaction thumbs up, but I don't think there's a reaction thumbs down. So might be a bit biased.
Confirmation bias of some sort here. No thumbs down. Oh, you can do that open mouth if you want for thumbs down. But anyways, I think let's do that maybe at the end of the first keynote.
Right. So the first keynote will start at 9 a.m. tomorrow Central Time. Yeah. So 10 a.m. we would have to.
Right. And thank you. This was my first whole day workshop since this pandemic began. So thanks for staying through and listening in this new mode. All right. See you tomorrow.